Well, good morning, ladies and gentlemen. We hope you had a good night's rest because it's been a full day and a full night last night. That night's sleep was not nearly long enough, but we had a great day yesterday with a lot of great information, talking to doctors, researchers, and fellow SPFers who are here. The fellowship, as you guys know, when you get a chance to be here, is very good, and so we always meet new people, create new relationships, and spend time with old friends. And so if you're at home, we've missed you, but we're glad that you're with us virtually at home. And as we talk about last night, if you were able to watch, you saw that we had an auction and a lot of hands going up and money being raised. And last night, I think, we don't have an official count, but our estimate at this point is that we finished somewhere last night between $30,000 and $40,000, and that's a good step toward a research project. So I want to first of all thank Vicki Joins for that beautiful quilt that she made that was auctioned. The Maria Koduri Foundation, Vamsey and his family, the beautiful jute artwork that was auctioned. And then, of course, Dr. Ozdinler, you guys know she's done that before, and she did it again. Yeah. And when the night was over, she grabbed the microphone and said, "We're going to raise more money." So
and she did.
So we appreciate all of that work and all of you, all of those who contributed by buying those. And then people were making just extra donations as the night went on. So that's all important, and we appreciate that because it takes money to get fundraising done and to make things happen. Norma's with me again this morning. As you guys know, we came to Washington to talk to federal regulators, particularly NIH and FDA. And with the shutdown that's here in Washington, those people could not come and be with us. So Norma has worked hard to fill the agenda. We've had other doctors and researchers here who are more than capable of filling in and talking to us about the things they're working on. So Norma, first, today we've got a couple of spots to fill. Tell us real quickly about our agenda today.
Thank you so much, Greg, and thank you guys again. I cannot appreciate all the work that happens behind the scenes. But we have in our audience John Audhya. He is one of the researchers that we have funded in the past, and there's, I think, some proposals that he and the University of Wisconsin is also working on for this next coming year. He will replace Walter at 9 a.m., so please don't think that we're going to take any breaks in that regard. And then in the afternoon, we have at 4 o'clock, Lindsay Perlman joined us yesterday from the Paralyzed Veterans of America. So you guys, if you were on with us, you saw her presentation yesterday, and I think there were 3 or 4 veterans in our audience that raised their hands. So I was very glad to see that. You guys know that we sent out, for those folks that are veterans, we did send out an e-blast earlier in the year. There's some researchers that are working with, I think, the Paralyzed Veterans of America to see about some research dollars in that population with PLS patients and with the veterans. So she covered that yesterday. You're going to be able to catch that on YouTube once that goes up live. And then also Dr. Rahul Sachdeva is going to be here. He also did an SPF Talks with us. You could catch that now if you wanted to go out there and grab that and watch that real quickly. If you've got questions, that'll give you a chance to get ready for that chat box. He's going to be talking about neurostimulation again. So I think that's going to be something that we're going to be seeing in the future. So those are our 2 new additions this day.
And today, topics that are important as we look at the complete realm of possible treatment and possible therapy. So it'll be good to hear those, and we're glad and thankful that they're here and prepared to share with our SPF audience. One other thing about our agenda today, if you were with us at the end of the day yesterday, you know, again, we're here working with federal relationships, and yesterday afternoon as we closed out, we had staffers from both Congressman Billy Rackus from Florida and Senator James Comer from Kentucky come and share with us the commitment of their offices to help in rare disease research and funding in the future. And today we're going to end our session, and I want to make sure you stick around and watch these. We've got recorded messages from Senator Charles Grassley of Iowa and Senator Amy Klobuchar from Minnesota, and you'll be encouraged to see and hear what they have to say about rare disease research, and we appreciate their commitment and their work with this foundation as we move forward in the future. Norma, share with us real quickly. We talk a lot of times about e-blast and SPF talks. Take just a moment and hit those real quickly so folks are reminded about that.
Well, it's hard for me to hit anything real quickly, Greg.
I know, but you've got to do that this morning.
So I want to let you guys know and be reminded that the e-blast we send out because that's the quickest and the fastest way for us to get as much information to you as possible. Please don't throw us into the junk folder or drag us into that area. If you do, then you're going to have to come up with another email address in order to register with us so that we can have your information on site and be able to alert you to these changes. But yesterday you should have received in your inbox 2 very important pieces of information, and that is the survey that Greg covered. You're going to be able to catch all that presentation again on our YouTube channel, but that survey is available as a downloadable document off of our website under the Get Involved area. So please go out and grab that now, pull that down, share that link with your family and friends. And then also we showed you guys yesterday in an e-blast about the $8.4 million that was awarded from NIH to the operation of the Spastic Paraplegia CERN, Centers of Excellence Research Network. So as you guys know, we've been building this foundation, the framework that really led us to that $8.4 million grant. That is going to be a game changer in order to get people diagnosed and into the natural history studies, the biomarker studies, all of those things that puts that into a uniform frame so that we are able to then to take the clinicians into translational research, into regulatory research. And those words are going to become more and more important. So I want you guys to make sure that you pick those things up and let's have conversations about all the things that we're sending you in the e-blasts.
And quickly, as we talk about our conferences, our annual conferences, you guys know in the past our conferences generally have been 2 days as this one is, but in past years we have focused one day on hearing from our researchers, our clinicians about the things they're doing, the research that they're working on. And then the other day we normally spent talking about patient issues, how we live with these diseases, how we can share with one another tricks to get us through the day. We weren't able to do that this year because our total focus was on the federal partnership and relationships here. But as we begin thinking about conferences next year, we want to let you know that we'll be shifting back more toward the model that we've been used to. So we hope when we find a date and find a place and let you know about next year's conference that you'll be looking forward to coming. And we love the time with you, and we think you'll enjoy the old footprint.
Yeah, one of the things that we've heard here is like, wait a minute, where's the breakout sessions? Where's the kids' agenda? We need to hear about how we live with HSP and PLS. Well, as we have built this framework, it has been important for us to understand that you're visiting with your clinicians, you're talking with your doctors, but we've got to connect the dot to those researchers that understand what's happening in the mouse models, in the zebra fish models, in the oiganoid models. But we got to translate that with our clinicians. And then on top of those things, it's kind of like a triangle approach. We've got to work with our regulatory agencies, which is the point of bringing us to Washington. And with this having had this announcement, it was actually announced, the $8.4 million, I think on September the 30th. And we were able to get that here and build upon that. And then what's the next step? Where do we go from here? And that is recognizing that we have all this 20 years worth of research, not only just our organization, but other organizations that are across the world. And we want to find a way to fill the gap of what's missing. And what we recognize is that we're heading into that pharmaceutical, small molecule therapy development. And so today I want you to pay close attention to the conversations that are going to happen this afternoon, and that's with the pharmaceutical companies.
A lot of things going on, and when you hear Norma spit them out, it's hard to keep up with. Like you said, it's hard to say things quickly, but a lot going on. And you guys at home know, we do what we do because we have one of these diseases in our family, and it happens to be one that is hereditary. One of our children has it. We have 5 grandchildren who have a 50% chance of having it, so the odds are that one or more of them will deal with it. And that's what keeps our foot on the pedal, both physically and financially, and we appreciate many of you who are doing the same things. We're in this together. We're going to do all we can to cross a line that makes a difference in our lives and in the future lives of those people in our family.
Which is what we really kind of themed our conference this year. As you guys see some of the backdrops and some of the banners that you've got, the shirts that we've got on, which again, by the way, you guys can get all of this merchandise in the Redbubble store. We don't make any really profit on that. It's just a matter of creating that awareness. But that's what it really comes down to, is being able to understand is that we recognize that our families are fighting these diseases, and it's going to live on for generations in most families. So what we've got to do is, how do we get the win right now? And that's what we've talked about many times with many of the researchers while we've been here these last couple of days, and even continuing on today. We've got to have a therapy that we can use right now that stops the progression, and then helps those unborn children not have to have this in their makeup with whatever therapy that may be available. And as you guys know, science is constantly changing, and we want to be able to be on the foothold of that and progress that so that our kids and our grandbabies never have to live with these diseases.
So we appreciate your involvement. We appreciate your watching virtually and the partnership that we all share in trying to cross those lines and make a difference in all of our lives and in future lives. And with that, let me say this. We've got a couple of guys here who have become like family, who are great friends, who make this virtual possibility a reality. And we want to tell you, this may be a long shot. There may not be anyone listening who has any need, but if you know someone who ever needs these kind of virtual streaming services, these guys are Jeff Woodford and Rick Davis, and their company is www.littlerockhd.com. They'd love to hear from you, and when they hear from you, tell them that SPF sent you. But
we'll add that to our website as sponsors because of the things that they've done for us and the time and energy that they've put into this. It's been just a great sponsorship and a great appreciation that we have for them. So we're going to get that uploaded onto our website, and you guys are going to be able to use them. They'll travel everywhere. As you guys know, they've been with us now several years, and they've provided great assets in providing the virtual. And we're going to get better at even having virtual opportunities, and we'll see how that goes next year with some more ads on.
Well, guys, thank you again for joining us. We're going to pause here, and in just a few moments, we'll be shifting to the front where you'll hear some great speakers today, and we'll talk to you more through the day. See you later.
Thank you, guys.
Good morning, good morning, everybody. Hardest getting that first word out this morning. Hey, thank you for a wonderful day yesterday, a fantastic auction last evening. It was a lot of fun. I know you learned a lot yesterday. It was a big day. We have a big day today. You're going to learn a lot more. You guys are going to be so informed when we're done at the end of the day, and you're going to be excited and happy with the future of the Spastic Paraplegia Foundation and the research and the science and the progress that's being made on your behalf. So we're really looking forward to really, really super great informative presentations. You can't tell it. I'm super excited, but I have to stay real muted up here so I don't explode. Guys, it's been really fun. It's been fun being together with everybody and meeting and greeting and seeing new people. And just, this is what it's all about, having you guys here today so you can learn and be a part of the process that brings us all together on your behalf. That being said, on a quick note, we're still selling 50-50 tickets. Out front, we'll be doing that for a little while longer because we'll have the drawing today after lunch, okay? So if you haven't gotten them, there's still plenty of time. Okay, we're going to get this show going. We're going to kick off this morning with Dr. John Audhya from the University of Wisconsin. And by the way, you have helped fund his research. So this is pretty good stuff. Dr. John, he's on his way up to the front here. And we're going to get us going. We're going to kick off this day. And just hang in there, guys. It's going to be a good one. Here he comes. Rock star entrance. Here he comes.
All right.
If you have questions, I'll have people. Okay.
Super.
Fantastic. There you go.
All right, we're all up and running. Well, it's, that's pretty loud. I can go forward? Okay, I don't want to hurt anyone. It's really great to be here. This is always a really fun meeting to attend. Been fabulous to meet a lot of you for the first time, to see some old friends as well. It's really a highlight to be here and tell you a little bit about the work that we've been doing. I'm starting with this image here, very similar, I think, to what Craig showed yesterday. We're very interested in this organelle called the endoplasmic reticulum. It's actually a really beautiful structure. It makes these wonderful networks in cells and supports cell health in many, many different ways. And we're in particular interested in proteins that are shown here in green that assemble on very specific parts of the endoplasmic reticulum and help to manage the movement of proteins that are synthesized in that organelle that need to get out to the cell surface, other organelles within the cell. And what we know from Craig's work and the work of a lot of folks, that many of the 90-plus genes that are impacted in spastic paraplegia impact these processes by which we're trying to move proteins from one place in a neuron to another place in that neuron. And so we're really biochemists, cell biologists, trying to ultimately translate what our understanding of mechanisms by which these mutations in various HSP genes then lead to neuronal deficits. So this is actually an older picture of my group, and the reason why I show it is because a lot of the people here started the work that I'm going to tell you about, and some of them have stayed on because they're so dedicated to the project. So a few that I'll point out, so Zihang here in the, I think that's the right, he has HSP. He joined my lab in 2019, really to try to have a passionate dedication to understanding his own disease. And he worked incredibly hard. I'll show you some of the work that he contributed to, and now he's off and doing a fantastic postdoc and continuing on his scientific journey. So that's Zihang out in the greenery of Madison, Wisconsin. Dr. Molly Lettman has been with me for a number of years. She's really the go-to person in my lab in terms of all of our animal physiology work. So we use a number of different model systems to study the genes that are impacted in spastic paraplegia. Molly is a fan of the rat model. So unlike many other labs around the country and around the world that use mice as a model system, we actually chose to use the rat. And the reason why we chose to use the rat is we actually feel that they're much more similar. Not going to say that you guys are rats, not at all. But there are a lot more similarities in the central nervous system between the rat and humans as compared to that between a mouse and a human being. We also use human stem cells in my lab, and so Irina Pustova, let me see if I can. There she is actually this is when she was at Berkeley doing her undergraduate work. She was able to come out to my group, has built our stem cell program, and she's done an amazing job. She's been able to use CRISPR technology to take normal human embryonic stem cells and add back the particular mutations that underlie various forms of hereditary spastic paraplegia. So we can look at very, very well-controlled situations where we're looking at only that one point mutation. Sometimes it's just a single nucleotide change amongst 3 billion nucleotides in the human genome that results in that disease phenotype. And then we can model that using both dissociated or differentiated neurons that we can create in a dish. And she's now transitioning to build these into organoid models. So these are 3D structures that actually can better mimic the central nervous system architecture. And Jen Piotr here has also gone on and started a postdoc as well, and she's done a lot of the work using dissociated neurons, so we can take our rats and we can actually take neurons from those rats and be able to study them in culture. So I'm going to tell you about a story today that we started on a number of years ago, focused on a mutation in a gene called SPG57. I would bet if I asked folks in the crowd to raise their hand if you have this particular variant or any of these particular variants, we probably wouldn't get anyone's hands up in the air. There are about 5 families around the world that have a mutation, that the particular mutation we've been studying in this protein called SPG57, and in particular, a mutation in what's called the coiled coil domain, right here, that changes this arginine into a cysteine. It's the same exact mutation in 5 different families that are completely scattered, some in Brazil, some in India, Saudi Arabia. It's a recessive mutation, and so you don't see phenotypes in patients that have a single point mutation in one allele. It has to be a biallelic mutation. What we've learned about this gene is that it's actually heavily mutated in a variety of diseases. So all of those mutations that have been identified in patients on the left side of the protein, shown over here, all of these mutations result in different forms of spastic paraplegia, some more complicated, some more pure. Mutations that are in this very flexible region of the protein, some result in HSPs, others result in ALS, some result in Charcot-Marie-Tooth syndrome. This is a peripheral neuropathy. some result in Parkinson's disease. What this already starts to tell us is that all of these different diseases, clinically very different from one another, actually could have some underlying foundational principles that are shared. This same gene is impacted in each of these different kinds of diseases. And that tells us, well, there's probably a relationship there. And so I've grown my research program, honestly, to cover a lot of these different diseases. And we have other projects that are focused on ALS and Parkinson's in particular. I'm not going to be telling you about those today. We're going to stick with that particular mutation, this R106C mutation that underlies spastic paraplegia. So as I mentioned, we're biochemists. We started this story, we identified this gene in a worm. So we did a genetic screen in C. elegans. This is a very small microscopic worm, and identified this gene as being important for the movement of proteins from the endoplasmic reticulum to other parts of the cell. And after we published our first paper, a geneticist in Germany called me and said, you know, I have a family that has this R106C mutation. Would you be interested in collaborating? And that's honestly what I really love about the HSP community. It's been so incredibly collaborative. And it's organizations like the SPF that have helped to bring us all together. So I think that's just one of the fantastic ways SPF helps support progress in the research community. So as a biochemist, the first thing we wanted to do is understand what happens to the protein when this point mutation occurs, or any of these mutations occur. And so what we did is we actually solved the structure of of what's called this PB1 domain over here. This is the amino terminus of this protein, and that this structure has helped actually us understand exactly how various point mutations, all that cause HSP in this gene, result in disease. That was not done just purely by solving this structure, but also using a technique called cryo-electron microscopy. So we can take individual molecules of TFG that we purify, and we can look at them under a microscope. These are incredibly small structures, but these little domains co-assemble into these ring structures that you see here. And that ring structure assembly is actually really important for the function of this protein. So by drilling down to the molecular mechanism by which these mutations are impacting the protein, we're hoping to understand how we could best treat that disease. So we've gone on to solve this structure of the TFG ring down to about 8 angstrom resolution. Some parts of the structure are even higher resolution, but this really shows us the molecular interfaces between each of the protomers, each of the individual proteins in this entire ring structure. And what we were struck by is that every single one of the mutations in the amino terminus of this TFG protein fell at the same molecular interface within the ring structure. So the disease in the population solved the structure before we were able to do it using electron microscopy and X-ray crystallography. All of these mutations ultimately that result in disease in patients disrupt that interface between these proteins that make this ring. And that is what we believe molecularly causes ultimately that disease. Now the question is, how do we translate this? How can we develop models that we can use for either drug development or drug discovery to try to combat this disease? And so what we did is, as I mentioned, we developed a rat model. And so this is a wild type animal that's just walking across. This is a rat at about 25 weeks of age. You see little lines that we've drawn that mark various regions of the animals. The reason why we do this is that we can track every single joint in this animal as it traverses a walkway. And we can train, using machine learning, a computer to be able to measure the gait of this animal. So we can get really, really fine measurements of the gait as this disease is progressing. And this is a progressive disease in this rat model. So this is the same exact imaging sequence. Now, this time, we have a single point mutation, that R106C point mutation in SPG57. As I said, it was recessive, so both of the alleles in this particular rat have that mutation. And what we can see is that this animal's gait is dramatically affected. And so this is actually towards the more end phase of the disease progression, so it's a very striking phenotype. But we believe, this is really the exact mutation that's found in a patient that we've now been able to recapitulate in a rat model. And to our understanding, this is really one of the first times we've been able to take the exact mutation found in a series of families, put it into a rodent model, and be able to recapitulate a striking gait phenotype like this. So this provides us the platform for discovery. And that's really the huge point that I want to make. And we're trying now to make a large number of these similar types of models to be able to develop therapeutics, to be able to treat first these animals, but then ultimately translate that to clinical trials. And the goal is by picking different mutations, all that underlie HSP, we can look at various mechanisms by which neurons, in this case, are degenerating. So the hope is that if we pick a gene like SPG57 that's involved in ER trafficking, Craig pointed this out yesterday, there are different parts of the neuron that are impacted by different mutations. Some affect mitochondria, some affect the Golgi apparatus, some affect microtubules. So in all these cases, though, we think that there's a common underlying deficit that's leading to that neuron to degenerate. So if we create a number of different rodent models and then test different therapeutics in all of those platforms, we're hoping we can find something that'll help not necessarily cure the disease, but help to limit the symptomology of that disease so we can improve somebody's quality of life. And so the way that we went after this particular case, let's just move forward, we can now do a lot of analysis on these animals. So as I said, we can use machine learning to be able to understand exactly how the animal's gait is impacted. The things that we look often at are the way the hind body of the animal sways between, and I'll just go back really quick here. And you can see the wild type animal walks basically in a straight line, and the animal that has the point mutation in SPG57 is swaying back and forth. We also look at the tail. So if you look at the wild type animal, the tail is held up high, and that's a motor control function in the hind part of the body, equivalent to the legs of a human being. And you can see on the right-hand side with that mutation, the animal drags their tail. So we can measure that as well. We can also look at their step cycle. As each time they take a step, we can measure that. And then quantitatively, we can see exactly what happens over time. So when these animals are born and are aged out to about 6 weeks of age, they're basically fine. There's no strong phenotype. But by 13 weeks, by 25 weeks, we're starting to see more and more deficits. If we look at the hind body sway, nothing really different in our mutated animals relative to our controls. That gets worse at 13 weeks and much worse at 25 weeks. So that quantitative ability allows us then to develop time points at which we can deliver a therapeutic and see whether or not we limit the progression of that disease, or if we can improve the function of that animal. So we've done a similar study to this just by using exercise as a treatment approach. And what I can tell you, it works. So as Craig pointed out yesterday, exercise is one of the main ways that we encourage patients with HSP to try to maintain as much of their function. It works. In our animals, it staves off disease by months. So that is an efficacious approach. We now want to develop therapies that can enable us to do even better. So that rat model, as I said, has a lot of hallmark symptomology as what we see in patients with spastic paraplegia. So this is a brain section that we've taken of the rat. In a wild type, they have what's called the corpus callosum that joins the hemispheres of the brain. This is relatively robust. And as you can see in the animal that has the mutation that causes HSP, we see a thinning of the corpus callosum. And we often can see that in MR imaging in patients. So this is very similar, and we can actually quantify that. It's progressive, so even at 13 weeks, we don't see much impact to the corpus callosum, but it gets worse with time. So what that's telling us is the earlier we could potentially intervene in disease, the more likely it is that we can preserve function for a longer period of time. We've gone to the electron microscope as well to look at myelination. So this is a demyelinating form of HSP. On the right-hand side, we see these thick myelin sheaths that encircle the axons that innervate your spinal cord. But in the point mutation, this is at 25 weeks of age, we see a dramatic thinning of that myelination that reduces nerve conduction speed, and that ultimately, we believe, contributes to the gait phenotype we see in the animals. So in many ways, I'm not going to continue showing you all the symptomology phenotypes of the rat. We feel it's a really, really good model system to be able to do drug development and therapeutic development. So one way that we've tried to go about this is using a gene therapy approach. I think many of you have heard about gene therapy. What we're trying to do in this case, it's a recessive mutation. So if we can redeliver just enough of the normal wild-type protein, we're hoping that we can regain the function that these animals have lost. And so I'm going to show you a bit of a sad image first. This is an animal where we've actually driven the progression of the disease much faster. And the way we did that is we reduced the amount of the protein that these animals produce, in addition to having that singular mutation that underlies HSP in these patients. So this animal is at 9 weeks of age, really is having a tremendous inability to walk across the platform at this point. We actually don't really do much of the gait analysis with these animals because their joints really aren't functioning as we would expect of a normal control animal. So that's as early as 9 weeks of age that this animal is showing these symptoms. At 3 weeks, these animals are actually perfectly fine. We start to see symptomology at 6 weeks, so earlier than the other model I just showed you that has 2 versions of that point mutated protein. In this case, we only have 1 version of that gene expressed in these animals. Now, what we do is we can take a virus and inject it into the brain of these animals when they're first born. So as neonates, we collect those animals and we inject a virus that expresses under a neuron-specific promoter, so we are only expressing the protein in neurons, and that's encoding a normal version of the SPG57 protein. And what we see is absolutely phenomenal. These animals are completely rescued. Their tails are held up high. Their gait is straight. These animals at 9 weeks show a resilient phenotype. At 18 weeks, continue to show a resilient phenotype. At 25 weeks, that's a half of a year, continue to show a robust ability to walk. So it's a persistent, these viruses we're delivering will continue to be expressed in neurons. Neurons aren't dividing a whole lot in your brain. What you're born with, what you grow up early with, that's what you're going to have for the rest of your life. And so we're expressing the normal protein in the majority of these neurons, and we've regained the function. So we're really excited about this result, and we again believe this is a great strategy that's very gene specific. So it's only tailored to a single or a small set of patients that would have this particular set of mutations in this SPG57 protein. So, but as I said, if we pool together all of the families we've worked with that have that point mutation, whether it's the R106C mutation, whether it's another point mutation that causes HSP, we only have about 20 or 25 families worldwide that we could impact. What we also showed from this, and I pointed out, we're re-expressing the wild-type protein only in neurons. And so what you can hopefully see here is their hind body sway is regained back to basically normal. If we then express, instead of just in neurons, into other types of cells in the brain, so in this case, we're re-expressing the protein in oligodendrocytes. These are the cells that drive the myelation of neurons, of axons. We don't see any rescue. If we drive the expression in astrocytes, these are glial cells that support neuronal health, we don't see any rescue. So what it's telling us is the loss of function for SPG57 is mainly felt in the neuron itself. It's not an impact on these supporting cells that are feeding neurons for your entire life course to keep them active. It's really a deficit within neuronal function. So that's informing us of how we could develop those gene therapy approaches, those gene therapy strategies. So as I said, limited population are infected by SPG57. We decided, given that success, we tried to broaden our approach, create additional rodent models. And so the one we chose was SPG4. So SPG4, called spastin, is a microtubule severing enzyme, and that's a key distinction. SPG57 is not an enzyme. We don't have to worry about putting too much of that protein or too little of that protein back in neurons. SPG4 is an enzyme and has an enzymatic activity that is necessary for cellular function, but too much of that enzymatic activity could be bad. So to develop this animal model, and this is an interesting protein, I think you're going to hear a couple of more stories about SPG4 today. There are two versions of this protein that are made in mammalian systems. The first is what's called M1. It's the longer isoform, and this particular protein is embedded in the endoplasmic reticulum. There's also an alternative start site. So instead of encoding this N-terminal region of SPG4, it starts later. And this form is a soluble form that we call M87. And so what we did is we used CRISPR technology to go in and create a singular point mutation at the M87 codon, so one nucleotide shift. And now none of the M87 protein is made, as we see here. And that M1 isoform we have yet to really detect in rats. We've actually just recently generated a new antibody that specifically recognizes that M1 isoform that we made in rabbits. And still, even with that reagent, we're not able to detect that M1 isoform in the brain tissue or in the spinal cord. That all being said, that mutation, we can get rid of SPG4 altogether. And this has been done in mice previously. So not a novel approach, but the phenotype is actually very, very different. So when we've studied the mouse model for SPG4, when we get rid of that protein, they actually have relatively subtle impacts that occur pretty late in their life course. So about a year of age, which is about a third of their or half of their lifespan, we see some phenotypes. However, in this case with the rat, this is at 6 weeks of age. Again, this is our normal animal walking across, shows good mobility, good gait function. However, in contrast, when we look at our SPG4 6-week-old animal, we can already see that this animal is having a real difficult time making its way across the platform. So I think this is really suggestive that this rat model, as opposed to mouse models, may be a better platform in many cases for being able to do therapeutic development, because we can now see a very early onset phenotype. So these animals, when they're born at 3 weeks of age, they walk fine. At 6 weeks of age, so it's a rapid onset, and then it progresses not very much further than what we're seeing here. These animals at 12 weeks, 16 weeks, basically show a very similar gait phenotype. So we decided, well, we had such a great success with SPG57, let's try a gene therapy approach. We worked together with a number of other laboratories in developing this approach to create the adeno-associated viruses to redeliver into the brains of these SPG4 mutant animals. And so far what we've found is that now we're not able to get rescue. What I'm showing you here is sort of the different, we can either express the full-length M1 version, the smaller soluble M87 version, and as we deliver as we deliver these genes at different concentrations of virus, which correlates with the amount of expression of these genes in the neurons of the animals, what we see if we just look at the M1 isoform, no matter how high we get in this course, so this is a very high level of virus delivery to the brains of these animals. We're not seeing any lethality, but we're not seeing any response in terms of regaining motor control in those animals. On the flip side, if we express more and more of this M87 form, the soluble form of spastin, this M87 form ultimately causes toxicity. So if we put too much of this enzyme into the neurons of these animals, it kills those neurons. It destroys those cells from being able to work properly. So we're working at this really modest interval where we need enough expression to regain activity, but too much is going to be bad for that cell. And so we've also gone ahead and looked at overexpression of catalytically inactive. So spastin, as I said, is a microtubule severing enzyme. This mutation, which is observed in patients, R499H, really reduces the activity of this, what's called the AAA ATPase domain that drives microtubule severing. Even if we overexpress large amounts of that mutant isoform of spastin, we don't actually see any toxicity or lethality, which suggests to us that that isoform doesn't have what's called a dominant negative effect. If we're putting too much of that protein into the neuron, it's not causing that neuron to suffer greatly. So that's a really important distinction in terms of therapeutic strategy, because we want to redeliver the gene, but we don't want to cause a dominant negative effect. This helps to tell us that that M87 or M1 isoform has that point mutation. It's not causing that dominant negative effect. And so what we really need to be doing, in our opinion, is redelivering wild type, but just the right level of the normal gene to be able to regain the function of that enzyme. So we have a lot of work to do, obviously. That gene therapy strategy we had hoped was going to be a home run like it was with the SPG57 model. Life isn't fair. I think we all know that. So what are we trying to do? We're trying a lot of different things right now. So one of the things that we're working on is using different promoters, so different ways of expressing the SPG4 gene, such that we can get the right level of protein expressed in those neurons. The question is, are we going to be able to target the right population of neurons? So a colleague of mine just did a really interesting experiment. When we think about our brains, we think about them as about 50% neurons, 50% glial cells. Glial cells are supporting neurons, neurons are doing the work. Of those population of neurons, I was shocked to learn that based off of what genes individual cells express, there are literally hundreds of types of neurons that are in the brain of people, of animals. So what function of SPG4 is being lost in patients that have disease? Is it in all neurons? Maybe not. Instead, it could be just a small selection of neurons that really need that level of SPG4 activity in order to thrive. Identifying which population of neurons to target has been a huge challenge. So we did an experiment. We took the brain, the motor cortices, so that's the part of the brain that enables movement in the legs. We purified that region of the brain and then did a procedure called RNA sequencing. So we sequenced every single RNA that was expressed in those neurons. And we would expect, given the phenotype we see in these animals, striking differences in the expression of different genes that are as a result of that loss of function of SPG4. And we were shocked that at a bulk level overall, we really saw no major differences in gene expression in the SPG4 animals. So what it's suggesting to us, what we're missing in that bulk RNA sequencing approach, is what's happening at the single neuron level. So if we're able to then identify the specific neurons, whether it's a specific subset of pyramidal neurons that we heard about yesterday, whether it's a different type of neuron that's important for motor function, that's the goal that I think we really need to pursue. And that's work that's ongoing now. It's not easy work. Single cell sequencing, so it's literally taking one neuron out of billions, sequencing expression or protein levels in that single neuron, and then seeing which neurons are being affected, particularly by the SPG4 mutation. So an alternative approach that we've thought about is let's get wider expression of SPG4, but lower its activity. So it doesn't have that toxic effect in all of the neurons that we're targeting, but we can get levels high enough of the virus to infect a wider population of neurons in the brain. So if we're able to target all of the neurons with a high level of virus, but with a version of SPG4 that has lower activity, hopefully we'll be able to reduce activity or toxicity, but at the same time be able to identify a rescue in those neurons that specifically need more SPG4. So based on the structure, and that's why I think it's important to bring the cell biologist, the biochemist, the neuroscientist, the clinical trialist, all have to come together to work towards solving this problem. So the structural biology tells us that this point mutation, specific glutamic acid, within that enzymatic activity domain, that microtubule severing domain, if we mutate that, it'll lower the activity by about 70%. So expressing that at a higher level throughout the brain, hopefully we'll target all of the right neurons to be able to get SPG4 expressed in those neurons that really need it, but not have a toxic effect in the neurons that don't need this higher level of expression of SPG4. So this protein, if we make it in biochemically purify it and measure its activity to sever microtubules, that has a lower activity to sever microtubules. Still can do it, so it's just a lower level of activity. So that's another strategy. Actually, it's in a grant we now have at SPG, at SPF right now, to try to develop that approach. The last one that we're just starting to work on is a CRISPR-based strategy, because one of the questions that we're struggling with is our model as good as we think it is? So if, for instance, the deficit that we've created happens in utero, so by the time we're giving them normal gene back, it's too late, that they've already had a neurodevelopmental consequence, that we're not able to then see any rescue. We don't know that. We don't know that's not the case. So what we're doing is creating a CRISPR-based strategy to fix the mutation that we created using CRISPR a couple of years ago. So by showing that we can correct that day one after they're born, and affect enough of the neurons, will we be able to see rescue of the animal model? That will demonstrate to us that the platform, that this rodent model for SPG4 is a valid one to pursue for doing drug development, for doing gene therapy approaches, which we don't know at this point. So I think this is a really important experiment for us to conduct. It'll also help us further develop the technology to go in and specifically edit a gene to see if we can get function back. The challenge is, and maybe many of you have heard of the baby KJ story. So baby KJ is a baby born in Pennsylvania, was born, was completely fine, and then slowly but surely started to suffer from a disease of her liver. And there was a particular enzymatic activity that she was missing. And so they went in and did a CRISPR approach to fix the gene that was mutated. The difference between a liver and a brain is that the liver is dividing. Those cells that they corrected through that first therapeutic approach, they multiplied. They continued to populate the liver as it continued to grow. They had to do a second course of treatment. Now baby KJ is actually doing really well. Difference in the brain is that those neurons aren't ongoing, you're not getting ongoing division. They're post-mitotic cells. So we would have to deliver enough of this CRISPR agent to be able to correct the mutation in enough neurons to regain function. That's a really, really hard problem. The field is not there yet to use the CRISPR technology in that way. Will it happen someday in the future? I'm 100% confident that there's going to be enough work that's going to go into this that's going to solve that problem, that we're going to figure out how to use CRISPR in a way that is safe, but also effective. So with that, I just want to thank the people that really help us do the work that we've been doing. My lab's recognized here. We've been working wonderfully well with groups at Drexel. You're going to hear from Peter Baas later, I think, in this morning. We work with folks at UMass. We work with folks like Darius, I think, who's had to take off. It's been a wonderful experience bringing all of these groups together. The way this has happened is actually through the Lillian Blair Foundation in particular, has helped to bring this group of scientists together. I actually got to know Craig much better through the Tom Ballig Stiftung in Germany, where I got to see Craig. I think you wore some sort of funny hat at a bar, and it was, I knew you were a real person, not this like neurology god that we read about all the time. He's a real person, and he drinks. NIH obviously is a strong supporter. Our grant through the Neurological Disorders and Stroke is focused on the the SPG57 project. We're working to try to get grant funding to support our SPG4 work, but we haven't been successful yet. It's really these foundations that have helped keep us on track to keep seeding our work that will, I think, enable us eventually to be successful in getting additional grant funding to be able to pursue this work further.
Do you have time for
I have time for as many questions as you'd like.
It's just going to be a couple.
That's
Here we
fine.
go. Here's our first one.
I'm wondering what the next steps are. These are very positive things you're doing. What are the next steps that you feel are the most positive ways you can get to some real results?
So a couple of ways. So first, we do believe that the SPG57 model that we've created is a wonderful platform for doing small molecule discovery. We've actually worked with 3 different pharmaceutical companies now to test various compounds to see if there's gain of function. One that targets neuromuscular junction function, another that targets what's called the integrated stress response. We're trying to keep the neurons alive and functioning normally for a longer period of time. So using that platform, we've been able to test those. We've been actually able to test a number of the small molecules that are currently in clinical trials, phase 1 trials now for ALS. We've been trying those in the context of our rodent model. So far, the compounds we've tried have not shown dramatic changes. But I think the platform's important as there's new discoveries, new small molecules that are being developed. We're very excited to work with pharma, to work with anyone who would want to share with us those reagents, and we can test them pretty rapidly within a 3-month span within our rodent model. Same goes true for the SPG4 model. I think that's where our work can be most impactful, and then handing off our successes to folks like Darius and others who are really involved in setting up the clinical trials to move this into patients.
could our population be contributing SPG4 tissue or something like that to your research?
So we actually have a large number of fibroblasts from patients that we've converted into human stem cells that we've been studying. We have a specifically edited form where there's no genetic background concerns. I think we're good. What we really need is the advocacy. You're all coming here to DC. I wish it was a different story in terms of the NIH being open for business. I come here actually every 2 months. I serve as our research dean at my medical school that I work at. I come here every 2 months and I lobby on behalf of rare disease, on behalf of NIH funding. What we've seen is a very positive outcome. NIH funding and appropriations bills from both the Senate and the House have held steady the level of NIH funding. That's really important. And I think the advocacy, all of the people coming together, showing that we care, that we want our federal government, as being constituents, we want them to fund this work. That's really important.
First of all, I want to say thank you for all your hard work. As you develop gene therapies in the lab, what are the biggest challenges that you face in getting these therapies from cells or animal models into human models?
Sorry, I missed the last. Sorry.
What is your biggest challenge?
Biggest challenge?
Yes.
Yes. So the types of viruses have to be safe to put into a person. So there's only a small selection of AAVs that we can actually express in individuals. The worry is these could cause off-target effects, could result in things like cancer, which obviously we don't want to do. So translating the AAV technology is something we really are relying on our collaborative partners, particularly at the University of Massachusetts, to help us through that story. Delivery, we've solved some of those problems. One of the things we're doing with the SPG57 model now is, can we deliver the therapy late after the disease onset occurs to basically see, can we stop the disease in its tracks if we're able to deliver later in life? So we've figured out a way to create basically stents that we can deliver the virus into the cerebral spinal fluid of these animals, even as they're 6 weeks, 12 weeks, 20 weeks of age. So we can start to see if the gene therapy strategy after disease onset, after symptomology, is happening. The other piece that we're doing is using the animal models to look for biomarkers. So can we screen patients much earlier for mutations that are known to lead to HSP? And those biomarkers, I think, are really critical. From the CSF, from our animal models, we can measure proteins that are elevated and then see whether or not those are also elevated in patient samples. So we're working to get patient samples for CSF, ultimately from blood. Can we develop a diagnostic test for earlier diagnosis? The earlier we can intervene, with exercise, with diet, at this stage, those are a lot of the approaches that are available to us. But as we develop new therapeutics, we need to get them into the individual before you're at a later stage of disease.
Great, Doctor. I've got one more. Sorry, I've got to get this one, and then we're going to move on to our next speaker.
Hi. As far as I'm aware, SPG4 mutations are autosomal dominant, yet you are using a null model. So in a null model, presumably, you have to express only protein back to the wild type level. In SPG4, the mutation in patients, that is not going to work, is it?
So it's a great question. So I'm going to go fast, I promise. So you're exactly right, dominant acting, but is it really dominant acting or is it haploinsufficient? So are you losing so much of the protein in a very specific subset of neurons that all we really need to do is redeliver it into those neurons? Or, as you're saying, could it be something that's dominantly acting, a gain of function? I don't think that question has been answered. I think our results showing if we overexpress massive amounts of what's thought to be a dominant acting mutation, we don't see any disease phenotypes. So it's suggesting to us it's really a haploinsufficiency. So too little of the protein is available to carry out its work. So if we are able to then, in that context, redeliver even just a little bit more and get it over the threshold to maintain spastin activity in those neurons that are really needing it, that's our hope, is that we can help to address the disease.
But shouldn't you use a model system then that actually reflects the patient rather than get rid of the protein and try to re-express it?
We would absolutely love to. It doesn't exist. So if we make a heterozygous animal, if we look at MR imaging, we can actually see differences in tractography of neurons. However, those animals don't show the striking phenotypes, and we need the phenotype in order to do any sort of screening. Doing brain MR on individual animals after a rescue approach would be really, really, really expensive and very, very, very challenging. So we really need the phenotype, the gait phenotype, to be able to do the work. Is it better to maybe use a cow model or other models that show? Absolutely. The drawback is, well, those animals take a long time to reproduce. I'm going to stop. People are getting mad at me. I really apologize.
Did a great job, Dr. John Audhya. Audhya. Okay, everybody. Coming up next is Dr. John Fink. We're going to take a second here to make sure we get all of his slides ready to go. Great. Here we are starting off. What a great presentation, right? How much did you all learn? A lot? My goodness. My goodness. And this is just a piece of the bigger puzzle of everything that's going on. So I promised you guys would learn a lot today. And by the way, there'll be a quiz afterwards. Okay, so I hope you're taking real good notes because we're going to pull from some of these presentations. So anyway, once we get set here, remember, 50-50 tickets. We're pulling for that today. And also one of the tickets will be for the $200 gift card for the Cadence shoes, which are really, really cool. So that's a nice thing. So we got 2 drawings today at lunch. Outside of that, I'm filling. Anyway, it's been really good and a lot of fun to be here. Has everybody met my wife, Tina, by the way? Of course, everybody. She's all over the place and meeting and greeting and making sure everybody's having a good time. And we want to thank the staff out front that has been doing a great job, Mary Kay and Linda, who are just keeping everybody running real smooth. Once again, we want to thank our sponsors that have helped us put everything together and helped to make this easy and convenient for you guys to come here and be with us. Yes, yeah, hey, God, I'm getting better. Wow, look at that, it's a miracle. Hey, by the way, in those little packages that were in your welcome bag was a little gift bag from Mary Kay that had a bunch of little bitty travel little items in there. And one of them was in there was like this Vita C stuff. Well, I already took mine that was in the package and I took my wife's. So if I find any loose ones out there, I'm going to be mixing my own cocktails with that later today. It's apparently it's working pretty good. So we're getting our slides ready. Dr. Fink is ready. Here we go. Ladies and gentlemen, Dr. Fink is one of the most recognized names in HSP and PLS research. For over 2 decades, his groundbreaking work at the University of Michigan has helped define the genetic and clinical landscape of these diseases. He is also a founding force in the global HSP and PLS community, inspiring countless researchers and families worldwide. Dr. Fink.
Thank you, Tim.
Thank you, sir.
Good morning, and it's my pleasure and my honor to be here. And I have to say, I've said this before, I learn coming here. And so this is really an education for me. And we're going to talk today about something that's, it's not rocket science, but it's a necessary part of developing treatments. And we're going to talk about progress towards in-home testing for PLS and HSP. And we're going to talk about ideas that kind of guide this strategy. we'll talk a little bit about our progress. We've studied more than 100 subjects, and we hope to get to 200 by June. And we'll use the word imagination. That's also driving this, and we'll use that word imagination in a very specific context later on. So, we talk about testing. The word testing, if we say, this is not a test, or we say, there will be a test. No, the word testing can have scary or anxiety. We don't mean it in that way. We're talking about, the non-scary, this is only a test. Or testing, pay attention. So, but when we talk about the purpose of testing, what do we mean? Well, we want to understand the disorder. So, for example, if you have your reflexes tested, or if you have your sensation tested, or if you have your walking tested, or your balance, or your cognition, or your vision, or any kind of testing, that kind of testing is to help define the disorder. What is the disorder? How many disorders are there? How many varieties of a given, for example, SPG4, very common. Many varieties of SPG4. And so within each type, there's a lot of variation. So testing can help us understand the differences between disorders, the differences within disorders. Now, we also want to use testing to develop clinical outcome parameters, things that we can use to say this treatment is working, this treatment is not working. What kind of treatments? Well, physical therapy, muscle relaxing medications, pain relieving medications, and, God willing, soon, really effective treatments to change the underlying process of the condition, or the processes of the condition. Whether those are small molecule therapies, biochemical treatments, or gene therapies, or CRISPR modifications, or electrophysiologic stimulations, vagal nerve stimulations, other kinds of treatments. Yes to all of the above in different circumstances. Now, our objectives for this research is to develop large groups of well-characterized subjects. We want large groups of people, for example, with PLS. Now, that's a very difficult goal to achieve. There aren't large groups of PLS subjects. There are if you collectively look at all the databases in the United States, there's less than 1,000 people with PLS registered. SPF database has many thousands of people with PLS, but for example, the University of Michigan, Northwestern University, Columbia University, NIH collectively have probably about 1,000 subjects that have been studied with primary lateral sclerosis. So these people exist, obviously. The SPF database is much larger than those other databases, but we have to get those people for specific testing. Now, HSP, much easier to ascertain. Not all subjects, not all types are easily ascertained. And the other part is that in general, most of the testing is done on the subjects who are affected, and much less testing is done on their family members. Why are family members important? We need really good case controls. We need people living in the same environment, with the same nutrition, with the same general exercise pattern and so forth, with the same background genetics. By background genetics, we mean that people share similar genes, but differ in a genetic mutation, but the other genes are shared in common. And we want to study the features of the people who live in the same environment, have the same nutrition, and so forth and so on, and share similar background genetics, and compare them with their family members who differ, for example, in one specific gene. So we need large cohorts of subjects, both with PLS, with HSP, and their family members. And the family members are various ages. So if we're studying a 5-year-old with HSP, we need children, control subjects, and so forth and so on. And many of these, not just ascertain people on a one-time basis, we need longitudinal longitudinal evaluation. All right. Now, one of the purposes of one of the other goals of our approach is to have an unbiased participation. There are many biases of participation. For example, socioeconomic factors. Who has access to large medical centers? Who has the medical insurance to go to a particular center where they're doing testing? Whose insurance provides network access? Okay, so there are economic factors, so forth. There's also geographic factors. But importantly, besides those obvious factors, there's disability factors. Okay, people become disabled and then can't participate in testing. So, and people at a very mild level might not even go for testing at the beginning. So we might not have ascertainment of people with the most mild forms. We might not have evaluation of people with the more disabling forms. So we want to ascertain and evaluate all subjects. We don't want features of the disorder to be a bias to entry into studies to study the disorder. But there's other factors I could go on about. With the socioeconomic, people who have child caring responsibilities or work, or for whom the disability requires that family members transport them, but the family members have their own work responsibilities. All of these things pose a limitation to participation in research and a kind of a biased ascertainment for who gets to be studied. And we have to be very cognizant of the biases, like if you take all these biases, then what we are looking at is a selected group of people who had a kind of disability with the kind of health insurance, who lived in a geographic region, who could get to a testing center, and then who could come back frequently for reevaluation. It's a very selected group of people. And we want to reduce the biases. We want to first be cognizant of our biases. And, the word bias has become a politically charged word. And to be aware of one's bias has become a political concept. We need to be aware of the biases that we bring to the research that help recruit people or help dissuade people from participating. Okay. Now, the other factors we want to look at are just the costs of testing and the efficiency of testing. Testing in clinic environments is expensive. It's time-consuming. We want to reduce the cost and improve the efficiency of testing. And we'll talk about other factors here. What kind of testing? This is a huge topic. And testing, it doesn't have to be scary. What kind of testing are we talking about? Well, there's functional testing. What's functional testing? The ability to do a certain task. The ability to walk from point A to point B, or to use walking to get from point A to point B. Now, the ability to get out of a chair, the ability to get into a car, the ability to get dressed. These are functional activities. Now, functional activities are different than specific motor tasks, like lifting 5 pounds. That's a specific motor strength assessment. Specific, for example, of the biceps, or of the deltoids, or the grip strength. So we have specific neurologic factor assessment, the reflexes, how long can you feel a vibration on your toes? Is it 15 seconds? Is it 2 seconds? These are neurologic factor assessments. So, for example, measuring vibration perception is not a functional assessment of your walking. It's a neurologic factor assessment. So testing can be neurologic factor assessment, reflexes, strength, sensation, balance, and so forth and so on. It can also be functional, ability to get out of a chair. Neurophysiologic testing, spinal cord conduction velocity. Mary Kay Floater here at NIH pioneered that, really, I think, in particularly PLS, spinal cord, but not just PLS, measurement of the spinal cord conduction velocity. And that's of huge value in measuring a neurologic or a neurophysiologic feature in people with PLS. So we have neurophysiologic features, EMG, and so forth and so on. We have neurologic features. We have functional testing. And of course, the other kinds of testing, biochemical testing, looking at molecular biomarkers, neurofilament light chain and spinal fluid or blood, neuroimaging, quality of life surveys, patient-reported outcomes. These are all a variety of different kinds of testing. So when we say we want to do testing, what kind of testing we're going to do, and then, of course, within each type of testing, there's different categories. But if we look at testing, and I put this up here basically to tell you where we are in our studies, and we are at the validity point. Validity, the concept of test validity is how well does a test outcome indicate a clinical feature. So, for example, how well does a 25-foot walking speed test, 25-foot walking speed, that's a standard test used in clinical assessments, or a combination of tests. Walking speed is one test. 25-foot walking speed is one test. A combination of tests together is, for example, the primary lateral sclerosis functional rating scale, or a combination of tests collectively is the spastic paraplegia rating scale. You take a bunch of tests together, a bunch of individual tests, combine them, and you have now a rating scale. But whether it's a single test or a combined test and a rating scale, how well does that rating scale actually measure what you're trying to measure? Which is, for example, how well does the spastic paraplegia rating scale measure disability in HSP? Or how well does the primary lateral sclerosis functional rating scale, the PLS FRS, actually measure disability in PLS? And so the ability of the test to actually measure the thing you're trying to measure, that's the validity. And those two tests that I mentioned have been validated, and they're very high degree of correlation between the test score and the overall functional disability. But we, and as we move towards in-home testing, we have to validate that the in-home testing is as valid as the same test done in clinic. And so I'm putting that up here. It's to let you know our progress and where we are now, because we're doing that testing. So that's why that is kind of a marker of our current status. Now, we have to think about confounding variables. And that is, are there some aspects of a disorder that interfere with the test performance? So, for example, let's say somebody's in pain. Well, maybe they're in pain and that limits their walking, but we're measuring their walking as a function of HSP or of PLS. But really, the performance on that test is limited by another confounding factor that we aren't really scoring. Or we may just note that the person's in pain, but it's hard to subtract out how much pain has influenced that performance. Anyway, so let's say that somebody doesn't understand the test. This is a huge factor as we talk about conditions that affect cognition. We know that for everybody, yes, and particularly for people with cognitive impairment, dual task walking, that is walking and window shopping or walking and talking on the phone or doing any other task, affects the gait pattern, the stride length, and so forth. So dual task walking affects motor performance for everybody, particularly in people with cognitive impairment. What about when there's cognitive impairment in HSP and we're measuring walking? we have to be aware that some of the gait problem reflects the cognitive impairment and the ongoing dual task nature of the test itself. When we say, walk in a figure 8 pattern, okay, now, if I say to somebody randomly in the audience, we want you to get up here and walk in a figure 8 pattern for 2 minutes. Okay, so right away you're going to think, okay, so what's figure 8? Does that mean a straight line? Is it actually continuously curving? So while you're walking, you're doing this to try to figure out if you're doing it correctly. This is a dual task. Okay, now that the effect of dual task walking has greater impact on people with cognitive impairment. It affects everyone's performance, every single person's performance, but it's greater in some individuals than others. We have to be aware of these. That's just one confounding variable, and there are many. So we talk about how relevant is a test. That's a big factor. The test has to be relevant. I mean, for the disorder, and it has to be something that we can test repeatedly and come up with the same results. It has to be accurate. Okay, we can talk about these test terms later. All right, so now we're talking about this testing location. In-home testing, or at school testing, or in the workplace testing, versus clinic testing. And each has their advantages and limitations. Okay, in-clinic assessments provide a standardized testing environment. It's usually the same from one institution, from one clinic to another, very similar. These are well-lit hallways and clinics, flat surfaces to walk on, and if you're walking in a distance down a hallway, then you have converging lines, and that is problematic for some people that find converging lines a source of anxiety, less problematic for other individuals, but that's less of a factor for 25-foot walking, more a factor for the 6 and 10-minute walking of these converging lines in the hallways, whether you're walking on a tiled surface or a hard carpet surface, but they're standardized. One clinic that does 100 subjects in their clinic is going to utilize the same environment, and the environment has an effect on the testing outcomes. Okay, if we're talking about clinic rooms, well, the clinic rooms have very similar size. When we get up from a chair, walk across the room, turn around, go back and sit down for what we call the up and go test, it's very similar from one clinic to another. These are and it's very standardized from one patient to another in the same environment. But the other aspects like staff interactions, the duration of the clinic visit, very similar. There's another factor that I'm sure everybody's aware of. That is that we call the performative aspect. A person comes to clinic, and whether it's the physician or a medical assistant or a research assistant says, okay, we're going to watch you walk. Go ahead and walk. Now the person feels like they're on camera, they're performing, they're being studied. Usually, or often, they do much better. They say, I never walk this. I mean, there's a variety of responses, but one of the responses is, I don't walk this well at home. This is good for me today. So, or, people want to perform better in those. That's one way. They may want to exaggerate or they may be nervous. So there are a variety of outcomes, but the fact that it's performative with an observer watching influences the outcome. And the only way we know that is by comparing sensor testing in the clinic, when a person leaves the clinic, continues to wear the sensors, and then we watch their same walking pattern in a person who's not being observed, we see differences. So we know, we have not a lot of, but we're gaining some preliminary data that says that there is a performative aspect, and the only way we can know what the non-performative aspect is to study people when they're not being observed. And there are differences. And so which do we want? We want in the free range home environment walking. Is that better? Well, we'll talk about that. Now, the in-clinic one value of in-clinic assessments is that a lot of things can be done at one stop. A person can come over for an MRI scan, blood drawing, gait testing, general neurologic care, genetic counseling, all at the same time. And is that a value? Yeah, it is a value. But I would have to say that as we'll talk about, so that is a value, that it's all like one stop. But it also, each of those other aspects of the interactions influences the other. Okay, so we talk about in-clinic assessment. It influences the participation. As we talked about before, access to clinic is not equal to for everybody. Distance is a factor, the timing of the appointment, other responsibilities. So it affects the participation. We talked about this. And it also can affect the outcomes of the tests. Also, the in-clinic assessment, there's a really important aspect, especially in colder climates, Michigan, but not exclusively. What happens if you sit in a car for 2 hours or more in the middle of winter, get out from the parking lot or valet parking, you're cold, the spasticity is aggravated, and then you come in for your gait testing? Not so good. And or sitting for an hour, or whatever, getting up early in the morning and missing sleep and nutrition and all these things. The pre-testing experience is very important for short-term impacts on gait and spasticity in particular. Now, I put this in yellow because I think it's kind of important. I think it's very important and something we don't think about, and that is that in the in-clinic environment, there's dual roles. The research subject is both a patient and a research subject, and they're there for clinical care, and the visit is charged with clinically significant interaction. And the investigator is often both an investigator as well as a caring physician. So there's dual roles on both the research subject, patient, and the clinician investigator. And these roles they're not simultaneous. It's like this minute or this segment of the interaction is a clinical care. Then the next segment of the interaction, immediately following that, is research. And so we may be talking about genetic counseling and childbearing decisions making. And then we may go, okay, let's stop that conversation and now let's watch you walk. And we're expecting that the person's no longer a patient in that moment. They're now a research subject that the previous experience has not influenced the next experience. So I'm sure it does experience that. It does affect that next experience. Cost of clinic. Well, okay, it's expensive. What does efficiency mean? Efficiency, I mean, what's the cost of doing something, and how and what can we do to reduce the cost and improve the throughput? Okay, now let's talk about in-home testing. Well, in-home testing, the person's in their familiar environment. One value of in-home testing is that it may be more valid in the sense that, for example, fall risk assessment. Most falls occur with turning or carrying and with distraction. Turning, carrying, and with distraction. And in the home, I think the number is 3 or 4. The average is 3 or 4 steps before you make a turn in a home environment. So, you walk in the kitchen, you turn, you walk in. There's constant turning in a home environment, which is quite different than in a clinic environment. And fall risk is greater with turning, carrying, and distraction. And so, and there's also the familiarity of the home setting. At any rate, so the home environment may offer a more valid assessment of functional gait performance. Now, our objective, what we're trying to achieve is to use wearable sensors that we would mail to people's homes. People would wear these. The sensors that we have access to record for 7 days. We're not using them now. We're using ones that record for a matter of 8 hours, and we would use them probably for 10 minutes a day for 3 consecutive days. They're low cost, they're easy, they're safe. They're the same inertial movement sensors that were discussed at the CERN meeting the other day, and they permit frequent retesting. So 3-day testing, then we can mail it back in 6 months, 3 more days, that kind of thing. And they reduce the barriers to participation, and in so doing, they facilitate large numbers of people participating. Now, we don't want to throw the baby out with the bathwater, okay? I'm not against in-clinic testing. I think it is very, very important because we want to get these neurologic parameters. We want to do the other testing. So in-clinic functional assessments are very important, at least for now. If we establish that home functional assessments are equally valid as the in-clinic functional assessments. I'm not talking about replacing reflex testing or neurologic testing. I'm talking about functional assessment. But when we establish, and I think we will, that there's, in the PLS population and the HSP population, that in-home testing has equal validity, then we can move away from doing those same tests in the clinic. And it's not a matter that these tests are validated in other subjects, in other disorders. They have to be validated in these disorders, and that's what we're doing now. Okay. All right, so I'm going to move to here. These are some of the things that this is our current panel that we do. I know you can't read all this, but this is a comparison. You just look at the left column, and it shows all of our direct examinations, and then what we call the instrumented examinations. That's with sensor testing. And I put on here several areas. One, finger tapping, foot tapping, and balance, and manual dexterity, and speech intelligibility testing. These I selected out because these are of particular importance for the people with primary lateral sclerosis. Let's talk about speech intelligibility. We're not actually measuring dysarthria, and we're not measuring speech, the volume of speech. I mean, the loudness of speech. In this testing, we're measuring what's called intelligibility. That is, when people read a list of words that's constructed from various phonemes, so different types of sounds that they're asked to, words that contain different specific sounds. They read these words, and then we score how well somebody can understand those words. So the person listening didn't know what the person was saying, both words and sentences. Now, there's a variety of speech intelligibility tests, and they're done by either an investigator listening who doesn't know what the person's saying or trying to say, scoring what they think they heard, and then counting how many errors they made. They're also done by family members, but we are going to use one that are scored by voice recognition software. So the person reads a list of words that are presented to them on the screen, and we didn't invent this. This has been used by other investigators. They're reading a standard list of speech intelligibility words selected from particular categories. They're reading those words, and then the computer scores how well, the computer scores what they think they heard, and we count up the errors. And we have to use a certain not very intelligent speech recognition software so that the computer doesn't get smarter and eventually learn what the person's saying. But we can do that. At any rate, so this is what we're doing. Now I want to talk about these inertial movement sensors. These are the ones like we talked about the other day. We're using the Movella dot sensors. And these we put on many people here have participated in this. Miss Alondra Rodriguez put these on people out here, and we're hoping to do more this afternoon, today. But we put these on the shoes, they're lightweight, and on the wrists and around the waist, and they measure hundreds of parameters. So, for example, this is an example. They measure the trajectory, the lift, the speed of the ankle. And then by extrapolation, by measuring the stride length, the stance, the distance walked, and so forth. Now, we measure lots of parameters, more parameters with these than a neurologist would measure by watching somebody walk. On the other slide I mentioned are some of our standard parameters, a up and go test, a 2-minute walk, a 25-minute walk, a 6-minute walk, foot tapping, finger tapping. We're doing all of that stuff, both in the conventional manner and while people are wearing sensors. But on this slide, this is one person's walking, and it shows on the top part of that figure the left to right movement of their foot, and on the bottom figure the elevation, the dorsiflexion of their foot. With each walk, with each step, each one of those lines is our number of steps, and the foot goes up and the foot goes down, and we can measure how fast it goes up and how far it goes up, and how far it goes up relative to to other factors in the legs, like the knee lifting and so forth and so on. We can measure all kinds of other factors. Now, the middle part is something I'm going to get to in about 2 minutes, and that is one separate discussion is the use of this information for rehabilitation. And that's that black box in the middle where we're going to collect this information, collect measurements, and use this measurement not as clinical trial outcome parameters, which is what we're working for, yes, but in addition to develop this information for feedback for rehabilitation strategies, and I'll talk about that in a moment. This is some of the parameters that the sensors provide. For example, the linear difference between successive foot placements, the lateral displacement. There's a lot of technical things that the sensors give us. But besides those factors, there's what I would call the primary data from the sensors. And that's like, I would consider low-hanging fruit. There's we're using artificial intelligence to analyze the correlation between various factors of gait. Okay, so this is an example. This is one person with primary lateral sclerosis, and this is an example of one person walking for 2 minutes. And each of these lines, and so on the left is a person with primary lateral sclerosis who's walking with a walker. Yes, with a walker. And on the right is a control subject, each walking for 2 minutes. And what we see is they're told to walk towards this target, just like we do out in the hall. Walk towards the target. And like we do during here at this conference. And you can see that how accurate are they in their trajectory towards the target. Well, there's a much greater accuracy in the person in the control subject than there is in the person with primary lateral sclerosis. And so this is just one person walking for 2 minutes. And we can measure their accuracy overall by the size of the circle that includes all the, say 90% of the points. And we can then look at, so we measure accuracy or trajectory, and then we can quantify that. And this is just one example of and there's no way that you would get this information by just watching somebody walk visually. Now, this is a very interesting thing I want to talk about. This is unexpected, but so we use these sensors, the inertial movement sensors. They go on the shoes, the wrists, the waist, and now we're starting out with insoles, putting insoles in addition to those, so they go inside the shoe as well. And we get personalized gait modeling. So we're not talking at this moment about making measurements for outcome parameters. We're making measurements to study and characterize a single individual's walking. And then we use this artificial intelligence, machine learning. And what we found was kind of unexpected. I didn't know this was going to happen, but we in our preliminary data, we looked at 38 subjects with uncomplicated HSP, and we just gave this information to the mechanical engineers. And they used their artificial intelligence, and they didn't know which subjects had uncomplicated and which subjects had complicated HSP. They just had a total of 47 subjects. And using their machine learning, they were able to diagnose the subjects as having either complicated or uncomplicated HSP. And they diagnosed, among 38 subjects with uncomplicated HSP, they said 37 of those subjects had uncomplicated HSP, and one they mistakenly classified as complicated HSP. And we didn't have as many people with complicated HSP. We have more now, but at the time the slide was prepared, there were 9, and they correctly classified 8 of 9 as having a complicated phenotype. And I thought it was I hope this trend continues, small numbers, and we're looking at this so we are now looking at analyzing data to distinguish HSP, if you can imagine this, HSP from PLS by the outcome of the censored analysis. And if you think, well, gee, how can a censored make a diagnosis of HSP versus PLS? That's unimaginable. Well, and that's the second time I've used that word imagination. But that's not unimaginable if you think, well, gee whiz, arm swing is going to affect stride length, and people that have trouble with their arms, I mean, we see it all the time in clinic that people that have impaired knee lifting very often have exaggerated arm swing subconsciously to help facilitate knee lifting, or trunk sway to help knee lifting. So it's very expected that upper extremity factors would affect lower extremity performance. And so I do expect that we're going to be able to find differences in the outcomes between PLS, that is with upper extremity involvement, compared to uncomplicated HSP, that is without upper extremity involvement. I expect we will, but we don't have that yet. But we're working towards that. Okay, this is not, okay, so these are other tests that we're doing. Okay, we'll skip past that. I do want to point this out, that our protocols permit our data sharing. So, with the subject's consent, we can mail their data, their raw data, any of their data. They have to say, please share my data with this person. And we will. We're obligated to do that. So that doesn't mean that means that other investigators don't have to join our protocol and get IRB approval. No, we can just mail them. So somebody at another university who says, we have 10 patients with this condition, could you mail those people your test kit? Well, we'd have to recruit them and consent them and mail the test materials to their home. They would send it back to us, and then we could share this data with any investigator. And that's our intent. The intent is not to make a data silo where we study large numbers of people at the University of Michigan, and that's where the data rests. No, the intent is to study large numbers of people who come from many different testing centers, and we would just mail the data back. That's the goal, to facilitate clinical trials plural in many different places. Now, in the last 2 minutes, I want to talk about this business about when we talk about optimizing or characterizing gait for an individual. This is something that Dr. Ojeda, who pioneered the development of these inertial movement sensors that are used, the technology that's used widely in other sensors, and Dr. Gonzalez Villasante, who's developing the artificial intelligence side of this, that the three of us are working on. What we're talking about is this business to try to use advanced techniques of mental visualization as a rehabilitation strategy. This mental visualization It's not so exotic. This has been done for decades by elite athletes, okay? Golfers who use visualization to train their golf swing, or skiers, or dancers who study over and over again the pictures of the performance they're trying to achieve, so that they can imagine it in their mind. Well, that's where we imagine things, and then use that to facilitate their motor. Baseball players use this. Elite athletes use mental visualization to enhance their performance. We want to develop this for rehabilitation of spastic gait. So, what it is that we want to use what was called ideational motor control. And what do we mean ideational? This is the third time I used the word imagination. All movement, every movement, begins in your imagination. If you say, I'm going to lift this pencil, well, or I'm going to lift this clicker, first, you have to imagine that you're going to do that. And as soon as you imagine that, your brain has a picture of where your arm is and where the object is, and how you're going to move from this point to this point. You have a spatial understanding of it, and also which muscles are going to be moved and which muscles are going to be not moved. So if I'm going to lift my arm and bring it over here, I know that my leg is not going to be moved and my other arm is not going to be moved, and this hand is going to stay where it is. So it's not just that my arm is moving, it's that my entire body is affected by this motor planning. And that process of planning that activity, and that's just before it's moved. And then there's all of the movement happens. It's all reanalyzed as the movement's taking place. All of that is in the not in the motor cortex. All of that is in the premotor cortex, which is next to just in front of the motor cortex, and other areas of the brain, the parietal cortex, the visual cortex, and so forth. Sensory cortex is all involved in planning the movement immediately before the movement occurs. And what people find is that training that planning, that elite athletes have found that training that planning facilitates the movement. So you train the planning of the movement, you train the imagination of that movement, and that facilitates the movement. And we want to facilitate the movement by training the planning. And our method, because we know that this works for athletes, and we want to bring it into a clinical sphere. So our idea is to use these sensors with this individualized characterization of movement to drive, to facilitate motor planning. Okay, so how do we do this? With the sensors, we can create what we call a digital avatar. We can create a picture of the person walking. It's basically like a videotape of the person walking that we can create by having them wear sensors. It's a Hollywood quality avatar, so it looks exactly like the person walking with Hollywood quality. With this scary AI generation that you can't tell if it's real or AI. That's what we do. It looks just like the person walking with the disability they have. It's not them, it's their own avatar. Then the concept is to take a normal subject. Now, there is no normal subject. There's males, females, children, adults, people that have different ages, and so on and so forth. So we have to take a person of the same sex and age and so forth, and then take a sort of a composite of a normal subject, and then create a normal composite avatar that looks exactly like the person with the disability, but their walking is normal. And we can do that. And we can do both of those things. The next step in our imagination of this is to morph the person with the disability gait towards the normal gait by 5%, so that now they have themselves walking compared to an avatar that shows a 5% or 3% improvement. And we haven't done that yet, but we're working to achieve that. And I'm not sure if it's going to be speed or balance or stride length or step elevation. I'm not sure what parameters we're going to change, but we want their improved self to be a very slight improvement. And our test, and we hope to start on this, on that aspect of it, probably next summer. And the test is that while walking on a treadmill, while studying a 5% improved version, does that help the person walk, or 3% improved version, or 1% improved version? Does that help the person, just studying themselves walk better, does that help them walk better? And we have all kinds of ideas about how to merge these two images so that as they're walking, we're regenerating their avatar so it now looks better and better. Now that we haven't done that yet, but that's the goal. So that's what we talk about, using the sensors to make individualized characterization of gait, so we can use that for to facilitate rehabilitation. That's what we're doing. And we hope to do these avatars starting next year. That's it. And if you say, last comment I would make, I've said this before, actually, but how do we, and this is not just for the clinicians, it's for all of us, how do we stay ahead of the curve in our research on this? Well, we have to be that curve. We have to be that frontier. All of us. We can't be derivative. We have to imagine what we want the future to be and how we want to advance this in all of our domains, whether it's in gene therapy or drug discovery, clinical applications. We have to just imagine what we want to and then just develop our imagination. Okay, thank you very much.
Dr. Fink, hey, Dr. Fink, I got one question in the back. We got time for one question, and I got one way in the back, so everybody can look back here.
So, Dr. Fink, with all the advances you've described in clinical testing, wearable technologies, and digital scoring, how do these findings translate into better rehabilitation for treatments right now for people with HSP or PLS? And after all these years of research, how do you believe how close are we to seeing true disease-modifying therapies reach patients?
Okay, I'll start with the second question. I think we're very close to a tipping point for real treatments, not symptomatic treatments. I think we're very close. And why do I say that? Because there are gene therapies for HSP now underway that have already shown that have already been tested for safety and look very promising for safety. That's first of all. So there are already ongoing gene therapy trials now in HSP and in a related condition, adrenal myeloneuropathy, which looks like an X-linked form of HSP, adrenal myeloneuropathy, and these are already ongoing trials. So the trials are underway now for a couple of forms of HSP, now recognizing there are 90 or 80-something different forms. So, it may work in some forms, it may not work in other forms, but there are a variety of other gene therapy approaches being tested with gene supplementation and gene inactivation and so forth and so on. So I think that's moving forward, not just in the United States, but broadly. Second, there are drug discoveries. I mean, we're waiting to hear, it used to be called NU9, now it's Acava something. Yeah, well, anyways, they're waiting for those trials to be extended into the HSP-PLS world. So there are drugs that in the ALS world that we want, when they're shown to be safe and effective, that we're going to use very quick, we're going to try very quickly in the HSP PLS worlds. So there are gene therapy trials that are ongoing in HSP. There are drugs that are being tested in related conditions that are going to be tried in HSP PLS. And there's a recent paper that came out last year. I'm very eager to see how this works out, of a drug that shows promise in SPG11, which HSP. That drug is shows promise in animal models of slowing the progression in SPG11, and that drug is pending FDA approval for humans. And so when that drug is, if it is approved, and maybe it won't be, I don't know if it's going to be delayed or if it ultimately would be approved, but it shows promise in animals and it has pending FDA evaluation now as another drug for, so whether it's gene therapies, whether it's small molecules, drug therapies, whether it's going to be neurophysiologic testing, those are, I mean, there are people are expanding, people have deep brain stimulation for Parkinson's. That's very effective. That's already been expanded into psychiatric disorders, and now it's being tested for spasticity reduction. So whether it's going to be some neurophysiologic testing, whether it be that kind of testing or other kind of testing, spinal cord stimulation or vagal nerve stimulation has been suggested. There are a variety of approaches. Now, as was mentioned, there's a large, well, there's been for 10 years, but a large animal model of HSP, the cow model or the bovine model of HSP is available, has been developed. It's a naturally occurring model, but it was recreated at University of Massachusetts, and that's a place to try drug therapy. So my point is we have resources to try these things in, and we have the methods to try these things. I think we're so okay. Now, if you say, is it next year? I can't tell you. We have a ways to go. We have a ways to go to get to a clinical trial. And I didn't even mention the value of multi-center collaborations that develop the methods for testing subjects and recruiting subjects to allow these trials to go forward. So I'm very optimistic. Now, I don't think it's tomorrow, but I think it's in the near future that we'll have more and incremental growth of clinical trials. Yes, 100%.
Thank you very much, Doctor. That was a great answer, great question, great response. Thank you, Doctor. We're going to take a second here to get set up for our next presenter. Oscar?
No, I can't. You can't. Yeah. No, this is the presenter mode. You can't. Oh, this one? That does end the show. No, this is your presenter mode. This is shared screen there. I'm just gonna try to click this button. Okay. All right. Good.
Closer, but you'll be okay.
All right, thank you.
Okay, everybody. I know you're standing up and stretching, but we gotta keep to the clock. This is Dr. Peter Baas. He's a professor at Drexel University College of Medicine. is a leading expert in neurology and axonal transport. His laboratory's discoveries about microtubule dynamics are reshaping our understanding of how motor neuron degeneration occurs and how it might be prevented. His translational approach offers real hope for therapeutic intervention. Dr. Baas.
Thank you. Well, if I had written that introduction myself, what I would have said is that attending and participating in the SPF meeting every year is my favorite professional activity. So it's absolutely wonderful to be with you all today. And it's really nice that a good half of you or more, this is your first time meeting. I've given talks at this meeting, I think, for several years, and you can watch them on YouTube. But being here with you in person is wonderful. So please don't hesitate to catch me in the hallway or at lunch. Ask me anything at all. And please email me. Feel welcome to contact me in any way that you like. So what I'd like to try to do today is present my research, but also hopefully in a way that demystifies it. So let me start out by talking about SPG4 HSP. This is the variant that I study, and I think that probably over half of you have the SPG4 mutation. This is the most common mutation that gives rise to hereditary spastic paraplegia. There are others. This is the one that I study, but I do believe, as some of the other speakers have said, that any one of these that we study, I think the results are going to be relevant to all HSPs and PLS. So with SPG4, we call this autosomal dominant. And by autosomal dominant, what I mean is it's not sex-linked. It's the mutations, the SPAS gene is not on the X chromosome or the Y chromosome. So boys and girls, men and women have equal chance of having this mutation. And by autosomal dominant, what I mean is that you only need one of your SPAS genes, your SPG4 genes, to have the mutation. And when that happens, we believe it's 100% penetrance. If you have that mutation, either from your mother or your father, then you will have SPG4 HSP. When exactly and how severe the symptoms will be, however, varies extremely among different individuals, even within the same family. It is the case, even though we call it hereditary spastic paraplegia, that there are de novo cases. And by de novo, what I mean is that neither of the parents have the SPAS mutations, but somehow, randomly, the child has a SPAS mutation. So even if everybody who has a SPAS mutation stopped having children, that would not obliterate the disease. It would keep coming back. So it's really essential that we develop an understanding of the disease and therapeutics. Now, let me try to explain a little more anatomically about HSPs, and this really applies to all HSPs. The upper motor neuron, also called the corticospinal motor neuron, is located in your brain. That's in a part of the brain called the motor cortex that I think you've heard a little bit about today. That motor neuron goes all the way, extends its nerves all the way down the spinal cord, and along the way, it synapses with what are called lower motor neurons. By synapse, I mean it makes a connection. So in HSPs and PLS, what happens is the upper motor neuron degenerates. So it's going to pull back from that synaptic connection. And when doing so, now the lower motor neuron becomes dysregulated. And it's the lower motor neuron that extends into your lower limbs, and that's why you have problems with walking. So the upper motor neuron degenerates, but the lower motor neuron becomes dysregulated. I think the lower motor neuron may also degenerate in some cases, maybe not a lot, but somewhat. And this is not well understood because everything we know about the disease really comes from assessments, say behavioral assessments. There's very little cadaver knowledge about the anatomy, actual anatomical dissections of cadavers, because these diseases are not life-shortening diseases. So generally people live a full, complete life and pass away in their elder years. So we don't have that kind of knowledge. But based on everything that we know about the behavioral studies, the behavioral, the disease progression phenotype, this appears to be what's going on. And again, this is true of all variants of hereditary spastic paraplegia, not just SPG4. Now, when you think about disease mechanism, I want to demystify mechanistically how these diseases work. There are really two mechanistic pathways by which a mutation can give rise to a disease. One is loss of function and the other is gain of function. By loss of function, what I mean is now that that SPAST gene is mutated, the protein that it produces, called spastin, doesn't work correctly. And by virtue of the fact that you only have good spastin from one gene, means you don't have enough spastin to carry out all its necessary functions. That's loss of function. You simply don't have enough functional protein to carry out its duties. It's also sometimes called haploinsufficiency, which means half is not enough. The other mechanism, which is actually more common in neurodegenerative diseases, is called gain of function. Now, don't be confused to think that gain means something good. It doesn't. What it means is the mutant protein is present, but it's doing things that it shouldn't. So it's sometimes also called gain of toxicity, because the mutant protein is now toxic. So the way that I kind of like to think of this is the loss of function is the kid didn't show up for class. Gain of function, he's there and he's making trouble. So that's an easy way of remembering it. What's worse is that it gets worse. So one thing leads to another. And this is disease progression, easily understood. Now, you've heard a few of the speakers talk a little bit about gene therapy. And we've been pursuing gene therapy, and I want to, again, demystify a bit about what gene therapy is all about. There are really two components to gene therapy, and what you see here on the slide is a vector, and the vector has multiple parts. What gene therapy is often called is silence and replace. One portion of that vector will silence your endogenous SPAST gene. So again, you've got a mutant SPAST gene, you've got a wild type means normal SPAST gene, and one component called microRNA will turn off the expression. So you won't be making either one. You're normal from your mother, you're mutant from your father, or vice versa. You won't be making that anymore. But the other component of the vector is a DNA that will re-express healthy spastin. So you're silencing what you're normally making, which is in part mutant, and you're replacing it with healthy spastin. And theoretically, whether the disease is loss of function or gain of function, it wouldn't matter, because silence and replace takes care of both. What makes things complicated, and I think you've heard a little bit about this already this morning, is that spastin is actually a rather complicated protein to understand. And as you heard earlier in John's presentation, there are two of what we call start codons in the SPAST gene. And what will happen with these two start codons is you'll make essentially two different proteins. One of them is a bit longer, and it's called M1. And it's a bit longer because it has a membrane insertion domain. And this inserts into the endoplasmic reticulum, other internal membrane structures in the cell, and it'll help shape those internal membranes. The somewhat shorter isoform called M87, that's the microtubule severing protein that you've heard about. So microtubules are cytoskeletal structures. They are important for mitosis in mitotic cells, dividing cells. And in nerve cells, they're the railways that occupy the axons, the dendrites, and enable organelles to move efficiently up and down these processes. What's really important is the length of the microtubules needs to be regulated. So microtubule severing is a normal process that regulates the length of the microtubules. So really think of them as two separate proteins. M87 is controlling the length of microtubules through severing, and then M1 is helping to shape the internal membranes of the cell. So now back to the idea of loss of function, gain of function. With M87, is it loss of function? Not enough microtubule severing? Maybe, but we're not sure. Maybe half is sufficient. With the M1, do you not have enough to shape the membranes? Maybe, but maybe not. Maybe half is sufficient. What about gain of function? When the M87 bears the mutation, and both of them will bear the same mutations, is the mutant M87 toxic? We don't think so. But the M1, when it has the mutation, we think it's very toxic. And we think it's toxic in part because that membrane insertion domain is very hydrophobic. That's how it inserts into the membrane. And whenever a protein is very hydrophobic, what it can do is misfold. And once you've started misfolding a protein, now domains of that protein that normally are hidden inside become revealed. So it aggregates, toxic domains become constitutively active, and now you've got a troublemaker. So haploinsufficiency maybe is a component. Gain of function toxicity of mutant M87, probably not. Gain of toxicity of mutant M1, almost certainly yes. Now, when you think about gene therapy, there are a lot of issues and questions. And some of these have been talked about already this morning, but I'll hit upon a few of them. First of all, the viral transduction. In order to take that vector I showed you and get it to enter the neurons of your brain and do its work, we incorporate into the vector what's called an AAV. It's a virus, so it transduces the cells. It essentially infects your cells and then can introduce those components of the vector that I talked about. If you're dealing with a mouse model or a rat model, it's pretty easy to get that viral vector to transduce almost every cell of your brain because that animal is so small. The human brain, by contrast, is big. So transducing enough neurons in the human brain is always going to be a limitation, at least until the virology experts develop even better AAVs. But for now, particularly an adult human brain is quite large. So you never know exactly how many neurons that you'll need to transduce to elicit a positive effect. That's a limitation. And also, as you heard a little bit about this morning, you have to be very careful with these viral vectors in human patients because sometimes they can cause problems like cancer. Another potential issue is with the microRNA to turn off the endogenous Spast gene. You have to choose these very, very carefully to reduce the endogenous spastin, but without reducing any off-target genes. So you want to be very careful when you select the microRNAs that you're not doing more damage than good by turning off other genes. Probably more important, the mutant M1, when it misfolds and aggregates, it becomes very long-lived and it'll accumulate in your spinal cord. So just because you've turned off the expression of more does not mean that that mutant M1 is going to degrade very fast. It might degrade with time, but not very fast because it's stable. So that's a potential limitation. Limitations associated with the DNA component of expressing more spastin, you've got to be really, really careful about expressing too much M1 or too much M87. Too much M87 will destroy your neurons. It'll chop up all the microtubules, and then your neurons will die. If you produce too much M1, you might just recapitulate the very disease you were trying to stop, because even the wild type M1 could aggregate in the same way that the mutant does. So with either one of these, you have to be very careful. So these are some of the limitations associated with gene therapy. I'll talk about a few more in a moment. But let me introduce you to our mouse model. This mouse model is one that expresses human mutant spastin. So we've left the mouse spastin genes alone, and we've introduced the human mutant spastin. So this mouse does not have the haploinsufficiency component, but only the gain of function component. In the upper panel, you see the wild type, the normal mouse, and it's walking the beam just fine. In the lower panel, you see the mutant mouse, and notice how it's really, really struggling. If we pursue the histology, the microscopy, to take a look at their cortical spinal tracts, where you see the big blue arrow is you see specifically the cortical spinal tracts are severely diminished in this animal. And this occurs adult onset, about 3 months of age for this animal. So both behaviorally and anatomically, we have a pretty good model for SPG4 HSP. Now, in pursuing the silence and replace, to kind of make a long story short and show you schematically, this is Dr. Emanuela Piermarini, who's really done all of this work in my lab, and she's hard at work back at home, just getting this paper published, as a matter of fact. And so what we've done is we've introduced this gene therapy vector into the newborn mouse. So remember that the symptoms don't arise until about 3 months of age. We don't quite know when the cortical spinal tracts start to degenerate, but the newborn pups, the baby mice, seem to be pretty normal, and we introduce the vector at that point. And when we do, both behaviorally and anatomically, they never acquire the disease. So it's 100% effective at preventing the disease from happening. So we consider this quite a success. Now, I'm just going to flash this slide up for just a moment to let you know this is a lot of work from Emanuela and from our colleagues at UMass that developed the vector. Western blots, behavioral analyses, histology, but all of this effort culminated in the conclusion that if we introduce the vector in the newborn, we completely prevent the disease from happening. Now, introducing the vector into a pre-symptomatic mouse or a human is less of a challenge than it would be for just about everybody in the room today. And the reason is that your upper motor neurons, your cortical spinal tract, has already begun to degenerate. That's why you have trouble walking, why you're in a wheelchair, why you may have some other secondary struggles as well. So what's going to happen when we introduce the gene therapy into an individual who already has a degenerated spinal cord? That's going to be more of a challenge, because theoretically we may be able to halt the progression of the disease, but can we restore to you what it is that you've lost? That's the big challenge. Another thing about the gene therapy is, remember, there's two components to it. There's the microRNA to turn off the expression of your endogenous SPAS genes, and then there's the DNA to restore physiological levels of the SPAS protein. But we really don't know which one of these is necessary. It may be that haploinsufficiency is not a component of the disease. Maybe half as much spastin is perfectly fine. In which case, all we would have to do is turn off the expression of the mutant gene. That's all. And we can do that with antisense oligonucleotides. Antisense oligonucleotides don't require a viral vector. They're not problematic in that sense. They're not toxic. If you take them and they give you any problems, you can just stop taking them. So antisense oligonucleotides theoretically are a wonderful option, assuming the disease is only gain of function. Now, what's also a little tricky about it, though, is that the antisense oligonucleotides, if they are to target only your mutant gene, they have to be designed per patient. So every one of you would get a different product from a company making antisense oligonucleotides. So that would be a more expensive option than, say, gene therapy, in which everyone with SPG4 would get essentially the same vector. Another option is small molecule inhibitors. So remember I said that mutant M1 is very long-lived, and it's creating toxic effects. It's doing crazy things that it shouldn't do. And if we can identify what those things are, what is this mutant protein doing that's gain of function? And one of the things that we've discovered is that it hyperactivates a protein called casein kinase 2. And that's a kinase. And what a kinase does is to phosphorylate proteins. It adds a phospho group to proteins, which turns out to be pretty important. And if you're doing too much of that in an unregulated way, that could be the mechanism of your degeneration, or at least contribute to it. So if we had a way of selectively inhibiting casein kinase 2, that may be a therapeutic that couldn't get rid of the mutant M1 protein, but stop its toxicity. So that's an option. And I think Oscar's going to talk about some other options, and maybe the Unravel group will talk about some other options a little later today. But small molecule inhibitors are one way of inhibiting the gain of toxicity effects of the mutant M1. Now, if it is haploinsufficiency, there's some other researchers, Cinzia Rinaldo is one of them in Italy, who are working on ways of increasing the activity of the spastin that you already have. So you wouldn't have to express more, but use an indirect way of activating more of what you have. Another small molecule inhibitor that we're working on are called kinesin 5 inhibitors. And I wanted to throw this slide up just to show you that in iPS cells from Oscar's lab, notice how beaded up they are when they bear the SPAS mutation. And if we put on a kinesin 5 inhibitor, notice that those beads are fully resolved. So this is very effective at remedying at least this manifestation of the toxicity. Now here I'm showing you what's called a Western blot. And a Western blot is a biochemical way that you can look at proteins, their size, their mobility on what's called a gel. And what you can see here is this big fat band, that's M87. And that really light band that you see only in the adult, that's M1. So we think this is why in most patients the disease is adult onset, because there's very, very, very little M1. Even though it's so toxic when it's mutated, there's very little of it. In fact, there's probably very little of it because of its tendency to become toxic. And the fact that you only pick it up in the spinal cord probably is why corticospinal degeneration is the hallmark of HSP. And maybe this is true across HSPs. Wouldn't it be interesting that regardless of what variant of HSP you had, it all wound up to be M1 problems? We made recombinant monoclonal antibodies to M1. And initially we wanted to make these antibodies because it's so difficult to quantify M1. In the gene therapy studies, we need to quantify how effective is the gene therapy, and we do that on Western blots. But the M1 antibodies also have another potential purpose. By recombinant, I mean that we know the sequence of the antibody. So antibodies are proteins too, and they have a sequence as well as other proteins. And we can make these antibodies into what we call intrabodies. And what the intrabody means is we can take that DNA sequence and we can express it in the neurons, just like the gene therapy vector. But this time, what happens is the M1 antibody will bind to the M1 protein and deaggregate it, detoxify it, and potentially target it for degradation. So the antibody was used in Emanuela's gene therapy study. You can see the green bands here with the antibody that we made. And here's that intrabody approach. And schematically, what you see here is that the M1 spastin protein has this hydrophobic domain, but it also has the toxic domain, which we think is at the very tippy tip of the M1 specific region. When the mutation occurs, you can see schematically that now all of these toxic domains are extended outward. So now you have an aggregate that's rippling with toxicity. The intrabodies within themselves, we think, and we have some evidence already, will deaggregate the aggregates. And that may be perfectly sufficient for the normal protein degradation mechanisms to kick in. But if not, if that's not sufficient, we can actually add sequence, proteasome targeting sequence that will target the antibody antigen complex for degradation. So with this strategy, we're going right after that mutant M1 to deaggregate it, detoxify it, and degrade it. So if that's really the culprit, we can get rid of it this way. Now here's the tricky thing that I alluded to a little earlier. The symptoms are getting worse and worse, whether it's our mouse model or whether it's human patients. And the worse the symptoms get, the farther along the disease progression, then any of these therapies are going to become less and less effective because your spinal cords are already degenerated, and we may be able to slow or halt the progression. But how do we get back what you've lost? How do we get it back? And that's where the physical therapy comes in. Now, I'm going to guess that almost everybody in the room undergoes some form of physical therapy, and I'm going to guess that most of you are not very satisfied with the results of the physical therapy. And that's because your disease mechanisms are still at play. Your spinal cords are still degenerating. So you can go in with exercise and all sorts of physical therapy, and it'll help a little bit, but not as much as you'd like because your disease mechanisms are still kicking in. But if we can go in with gene therapy, if we can go in with intrabody therapy, if we can go in with small molecules inhibitors, if we can go in with the ASOs, the antisense, and stop the disease progression, now I'll bet you the physical therapy is going to help you a lot. And that's what we're thinking, and we're partnering with the Marion Murray Spinal Cord Research Center at Drexel. So these are people who've studied spinal cord injury for 40 years, and they have a lot of techniques they use. They're very much into exercise therapy, the benefits of exercise therapy. Your degenerated spinal cord is almost certainly not going to regenerate. And you probably wouldn't want it to because you don't know if regenerating axons, nerves, are going to go to where they should. But what the exercise therapy does is it stimulates neurotrophins so that your healthy axons will sprout and they will reroute and they will find the correct targets. So you may not walk the same way that you used to walk. You may walk differently, but you'll be able to restore function, we hope, by rerouting your nervous system in this fashion. So exercise therapy is very powerful in that regard, and we can actually also give you neurotrophins directly inject them or use a gene therapy-like approach, increase your neurotrophins, and hopefully restore the functions you've lost. Not entirely, but I think we can do pretty well. The other strategy, in addition to exercise therapy, is the neurostimulation strategy. And neurostimulation is not as well understood mechanistically. Why does it help? But it seems to help a lot. So here we have cerebral palsy patient. Now, for all we know, this child has SPG4 HSP because we know that cerebral palsy is often a misdiagnosis of SPG4 or other HSPs. But notice that this child is not putting his feet down at all. But when we apply this neurostimulation, and what I mean by neurostimulation is this is not any kind of surgical implant. This is simply taking these electrodes and taping them onto the individual's back in the spinal cord area. So it's very non-invasive. It's not going to create any harm. And notice how while this child's spinal cord is stimulating, that he's walking pretty well. And what the studies have shown, we don't have a lot of clinical trials yet, but what the early anecdotal studies show is that if you apply the neural stimulation, say a couple times a week, 1, 2, 3 times a week, that this will be long-lasting. It's not only while the patient is hooked up, but it will be long-lasting. So the device, this X-step device, is being used for bladder control, for example. I know that almost everybody, adults who suffer from hereditary spastic paraplegia or PLS, have bladder problems. So this is very good for bladder problems. As you can see here, it offers a lot of hope for walking as well. And I would bet you that if combined with the mechanistic therapies that I described earlier, that whether it's exercise therapy or neurostimulation, it's going to do a lot more good and really, really even surprise the individuals who are doing this kind of work. So later today, I think at 4 o'clock, you'll hear a lot more about this neurostimulation technique from my colleague, Rahul, who's in the audience today, Rahul Sachdeva. He's at Kentucky, University of Kentucky. So the next issue is, how do we know when to start the therapy? Now, you may have someone in your family who is 5 years old or 10 or 14 or 20, 25, or even 60. You know he or she has the mutation, but there's no symptoms yet, no apparent symptoms yet. So do we really want to go into a person who seems perfectly fine and start giving gene therapy and small molecule inhibitors and all this kind of thing? What we'd really like to know is when to start the therapies, because it's kind of pointless to start 20 or 30 years before you have to. And that's where biomarkers become very important. So what is a biomarker? A biomarker is something, hopefully in the blood, because the blood is easy. You can extract some blood, you can perform a biomarker assay, and then you can know how far along in disease progression this individual is. In addition, you can test how well the therapy is working. So imagine this. Imagine you've got a patient who has had maybe the intrabody therapy, and maybe this patient has gone in to have the neurostimulation, and you want to know, is it helping? Now, you can, hopefully the person will be walking better, but if you want an independent assessment of whether it's working, you can take a blood sample before the therapy, you can take a blood sample after the therapy, and then you can use the biomarker. So the biomarker will tell you when to start the therapy and if the therapy is working. That's an ideal biomarker. These days for HSP, what people have been using is something called neurofilament protein. The problem with neurofilament protein is that's in every single neuron of your body, so it's not very specific. What we've been pursuing is a particular isoform of tau. Now, many of you have never heard of tau, but I think all of you have heard of neurofibrillary tangles. That's what happens in Alzheimer's disease. They're made up of tau. That's what tau is. Well, it turns out that the many neurons of the body, particularly the peripheral neurons, and as it turns out, the lower motor neurons, and I think the upper motor neurons, express a very specific isoform of tau that's not expressed anywhere else in the brain or spinal cord, and that's called big tau. It's a bigger variant from the same gene. And look what we've got with our animal model. What you can see, this is called an ELISA assay. It's kind of like a Western blot, but you just put the protein on a filter paper and then you apply the antibody. And the wild type mouse just gives us this kind of dull green appearance. But look at our mutant mouse. See how bright that is? That's a good positive signal. And this is with our mouse. So we're very excited about big tau as a biomarker for the disease. And you can see quantitatively in the graph just how much big tau there is in the blood of this mouse. So what we want to do is we want to go back with the mouse and look at the mouse at newborn age, 1 month, 2 month, 3 month. And I think what we're going to see is a point along the way in the life of that mouse when the degeneration starts. And that's probably the age at which we should begin the gene therapy. Maybe it's 2 months, maybe it's 1 month, but we'll find out. And then we'll also be able to test the blood that we've already done the gene therapy. And we saved the blood, by the way, so we're in good shape. And we can test that blood and see if the gene therapy is also reflected in the blood of the animals that underwent the gene therapy. And moreover, through collaborations with Darius, we can get the blood of the patients, the children who have de novo cases of HSP, and they've donated their blood, and so the progression of the disease, we can look at it. And then, again, any therapies that we apply to the human patients, we can see if it's working. So, we have a nice model, mouse model. We have very good data showing that gene therapy is effective if applied before symptoms arise. And we have an intrabody approach that we're working on. We have small molecules we're working on. And I just want to talk briefly about one more tool, and that's a new mouse model. The old mouse, the one we've been working with, was created with an older technology. And again, we left the mouse genes intact and we introduced the human mutant gene also. So it only tests the gain of function component. The new technology, I think you've heard the word CRISPR-Cas9 a few times. The new technology, what we've been able to do is to go into the mouse and literally replace both mouse genes with 2 human SPAS genes. So this new mouse has no more mouse genes, only 2 human SPAS genes, and one of them has the Lillian-Blair mutation. So we're very excited about this new mouse as a far more, I won't say perfect, but a better model of SPG4 HSP. And so we're very hopeful about this model to be used for studies in the future. The other thing that's really nice about this model is we're able to put these little tags on the wild type and the mutant genes, so it'll be very easy to tell. Are we depleting the mutant gene or the normal gene or both of them? It'll be very easy to tell. So I think this mouse will be extremely powerful in that regard. And I want to acknowledge the Lillian-Blair Foundation for paying for this mouse. So these are the people who contributed to the work that I showed today. Our collaborator, Miguel Estevez, for the gene therapy, and others in my lab, Brighty and Korai, who did some work on this, and another collaborator, Gerardo, who worked on the CK2, the casein kinase 2 inhibitors. I want to give all the credit in the world to Emanuela Piermarini, who really did almost everything I presented today, and she's absolutely wonderful, and she's back home. We've almost got our gene therapy paper accepted, so I'm going to rely on all of you once it's published to publicize all over the place so we can really stir up excitement about it. And then also, of course, I want to acknowledge Oscar, Dr. Qiang, who will be speaking a little bit later today. So really the big conclusion here is we have a plan. We are developing a multi-tier regimen that may include gene therapy. For some of you, it may be intrabody therapy, it may be ASOs, it may be small molecule inhibitors. Whatever it is, I think it's going to be coupled to exercise therapy, physical therapy, neurostimulation to get you back to where you were a while ago. That's our hope, and the whole goal here is to restore lost function. And I know it's an ambitious goal. I know that a lot of people have probably told you that the best you can hope for is not to get any worse. And whether they are correct or not, I don't know, but I refuse to settle for that. And
Doctor, would you like to take a question?
I would love to take. I just want to acknowledge these wonderful people from SPF and these other foundations. And many of them are here today, and I just want to acknowledge all of them. All right, questions? Questions?
Hello, Dr. Baas. Given the potential of the neurotrophin injections, are there any safe ways these could be tested in people for HSP and PLS today, or are they still in the preclinical stage?
It's kind of a good question if we're interested in stimulating new growth. And fortunately, like I said, I'm surrounded by the spinal cord injury field, and I can consult with them about it. I'm not sure if that's really made it into human patients yet. I don't really see a problem with it, though, because it's not like you're transducing the brain. You know, you're transducing essentially your muscles in order to get the nerves to grow. To grow in that direction. So it seems to me to be quite feasible. I mean, overall, I guess my thought is that we better stop the HSP mechanisms first, before doing that. But it's something we're certainly excited about, and I think it's tractable. It's not, like I said, not nearly as challenging as the brain.
Thank you, sir. I got another one right here.
Peter, amazing talk, and I'm really moved when you said, I don't settle for that. So I think everyone in this room, are with you on that. So thank you so much for, stating this. I have a question about your gene therapy approach. Maybe I missed it. Do you use AAV? Do you use overexpressed wild-type form? Do you correct gene expression? What kind of vector system do you use? Can you give a little bit more detail, please?
Yeah, it's AAV9, and it's a cDNA for human spastin, and it's a neuron-specific promoter. Now, it's not corticospinal specific, but it's a neuron-specific promoter.
CLV or CBK1?
It's what is that? MECP2 promoter.
MCP2.
Yeah,
okay,
yeah.
right.
So it's a neuron-specific promoter. I mean, some people have approached me to say, well, why don't you use a corticospinal specific promoter? And I think, Hande, you have dealt a lot with developed corticospinal specific promoters. And I suppose my response to that is there are a lot of patients who have symptoms that are not explicable simply on the basis of corticospinal degeneration. There are people who have language difficulties, speaking difficulties, I should say. There are some people who have cognitive challenges and so forth. So my first thought is that you'd want to transduce other tracks as well. Right. Unless, of course, it caused a problem. If it caused a problem, then you'd want to go back to a corticospinal motor-specific promoter. But so far with the mouse, I must say, Hande, I think we just got lucky. I think the vector that we used worked really, really well. And it didn't have to. I mean, if we used a different promoter or another scenario and we expressed too much spastin, it could have been a tragedy.
And then you overexpress, or you express the wild type form of the gene, right? So that's
Yeah,
the
yeah, the
strategy.
wild type, yeah.
Yeah,
And the
it's-
microRNA will remove all of the endogenous spastin, both the mouse spastin and the human construct we knocked in to create the mouse. All of that will be turned off and then replaced by the cDNA.
Thank you, Dr. Baas. That was fantastic. Guys, I wish I could take 50 more questions. We've got to get you to lunch. We've got another presentation we got to do. Dr. Baas is available. You want to ask that question? Sit at his table at lunch. You can get a whole hour with him for free. I swear, I'm telling you guys, they're here. They're next to you. They're sitting there. Go talk to him. He's available.
Yeah, don't
Okay.
hesitate. Just grab me anywhere
Grab and go.
talk.
Grab and go. This
I'm
is the
happy
best.
to talk with you.
Dr. Baas, thank you. Guys, we're going to take a quick second to do a quick flip. Don't go nowhere. Don't get up.
Yes. I'll open it back.
Come up on this one. Thank you, sir. Thank you, thank you, thank you. She'll control the videos for you and everything.
Yep.
Do you want to just use this one?
Yeah, I can just use this one.
Turn this one on. I'm going to do a quick intro for you. Okay, just like we always do. Hey, you guys, real quick, while we're getting ready to set and do this, remember, you can still buy your 50/50 tickets on your way out, on your way to lunch today. We're trying to set a goal of about $1,000. We'd like $1 million, but we know it's kind of tight right now, but do the best you can. But we're going to hit that goal of $1,000 today, and we're going to be doing the picking after lunch, back here in this room, after we get everybody back in the room, okay? And you know what it is. You know the old sign, you can't win if you don't play, and you got to be in the room when it happens, okay? You can't be chasing you down the hallway looking for tickets, okay? So you got to be in the room to win. And we have two prizes. One is a 50/50, and the other is for the Cadence Shoes gift card, which is pretty cool. Okay, we're almost ready to go. Looking good. I think we're getting close here, but I'm going to do my intro now. Anyway, we're distributing you guys some folders out there for you for this presentation. So keep going. Here we go. Ladies and gentlemen, this is Javier Tuel. Backed by popular demand, he returns to lead another energizing session, reminding us all of the importance of movement, mindset, and community connection.
I think we need a second before we get started, but I am the warm-up before lunch. That's always exciting. So if I'm getting you guys hyped up here. So I think you give us a couple seconds and we'll get started.
Well, I thought I timed that out perfectly. Okay, the Vita C is working pretty good. It's not quite all the way. Oh, by the way, thanks for giving me the extra Vita C. I enjoy it. Apparently, you're only supposed to take one of those a day. I think I blew past that about 600,000 milligrams ago. So if I get goofier as the day goes on, you'll know why. So, but anyway, are you guys all having a good time? Are you learning anything? Okay. And it's also interesting, you just saw a little action between two researchers there, that last question. So you're in the room where it's happening, okay? You got researchers asking other researchers other questions about stuff, and they're learning from each other, and they're working collaboratively, and they're making this research, and they're doing all this on the behalf of you guys here. And I don't know about you, I understand it about 4% of what I saw, but I know that it's really important, and they're drilling down, and they're getting closer, and they're moving together. And if this is the most positive day I think I've had in a long time, and I love coming to this event, and I love being a part of this foundation, and I love listening to these guys and seeing what everybody's doing. So I'm hoping I'm feeling the best I can. And I'm just going around. Don't worry, you don't have to worry about lunch. It'll be there when you get there. No problem. It's not going anywhere. And then this always happens. There's so much information for people to present. There's so many interesting questions. We could do hours and hours on just a Q&A, okay? But we got to get to these other information. And there's even more great stuff coming your way after lunch. More and more and more great information that you're going to learn about. Now, the best part about this, you all have to go home and glue it all together, okay? And you got to figure out which pathway and where we go and what we do next. But the main thing is, and my wife, Tina, back there she is. There she is. The one thing we do with her all the time is we keep her healthy and strong and working out and being ready and if you need anything, she's available. She's ready to step up at any moment, at any time. And I know everybody here would do the same thing. These guys are on the cutting edge of moving to the next step. And the best part about being this foundation is the amount of people that we have available. When they ask for people, when they ask for specifics, we've already got that. We're working on the biomarkers. We're collecting this information. The survey was the most brilliant thing put together by our fabulous volunteers who collected so much information that everybody is just in wonders of, because they can see it from your perspective. And that helps us. And I'm looking to the right, and we're now moving to the podium. We'll see what happens next. You're going to connect up there or just work from that? Okay, you're good to go. All right, ladies and gentlemen, Javier.
I was kind of nervous before, but now I'm really nervous. Let's see here. Should we just go? Okay. I'm just going to go. All right, my name is Javier Tuel, and I was here yesterday. I'm very excited to be back again today. I am a father, a son, a brother, a friend, a business owner, and a personal trainer. And the reason I bring that up to you, because I think a lot of times when you have a diagnosis, or you're a friend or family person with diagnosis, you forget sometimes who you actually are. And I want to tell you, that's probably one of the most important things I can talk about today, is you are not defined by your diagnosis. And if you are helping someone who has a diagnosis, don't forget that you are also a mother, a husband, a wife, all those other things that go along with those characteristics, okay? Energy check. How's everyone feeling today? Let's try that again. Energy check. How's everyone feeling today? Thank you. So I asked that, did anyone have a little bit more energy this morning, or are you guys getting a little bit tired? This morning, I get up every day, usually about 2 o'clock in the morning by choice to get up and work out, because I have clients that start with me at 3 o'clock in the morning. So this morning, I got to sleep until 6. And it was exciting, because I ended up going to the gym. And I did see some people in the gym this morning, and I was really excited about that. The other thing is the gym is very small, so that we got to know each other very, very well. Remember from yesterday, movement is for everyone. It isn't about being perfect, it's about progress. Movement doesn't have to be overwhelming. It starts with just one step, one stretch, one choice. The power of small wins, and I'm going to tell you guys a quick story, and I'm going to get you guys to lunch as quickly as I can. The story is one of my favorites. It's simple, but it's so telling for so many of us sitting in this room. Kim was a mom of some wonderful boys, a wife, an employee, so much more. She was in the process of giving back to herself by taking a few hours a week to train. The first month of training, she had a lot of success. I believe the biggest success that I saw was the smile on her face after working out with her kiddos. She had a sense of pride. I know she was showing them how important it was to take time to get back to herself and to get healthy. You could see how proud she was. A few days after Mother's Day, I could tell Kim didn't have the smile the same way as she usually did. After a while, I finally asked Kim, what was wrong? Kim broke down. I just threw it all away, all my hard work. I told Kim to explain. She went on, Javier, I drank a Coke. And I smiled and asked her a simple question. How did the Coke taste? Now here's the thing about this story. Kim used to drink a lot of Cokes every single day. And she stopped drinking Coke to get healthy. But that one small little failure that she thought was a failure was a big success. Because I asked her the simple question, how did it taste? She's like, Javier, it tasted so good. I was like, you won. You changed the perception. There's going to be a lot of days, and I want you guys to put this in perspective, that it's hard to do certain things. But if you can do one thing that you didn't do yesterday, you won. If you got your socks on this morning, you won. For me to shave today, I had to laugh because I told Justine I only cut myself once this morning. That's a big step for me. Last night I went to a restaurant. I sat and looked at the whole Capitol. It was amazing to me. I'm deathly afraid of going out. I'm afraid people are going to see me shake when I eat. But I did a big step yesterday. That's a win. I'm not sure if every day is going to have wins. But the days that I do have wins, I need to make sure I give myself a high five for those. And I want you guys to do the same things. It's like the Coke, right? So if you guys have a win, please take those wins and hold them tight and be proud of yourselves. We're living day by day. So what I'm going to do is I'm going to do an individual workout plan or individual goal plan. And the reason I want this is because I'm a true believer if you write something down, you're going to challenge yourself to do it. Why goals matter? Because they give you accountability. They give you clarity. They give you self-belief. Goals don't need to be huge. Sometimes the most powerful are the simple and repeatable goals. This individual plan is very simple. You guys have one in there, and you guys can use it if you want to. I really hope you do. You put your name on it. My name is Javier Tuel. This goal belongs to me. The trainer, and for some of us, is going to be ourselves. I am my own trainer. So I'm responsible for doing for this goal. I set this goal on 4/25/2023. The goal is very simple for me, was to get comfortable eating out with others in public. And why is it such a big goal? Because I think I was selling my family short. I think I was selling some people in my life short. I was afraid to go to a restaurant to eat, so I wouldn't go. I would eat at home. I would do less social things. So my biggest goal, it wasn't just to get in better shape, it was to do something that was going to help me and those around me. So I had to come up with a goal. Strengthen my grip. So I practiced that. And I will tell you guys, I was in Milwaukee a couple weeks ago. 2 trips in 1 year. Pretty exciting. And I went to a steakhouse. And for the first time, I felt comfortable cutting my meat with a knife. It was an exciting thing for me. So I hope you guys do this. Another simple goal for us is to remember who you are. If you need to, you might have to write down, I am still a dad. I am still this person. And what is it going to take to get there? You can't forget that. It's more than just an individual workout goal. It's an individual goal for yourself. And it can be as simple as this. If I can get the screen to move. Write the word believe down. That was the very first goal I ever set for myself when I started this journey. And it's a big goal. I wake up every day and I tell myself one thing. You got to believe in yourself today, Javier. It's not always going to be easy. But it's as simple as if I don't write it down on that piece of paper that's an individual workout goal, I write it down on this thing that says believe right there. So please, do that for yourself today. When you go home, write it down. If you guys get on my Facebook page, again, I'm not asking you to be my Facebook friend. But if you want to, I'll take you. Every single one of my words after every sentence that I write is believe. It's an individual diary for myself, not to let me forget. Okay? Let's go to the next slide. So this isn't a sales pitch. In the last few months, we've designed something because I wanted to do something to give back. We designed the Believe Stronger app. And the Believe Stronger app, you guys get for absolutely free. We've made it free for every single person that we can possibly give it to and get the word out to. The Believe Stronger app was created because people had reasons why they couldn't work out. Number 1, the workouts were too hard. Number 2, they didn't have confidence to work out. Number 3, they couldn't afford it. We've tried to take everything, all those away. all barriers away. We're going to present this on January 15th, and it's a community. And we have 3 tracks of workouts. Those workouts are stability track. Stability track is for somebody who needs to use a chair. There's power core track. That's for people who want the most intense workout you can possibly get. And there's also a chair track for someone who needs to do the workout in a chair. And the reason we put those all together, all the workouts are simultaneously. So each day you'll be doing the same workout as someone with modifications. And why is that important? Because we want to be included. So I'm going to show you some of those today. You guys all have a card in your box that you guys can see and that you guys can download the app if you want to. And if you're already working out, please do me a favor, continue to work out, and you guys can use this app if you want to. This app is also inclusive. You can give it to your friends and family. If you have a son or a daughter or somebody who has more intense workouts than you, like, join me. There's challenges, there's community, there's going to be information for you guys. There's motivation. So you know what? Let's work out. If you can stand up, stand up. If you can't stand up, that's all right. If you need to use a chair, use a chair. About 3 years ago, I decided I wanted to learn how to ski again. I have troubles turning to the left. I turned to the left too hard one time, buried myself into the snow. Now I had to use a chair for 6 months, came up with a lot of these exercises. And today, we're gonna play a little bit of music, because yesterday I was thinking about this as I was sitting here. I was like, what's gonna get you guys a little bit more motivated for lunch than a little bit of music and working out? Because yesterday I was just trying to count down. But we're gonna start off with a seated march, and if you can't do a seated march, you're gonna do alternating arm raises, where you just go just like this, alternate. But otherwise, you're gonna do this. And if you can do both, you're gonna do step, up, 1, 2. Otherwise, it looks like this. 1, 2, 3, join me. 4, 5, 6, 7, 8, 9, 10, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Shoulders here, up, shoulders, up, shoulders, up. 5 more. 5, 4, 3, 2, 1. Let's roll them backwards. 1, 2. Let's do 10. 3, 4, 5. It's okay to smile again. 6, 7. Come on now. 8, 9, 10. Torso twist. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now let's roll our necks like this. 1, 2, 3, 4, 5, 6. Come on now. 7, 8, 9, 10. Other side. 10, 9, 8, 7, 6. You're gonna be ready for lunch. 4, 3, 2, 1. Let's get in the workout. If you're here, stand up. You're gonna go just like this. Arms out. And you're gonna hug a tree. We're gonna go 1, 2, 3. Now do me a favor, flex your pecs. And if you need to, we're going right here. Let's do 8 more. 8, 7, 6, 5. Squeeze harder. 4, 3, 2, 1. Great job. Next one, we're gonna do a back exercise. You're just gonna lean forward just like this. If you're in a chair, you're gonna lean just like this. And you're gonna take your elbows and we're gonna row here. So let's do 10. You guys ready? 1, 2, come on now. 3, 4, you got this. 5 more. 5, 4, come on now. 3, get it. 2, 1, shake it out. Good job. We can do this. Next exercise, we're gonna do shoulders, seated, overhanded. We're gonna do standing face pulls. You're gonna stick your hands out like this. And pull. Let's do 10. Here we go. 1, 2, come on now. 3, get it. 4, come on. 5, 6, 7, 8, 9, 10. Shake it out. Let's do that one more time. Hands up. Here we go. 1, 2, get it out there. 3, 4, come on now. 5, 6, almost there. 7, 8, 9, 10. Good job. One thing I want you to think about every time you do an exercise, take a deep breath. Bring it in, exhale on the out. Next exercise, we're gonna do triceps. You're gonna go right here behind your head. And extend up. Elbow to wrist. You guys ready? We got 10. Here we go. 10, 9, 8, come on. 7, 6, 5, 4, 3, 2, 1, and break. Every motion you do, it keeps us independent. It doesn't matter if you have a diagnosis or not. This is so important, guys. Next one, bicep seated curls. You're gonna lock your elbows tight right here. Curl. 10, let's go. 10, 9, 8, come on. 7, 6, 5, 4, 3, 2, 1. Now who's up for a challenge? We're gonna do a seated leg extension or standing leg extension. So if you need to, hold your chair, bring your leg up. If you're in the chair, bring your leg up, right here, and kick it out. 1. So if you need to, right here. 1, 2, 3, 4, 5. Other side. Pick it up. Let's go. 5, 4, 3, 2, 1. Great job. How you guys doing? This is amazing. What I'm saying right now is I'm showing you guys you have the capability to do anything that you put your heart to. I promise you. If you got to make the modification, make the modification. Yesterday we did a challenge one, and each day there's going to be a challenge. Today's challenge, you're just going to go just like this. Hands like this. And you're going to make a hammer, and you're going to come right to the middle. And we're going to do this for 30 seconds, and you're going to go as fast as you can with good form, okay? And this is a challenge because I want you to do it once, and then we're going to do it again. Our goal is to beat it the second time. But do not cheat on the first one by not going as hard as you can. Remember what I said. Believe in yourselves. Okay? This is for you. Every exercise, every movement is to help you stay independent and to remember you guys got this. Right here. Get set. Here we go. 30 seconds. Just dig deep. Come on. 15, halfway there. Keep going. Almost there. Don't stop. Keep count. You got this. Break. Now remember how many you did. If you didn't remember, just go harder the second time. Change the song. Okay, so every day there's going to be a challenge in our lives, right? So the goal is when you wake up, I tell myself every day, I give myself one chance to tell myself I'm tired every day. That's it. The minute I get out of bed, if I'm tired, that's when I say it because I don't say it again. So I want you to change the way you think. Every day is an opportunity to be the best we have. We just did 30 seconds of an exercise. On this one, do better than you did last time. And I want you to start thinking about that every day. I want you to do better than you did the day before and do the best that you can that day. You guys got that? Are you guys ready? Are you guys ready? Okay, I'm going to tell you something. When you wake up in the morning, I need you to do, yeah. Are you ready? You tell yourself in the morning when you wake up like I do every morning, are you ready? Yeah. Let's do 30 seconds. Here we go. You ready? Let's go. Come on. Push hard, push hard, push hard. Come on. Almost there. Halfway there. Beat your last one. Come on. Get it. 5, 4, 3, 2, 1. Clap for yourselves. Okay, I'm not going to let you sit back down because Norma says I got to keep you guys up. But I want to thank you guys for giving us the opportunity to come out. What I want to tell you is so important. What you guys just did is what we need to do every day. We need to believe in ourselves. We need movement. We need motion. And I promise you right now, these doctors, what I'm hearing, are doing the best they can to help us get to where we need to be at. But until we find that cure, motion and movement are what we got. So please use it as much as you can. And I'm going to tell you something. Get on that app, email us, message us. We will get back to you, I promise you. That is a distinct promise. Justine and I will get back to you. If you have any questions, you guys have our cards. This isn't a sales pitch. This is a community and a group who's working together to get to where we want to be at. And remember, every day, tell yourself that you believe in yourself. If that is hard for you, find us over at Toolshed Training. Thank you guys so much. Go to lunch.
Ooh, whoa. I about woke up a sweat in that. Javier put us through a good workout. I hope you at home were joining that with us. You can see this group here, everybody throwing arms in the air up and around and just getting loosened up, and great exercise. And again, that was Javier Tuel who joins us at this conference from Iowa. We appreciate his being here and loosening us up. As you know, it's about lunchtime here. We're going to move out to a quick lunch, and we're going to try to be back here by 1 o'clock Eastern Time. We've got a lot to get done this afternoon. We'll do the 50-50 drawing after we return. We've got a number of good speakers this afternoon who, some of them after having heard some of the discussions this morning, has slipped over to Norma and said, I may need a few extra minutes. And we're going to try to give them that, because while we're all here wanting to learn, wanting to hear all that we can about these diseases, possible research and treatments, we're certainly going to give them the minutes that they need to finish their presentations. And this morning, I heard a lot of good things, but the one thing that sticks with me most, Dr. Baas said, when he said a lot of researchers, a lot of folks believe that we might be able to find research that can halt the progression, but probably not to rehabilitate and rebuild and improve. And he paused and he said, but I don't buy that. And we don't buy that either. We got to continue this work, continue this collaboration with everyone across the board to find a way to make these lives better, to make our future better, those of our children and our grandchildren. So join us this afternoon. We will finish the afternoon with 2 messages from our senatorial people, our senator from Iowa and our senator from Minnesota, and they are very encouraging to hear and will make you feel good as we end this conference. So enjoy lunch. We'll be back around 1 o'clock, and we'll have a wonderful afternoon. So thanks. See you in about an hour.
Okay, everybody, thank you for coming back from lunch, and we're getting ready to start the second half of our day, and we've got some great presentations ahead of you. I want to do a couple things here first. I wanted to tell you something about the Spastic Paraplegia Foundation is proud to share that Christine Hendrickson, representing the SPF board and community, presented 2 Upper Motor Neuron Achievement Awards at this year's Northeast Amyotrophic Lateral Sclerosis, otherwise known as NEALS, annual meeting. The 7th Annual Upper Motor Neuron Achievement Award was given to 2 abstracts focusing on PLS and upper motor neuron research. Congratulations to Dr. Hande Ozdinler, with Northwest University, and Dr. Grace Qiang with Columbia University for being the 2025 UMN Achievement Award winners. And here's a quick note. Hold that applause. She has won since the beginning of these awards. This is her 7th consecutive win for her lab for getting this award. 7th consecutive win. That is so fantastic. And because of the great work that they've been doing at the NEALS conference in San Diego this December, there will be 2 presentations on their schedule of presenters focusing on PLS. A first time. This is a first time. That's a big deal, guys. Super big deal. Now, here we go. I would like to present Dr. Hande Ozdinler, Associate Professor at Northwestern University, is an innovator in motor neuron biology and neurodegeneration. Her lab's pioneering work on upper motor neuron vulnerability has brought critical insight into both ALS and PLS. Her collaborative and open science approach embodies the future of translational neuroscience. Dr. Ozdinler.
Thank you so much. What a great introduction. I'm
honored and humbled. Thank you so much. Yes, this will be the first year that ALS MND meeting will actually have an upper motor neuron and PLS and HSP session, an independent session within the ALS MND. And I think that's a very important and big deal. And our hope is to continue this and emphasize the importance of the upper motor neurons and upper motor neuron diseases within the large neuroscience community. And I'm very happy to give my presentation to you today. But before I talk about science, I want to thank our collaborators. Of course, Dr. Peter Baas, who has given us the spastic mouse model. I'm very thankful to him, and you watched his presentation. I think that's one of the best models for the spastin. Dr. Gerardo Morfin is helping us analyze the corticospinal tract aspect of it, and I have my long-term collaborator, Dr. Silverman, and I'm very happy that he will be actually giving a talk in this panel. And we worked together with him on drug discovery for upper motor neuron diseases. And Dr. Mukesh Gautam is here in the audience. He gave a talk yesterday. And to be honest with you, we told him, Mukesh, can you give a talk today? And you have only 2 hours to prepare those slides. He just had 2 hours to prepare those slides to you. And I think he has done an amazing job. And he has shown that he is already a diamond. I'm very thankful to people in my group. Of course, Dr. Quintanilla, Dr. Lupanar have contributed to this. But nothing really could be possible without the support that we actually have from people living with HSP and PLS. You are the driving force. You are the people who make the change. And I don't know if Hank is watching from home, but Hank actually introduced me to this family, and I'm forever thankful to him. He had events organized in near Chicago, and I attended those events. I became friends with people living with HSP, PLS. I became friends with the foundation, and once you become a friend, you are always friend. And I am very thankful to be with you today. And there's one person that I would like to highlight. It's actually Anne Gridley. And could you please stand up? Yes, I want everyone to know Anne. She is a remarkable person. She touched me in many ways. She was actually a visiting professor at Northwestern. Anne has HSP. She is also an actor, and she will have a show, a Broadway show, one-man show, and she wrote it herself. And the name of the show is Watch Me Walk. And we heard Dr. Fink this morning, watch them walk them walk, She is actually doing the show. Please take this QR code, learn more about it, find a way to support her, because she is going to bring HSP to Broadway. This is the most significant achievement that I think an HSP patient will achieve to bring awareness to the disease. So thank you so much, Anne. I'm happy to be your friend. And of course, all the people who fund our research, I am very happy to be funded by Spastic Paraplegia Foundation. I'm going to talk about the 2 grants that we have received and what kind of difference that made. And of course, in the future, what we would like to accomplish. In times like this, when an NIH grant is not always certain, foundations are extremely important to fund the initial aspects, the initial phases of research, and then you can get bigger grants, and then you can get more center grants. But if you don't foster those initial ideas, the early steps, then you can't really apply for big grants. So I want to thank the Spastic Paraplegia Foundation for allowing science to grow. Because if the science doesn't grow, we can't really have translational, innovative approaches. So thank you so much, Foundation, for bringing us together, for allowing science to grow. I'm very thankful to you. I'm also thankful to the Cure SPG4 Foundation. There were 2 mothers, supporting research. And I think families are extremely important because, you are touched by this disease. You know what it means. And then, you are also the driving force to make a difference. So thank you so much for that as well. In today's talk, I'm going to focus on 2 things. One of them is for drug discovery, and the other one is about gene therapy. Because we generate knowledge to develop translational efforts. And I think for translational efforts, one will come with small compounds for drug discovery, and the other one will come with gene therapy. So I'm going to focus on those two things, and we have made important progress for both of them. And first, I think spastin gene is an important one because not only that it's 40% of the patients have that mutation, but spastin as a protein is critically important. And, the mutations were detected, of course, in the patients. And now we know more about this protein, not only within the context of axon or microtubules dynamics and so forth. For example, we know that it's actually playing a role with ER and mitochondria. And you may remember from the opening talk how in the HSP the mitochondria is affected, ER is affected. So this mitochondria, ER, those two key organelles are extremely important for the health of motor neurons because mitochondria, among other things, generates ATP, the energy, and ER is where the proteins are made. And they communicate with each other all the time. And that their communication is also important for calcium homeostasis, for metabolites, for the homeostasis of the cell. And now many more work is showing that spastin is involved in multiple cellular events, like looking at the structure of the ER so that the ER actually is in many places in the cytoplasm, and also looking at the endosomal dynamics with lipid rafts. So the lipid is also important, and we see many in that TDP pathology. Now spastin plays a role in that, and endosomal trafficking with all these vesicles moving. So spastin has numerous other roles that we haven't thought about in the past. So that's why it is a very good target for developing therapies. And what we have done in our lab was actually to look for the spastin protein and look at the other proteins that the spastin interacts with. And that's also very important because proteins have different domains, and each domain is responsible for a different cellular function. Depending on where the mutation is, the protein may be more toxic, and I think that was also covered during the symposium. The location of the mutation is very important to see which cellular event is mostly affected. So then we actually performed the study to look at the binding partners of spastin and what that binding partner and protein-protein interaction would tell us about the role of spastin. So here are the domains of the spastin. You will see like orange, blue, green, red, right? And then we also did the AlphaFold analysis of the protein three-dimensional structures and the binding partners of spastin and which domain they interact with. Then we look more closely in each domain, and then we look at the canonical pathways, which means cellular events that are mostly associated with those. And you know that it's actually mainly clathrin-mediated endocytosis, vesicle transport, axonal transport, but there are many cellular events that are particularly involved with unique structures of the protein. So that's why, like, patients may say, I have mutation of the spastin gene. Well, where's your mutation? Because the location of the mutation also tells you how severe it is and what cellular event will be most affected. So that's why to better understand or to better associate the location of the mutation and the cellular pathology, we had to do this study. Then we looked at all the mutations that are detected in HSP and also PLS. Now, this is very interesting because there are 100 different genes mutated in HSP. Even though HSP is a rare disease, there are so many genes mutated. Why is that and how is that? Even though these genes or the proteins that are coded with those genes are very different, the clinical outcome is very similar. And why is that and how is that? So then we said, when a gene is mutated, it leads to a disease, that gene must code for a protein that is critically important for the health and the function of the upper motor neuron. And how do you determine your importance? You determine your importance by your connections. If you're always alone in the room, you may not have such an impact. But you're always talking to other people, you're attending the then you may have more impact. So proteins are like that too. Proteins bind to each other. Then we said, okay, whom do you bind to? All these genes that are mutated in the HSP patients, they code for a protein, and all those proteins have binding partners. They interact and bind to those proteins. Then we say, binding partners, binding partners. What do you do? What is the game that you like to play inside the cell? What is your primary function inside the cell? Then they begin to tell us, oh, I'm trying to make sure lipid homeostasis is okay, cytoarchitectural dynamics is okay, and I'm trying to reduce neuroimmune modulation. So they really play a game by this interaction. And then we went even more deep and say, all right, you told me lipid metabolism was enough, or was your game. Whom do you play that game with? Who are your binding partners? This information is very important to identify targets for future drug discovery efforts, because then you want to find targets to modulate these altered cellular events, okay? So that's why we have now gained a huge amount of information about what does the mutation mean and the location of the mutation mean, whom do they bind to, what cellular events they play, and so we begin to understand more about the spastin protein. And again, this shows that. So then I think we come to realize that spastin is more important than we think. It's not just actin-binding protein, severing protein. No. It has more than 50 important roles for the motor neuron. That's why when you have a single mutation, you basically develop a disease. It is a key and critically important protein. And then it has multiple roles, and it is a good target. But then how do we understand when the mutation hits what is really happening inside the cell at different stages of the disease? So as Mukesh was introducing you the upper motor neuron reporter line that we developed in the lab, this was a big deal at the time. We actually received $3.5 million from NIH at the time because this was the first reporter line that is specific to a cell type population within the motor cortex. Because there are many reporter lines, they are GFP, but it's a mixed population. They are GFP, but who are they? You don't know. And then with this reporter line, we knew that within the motor cortex, they are upper motor neurons. And as you can imagine, we now cross them with the spastin mice that was gifted to us by Dr. Baas. So in that case, we actually have fluorescent upper motor neurons that have the human spastin mutation. So then by doing this, by generating this reporter line, we are not studying mouse anymore. We are studying the neuron. And that is critically important because it shifts our attention from mice to neuron. And especially when you FACS purify them, which is fluorescence-activated cell sorting, it's a technology to purify neurons based on their fluorescence character. So then you can actually microdissect the motor cortex, apply fluorescence-activated cell sorting, so then you are not taking the whole motor cortex because it's very heterogeneous. You are purifying the neurons that die, the neurons that become vulnerable. So you are as precise as it can be. Then you do this at two different time points, P60, P90, postnatal day 60, postnatal day 90. P60 is a very, very early time point. They don't have any symptoms. They're just walking fine. It is pre-symptomatic. P90, still, early symptomatic maybe, but again, not full-fledged disease. So then you can actually isolate these neurons when they are vulnerable or when they are beginning to become vulnerable, like very, very early stage. Because we want to understand what makes them unhappy. Why are they vulnerable while other cells in the brain are just fine? So then we isolate the green fluorescent neurons by FACS. Then we actually perform proteomics, which means we look at the proteins that are present in those FACS-purified neurons. But this is like a very unique technology. We're talking about nanogram, femtogram protein levels, and then you do the proteomic analysis in those FACS-purified neurons. And as expected, the spastin protein is high in the spastin mice. then this comes up, that at P60, there are some genes that are upregulated, and at P90, there are some genes that are downregulated. So it is a very dynamic gene expression profile. And why would those genes be upregulated at P60? Why would they be like, what does this mean, right? Why there is this dynamic change? So we put that gene information into ingenuity pathway analysis to look at the canonical pathways, cellular events that are involved. And before we do that, we confirm that the genes that we find with this FACS purification is actually indeed expressed in upper motor neurons, and they are, so that's good. Then we say, all right, genes and genes that are upregulated at P60, what's up? Like, what's your game? Like, why are you up? You know, what's happening? And they tell us, oh, I'm trying to make sure that the TCA cycle is in check. You know, what is that? TCA cycle happens in the mitochondria. Oh, so are there some problems in the mitochondria? Like, why is that so? And then it says, oh, microautophagy, I have problems with microautophagy, you know. Early in the disease, there is no symptom, nothing, but the cell begins to speak to us with the proteins that is present in those specific cells. And they say, and then we say, all right, why do you tell me that this is upregulated or downregulated? It says, oh, look at all these genes, you know, I expect them to be up there really, like, you know. They even tell us which proteins within that domain are involved. Perfect. Then we say, all right, so for example, the microautophagy was involved, right? And why is that? Why is microautophagy comes up at the very beginning? And there are many ways that the cell begins to clear aggregated proteins. Microautophagy, macroautophagy, and then chaperone-mediated autophagy. There are three main pathways. And the microautophagy is usually like when the aggregations are small, you know, they can engulf it, and then they dissolve it, right? And we are talking about a very, very early stage in the disease. But even at that time, they start having problems with the microautophagy. And you might have seen the images that Dr. Gautam has shown. Later in the disease, you have these big aggregates, because I think the protein aggregation starts to become, begins to emerge very early. Then we say, all right, how about P90, which is like 30 days later, same cell. What's happening? And it says, RAP granulation. To be honest with you, I didn't know what that means when this came out. And it's basically a way of clearance of proteins, because those lysosomes must be attached to the autophagosome, like the images that Mukesh has shown. And if they are stuck or there's no good fusion or something, they get frozen and they never get cleared, and then you see more of those, right? And it seems as if that's what's happening. And now imagine we get this information by just isolating these neurons as a pure population and asking them what is the protein that they have. Then we said, okay, from P60 to P90, what is really happening? So they say, you know, Rho GTPases are very important for us, and which we know for spastin that's important. But then they say, for example, the organization of cytoskeleton, look at that, organization of cytoplasm, microtubule dynamics, axonogenesis, it becomes more important. Like P6, you know, P30, we were able to detect it. P60 and then P90, it's even more. So there is, you know, axonal problems coming up. They cannot maintain cytoarchitecture, actin problems. So, you know, this tells us. And then it says, oxidation of fatty acid, oxidation of lipids, they are potential problems with mitochondria. So looking at the proteins that they have, we begin to understand what could be the problem. And we have to understand this to develop therapies and drugs, because what is our target, right? What is our outcome measure? Then we say, all right, on the left-hand side, this is actually mitochondria observed. Like you can see one healthy mitochondria, relatively healthy, and beneath it is the unhealthy mitochondria. You can see that it's hollow inside. The inner mitochondrial membrane is broken. When it is like this, they can't really make ATP. And look, there are other examples from the spastin mouse model that mitochondria is affected. So then what we see with proteomic analysis is actually holding true when we look at the tissue. And again, all these aggregations like autophagosomes, right, in the spastin mice, and look, this is in the postmortem of human brain. So then if you focus your attention to the neurons, the upper motor neurons versus upper motor neurons, there's great translation. So then, we see the same problems in human brain and in human upper motor neuron and in a mouse upper motor neuron. And again, these mouse were generated by mutations detected in human patients. And ER is also, expanded, sometimes broken. You see all these ribosomes floating around, so there's a problem with ER, and you have more examples here. So then we know that there's protein aggregation problem, mitochondria problem, ER problem, and as Mukesh has showed you, there's also a corticospinal tract problem, as you would imagine. So now that we identify the problems and we know what to look for, we ask whether NU9 treatment improves the health of upper motor neurons that are diseased due to spastin. And why NU9? So this is based on the study that we published with Dr. Silverman, and Dr. Silverman is the inventor of NU9. It was discovered in his lab, and we had two key papers to show that NU9 actually helps with misfolded SOD1 and also helps with TDP pathology, two different protein problems, and that it works also in combination with other FDA-approved drugs, which is great. So based on this, we found, for example, that NU9 is pretty remarkable for its impact in improving the health of diseased upper motor neurons, and that was the first compound identified to improve the health of upper motor neurons. So then, Dr. Silverman is going to talk more about this, that we realized that protein aggregation is a common problem in many neurodegenerative diseases, even though different proteins aggregate, including ALS, FTD, Alzheimer's disease. And in collaboration with Dr. Klein, Dr. Silverman actually found that AKV9 or NU9 is also effective within the context of A-beta amyloid. I mean, can you imagine a compound can help with misfolded SOD1, TDP, and beta amyloid, like 3 different proteins? So it must be on the top of the food chain. So it doesn't care which protein. It must have a mechanistic approach to solve the protein aggregation problem, right? And that was the reason we actually received $7.3 million from NIH to further investigate NU9 within the context of neurodegenerative diseases, including ALS, FTD, and Alzheimer's disease. So now I'm also investigating it within the context of upper motor neuron disease in spastin. So when we treat mice, the spastin GFP mice, with NU9, look at this. This is 100-day treatment with 100 milligram per kilogram, and we didn't treat them Saturday and Sunday. It was only Monday to Friday. And the mitochondrial clumps or mitochondrial problems were significantly reduced, which is great because we know mitochondria is a problem. And then all these broken cristae of ER and ER getting really disintegrated and everything, and that was eliminated, which is very important. And as you know, ER and mitochondria is very important within the context of HSP. And I want to show, I don't know if I can, the videos. This is actually a video from a spastin CSMN. Maybe I should show the wild type first. In the wild type, you will see the mitochondria moving. Do you see? It's a 5-minute video. And here in the spastin, this is the same time, but you actually you don't see that much movement. Yeah, so in the spastin CSMN, there seems to be less axonal movement. And we quantified some of this, like the organelle transport using mitotrackers and so forth. So there seem to be defects within the disease, and it seems this is improving with NU9 treatment in culture. So these are all promising, and of course we need to increase the numbers for this. And that work was supported by the Spastic Paraplegia Foundation grant, so I'm very thankful. So then I think I want to leave you with the question that can NU9 be considered for the treatment of HSP? That is actually a very important and valid question. Because first we understand the molecular mechanism behind upper motor neuron degeneration using pure populations. We confirm it with EM using mouse models in human. And then we treat them and we look for the outcome measures that we characterized. And does NU9 reduce protein aggregation? Does it improve mitochondria ER? Does it reduce autophagy? And what are the outcome measures for upper motor neuron diseases? And could CERN clinical trial readiness program actually be aligned with this time-wise? It could be that all stars aligned, because we need to do some more work to get that ready. But in the meantime, the CERN platform is actually working to be clinical trial ready, and it may be that all stars align and we may start a clinical trial. So I'm very excited about this work. So now I'm going to switch to the second part, which is gene therapy for upper motor neurons, because not everyone has the spastin mutation. And then they feel left out, like, okay, I don't have the spastin mutation, then how about me? And it may be even a rare form of the rare disease, then what's going to happen to you? So gene therapy actually offers great opportunity for people with ultra-rare forms of HSP. And again, we received a grant from Spastic Paraplegia Foundation for developing directed gene delivery to upper motor neurons, and that was with Dr. Hatsopoulos at University of Chicago. And we have been working on gene therapy approaches to upper motor neurons for more than 10 years now, and I want to tell you, first we started with retrograde transduction, which means we introduced the virus to the corticospinal tract, and we want the virus to go all the way back from axon to the cell body, and that transfect the neurons in the cortex. So we published this work using different viruses, AAV2, 5, 6, 7, 9, we all tried different serotypes, different packages, and so forth. And we realized, 2.2 is more specific, 2.9 is transduction efficiency is higher, so we published it when, like 2000 something, but that was some time ago. And then we also tried direct motor cortex injection, not corticospinal tract injection, because the corticospinal tract in the mouse is in the dorsal funiculus, which is like very close to the top of the spinal cord. But in human, it's not on top of the spinal cord. You need to go really like lateral, the ventricle, to the, it's not on the top. You really have to go down, and you don't want corticospinal tract injection in your spinal cord to transduce your brain. You may get spinal cord injury. So that's not translational in human. So then we said, how about we develop direct motor cortex injection? And we worked on this, we published this work, and we looked at different serotypes and so forth. And the problem with direct motor cortex injection is that the injection area has a huge load of the virus, right? Because the area can have astrogliosis, microgliosis. The area where you inject is important. So you may actually be damaging the brain if you want. You want to help, but you may damage. The best would actually be through the bloodstream, but then there's blood-brain barrier. You cannot go into the brain. And it could be intrathecal injection. And we actually worked with a company, and I'm very happy about this. It was a Korean company, and they were developing HGF delivery as an impact for neuroimmune modulation. So they found us at one of those Niels meeting when we got the award, and they said, let's work together, and we published in Nature Gene Therapy. It even made it to the cover, that we realized that intrathecal injection could be a way to modulate gene expression in the motor cortex, and who would have thought that intrathecal injection could be useful? So that's one way of route of administration, but the blood-brain barrier would be much better. So then, okay, we can improve the route of administration, but what is it that we're going to change? So we found a gene, UCHL1. It is very important for the health of upper motor neurons, and we realized that this gene, UCHL1, when expressed in upper motor neurons that degenerate due to misfolded SOD1 or TDP, improves their health. Oh my God. Because it is a therapy that can be applied not only patients with UCHL1 mutation, but more broadly within the context of SOD and TDP. That's why this was very exciting at the time. It again made it to the cover of Nature Gene Therapy, and Clive Svensson actually wrote a review about it. when Dr. Clive Svensson writes a review about your paper, that means you did a good thing, okay? So, and he says getting the upper hand in ALS, which means the cortical component is really very important. And then UCHL1 then emerged as a potential target for gene delivery for a broad perspective of patients with upper motor neuron loss. So now we have a target. We're also working different routes of administration. We also improve the serotype and the plasmids. This again shows that with UCHL1, you can improve the integrity of both the SOD and the T. This is the other model. And that you also reduce protein aggregation both in the SOD and TDP. So this was actually a very nice paper. I suggested you read it. And as we were working on this, our collaborators, especially Darius at MGH, began clinical trials with gene therapy to the upper motor neurons. This was a remarkable publication at the time that gene therapy begins to emerge as a potential therapeutics for upper motor neuron disease patients. But then there are some limitations. And the limitation is mainly the blood-brain barrier. Because the virus does not cross the blood-brain barrier, you have to give a bit high dose so that maybe some of it will pass the blood-brain barrier. But because you give high dose, then you increase the chance of target effects, which means liver, this, that, other organs, they're going to be exposed to the virus. Like, so you are targeting the brain, but what other cells and organs are also getting the virus, right? So you want to use the minimum virus and most directed to the motor cortex without affecting other cells, other tissues, or other organs in the cell. You need specificity, precision, and you need effectiveness. So that is the challenge with gene therapy. Because again, as I said, the blood-brain barrier is good for us as a defense system, but when we are using viral treatments or virus treatments for gene therapy, then it's a barrier. So we have to develop a way where we can open the blood-brain barrier just a little bit, like 5 minutes, 10 minutes, okay? And right on the motor cortex, so that it's not open anywhere in the brain, just in the motor cortex. For 5-10 minutes, you give the virus to the bloodstream, you open the motor cortex blood-brain barrier, 5-10 minutes, the virus goes into the brain, it closes. Then you don't affect other regions of the brain, you don't give high dose, and if this technology is improved, we are going to be safer with our gene therapy approaches, especially for little kids. This is very important. We need to be more specific, more effective, and then once you give the gene, you cannot ungive it, right? So you can fix a problem now, but you may be creating a problem 30 years later, like you don't know. So then we need to have long-term and effective treatment strategies. That's why I think this technology is so important and novel. This is using ultrasound, okay, to open the blood-brain barrier for a limited time. And there are now papers, many papers published about this, that you can actually disrupt the blood-brain barrier with pulsed ultrasound, and then boom, it's open, and then boom, it's closed, like it's done. And yes, that's actually used for Alzheimer's. Now it's used for ALS mouse models in the spinal cord. And now it could be an emerging therapeutic strategy for neurodegenerative diseases, especially where brain cells are affected. And I'm so happy to tell you that there is a company who does this, Carthera, and they are in phase 3 clinical trials for glioblastoma tumors in the brain. Because imagine that in the brain there's a tumor, it's very local, right? And you want to deliver the therapeutics where the tumor is, but it's very hard to do the surgery, blah, blah, blah. So you put a probe where the tumor is, and you give the drug to your bloodstream, you do the ultrasound, the drug goes where the tumor is, and then boom, it's closed, and then now you have very effective and selective treatment towards the tumor. They passed phase 1, so it's safe. They passed phase 2, so it's efficacious. Now doing phase 3 at Northwestern. I said, oh my God, can we meet? Can we talk? Can we work together? And after our first meeting, they said, Hande, we want to work with you. I love it. So then they came all the way from Europe. They sent me that machine. It was like $300,000 machine. They gave me for free. They built it in our lab, and they also sent people from Switzerland to train us. We are so happy. And we started doing those experiments together with Cartera. And look at this. I want you to focus on the brain, the mouse brains on the right. Do you see that blue area? It's directed delivery to the motor cortex, but not on the other side. So we can actually play, depending on where we put the probe, we can guide like where we want to open the blood-brain barrier. And we give very little virus into the bloodstream, okay? So you open, you pulse it, boom, it's closed, and the virus is in the brain. So you give those micro bubbles, and micro bubbles with the ultrasound opens the blood-brain barrier for like 10 minutes, but you should see us doing those surgeries, like timed, okay, the moment you open, okay, open, go, do, like with 10 minutes done. You know, like time is the essence, and I love those experiments. And look at this, like we were able to get very directed in the motor cortex, then we section them, and look at this, the ipsilateral, meaning like where you see the blue, there's anti-IgG, which means the blood vessel was open, that we can actually see the opening right in that. But if you look at the other side of the cortex, look, it's blue, there's nothing. And if you do a no treatment, it's like no treatment. So we are not affecting the whole brain, we are very precisely affecting where we want to affect. So I think this technology, when developed, would be very useful, and especially now that Cartera is a company that is already in phase 3. When we talk to them, they say, Hande, we want to go to HSP patients, we want to go ALS patients, we want to go upper motor neuron disease patients, and we already have approved phase 1, we already have approved phase 2. If you tell us which genes, if patients have different genes, we can have the constructs, and you know, they are so willing to work this for the gene therapy for upper motor neuron patients. And now, you know, working with them, hopefully we will be able to develop this technology such that it is feasible, it is possible, it is it is not toxic, and you know, we can get the genes to the neurons in need. And that's why I was asking Dr. Baas the question, which virus vector do you use, which promoter do you use, how selectivity do you want? But I mean, we have figured it out for the past 10 years. We have looked at this promoter, that, I mean, we already, and thanks to the support that we got from the foundation, now we need to optimize this. So that's also coming in line, because as the CERN develops their platform, I think with this new technology and with the company involved, it will be a win-win for everyone. So then, with this, it will be more directed and improved gene delivery. You don't want dirty gene delivery. You want the genes of interest to go into the neurons of interest and nowhere else. You want it as clean as possible, as effective as possible, because you don't want, to fix something and then to destroy 10 other things, right? So then this will also allow personalized gene therapy approaches, because you can have the virals and the vectors and everything designed for you, for that particular neuron, and for that particular mutation. And I think that's possible. So then I think this will increase the success rate in clinical trials, and I think this is definitely within reach. So in summary, I can tell that we obtain the information by using pure populations of upper motor neurons, and I think that's the key, that we don't use the full mixture of the brain. And then by using pure neurons that degenerate, they begin to speak to us at a molecular level, and they tell us what are the problems that they're facing with. And then this helps us generate outcome measures for preclinical studies. And in my opinion, NU9 could be important within the context of spastin and HSP as well. On another context, the gene therapy approaches, I think, needs to move in parallel, because you may not have drugs for everyone. Some patients could be more unique and they could be more rare. And then we can actually develop personalized approaches for them, again, developing the safest and most effective gene therapy approaches. And the Cartera technology, I think, can be transformative. So I really believe that there is a future, bright future ahead. And maybe this is the 4th time that I'm attending this meeting, and I've been telling people that this is the most transformative symposium that I have attended. Previously, people were talking about, individual science projects that they have done, but now we are more geared towards translation, more geared towards effective treatments, and I'm very optimistic and I'm very happy to be with you. As a final note, some of the speakers talked about ASOs, remember, antisense oligonucleotides? I haven't talked about them in my talk, but antisense oligonucleotides are very important for neurodegenerative diseases. And please register to our upcoming Les Turner Symposium on ALS, because Dr. Don Cleveland will be our keynote speaker, and he is the one who discovered the ASO technology. In my opinion, he may get a Nobel Prize, because ASOs have been a treatment strategy for ALS. Now they're also using it for any mutations, any different diseases. So ASO technology could also be applicable for HSP and PLS patients. And please register. There is an online version. It is free. And the neurodegeneration community, when we get together, I think we will make a change. So thank you so much for your attention. I'm ready to take questions.
Okay, Doc. Okay, who would like to ask a question? Okay, that's great science, by the way. It's okay. It's okay. First of all, isn't this cool? I mean, isn't this cool stuff? This is transformative. This is really impressive stuff. Well, doctor, everybody, they understand everything. We're going to quiz them later.
There's a question. There's a question. There are questions.
No, wait a no. Wait a second.
Hold on.
Injecting a virus.
I can't hear you.
When you talk about opening the blood-brain barrier and injecting a virus to that specific part of the brain, how do you prevent it from migrating? Aren't viruses by nature something that spread quickly to everything around them?
Yeah, I can explain. So we tried multiple routes of administration: corticospinal tract, direct cortex injection, intrathecal, and blood to the tail vein, infraorbital. We tried multiple routes of administration. So what happens is when you give a virus to the bloodstream, because blood circulates, right? So if you fill your bloodstream with viruses, they go to every organ, they go to everywhere. But they don't go to the brain because of the blood-brain barrier. But our goal is to make the virus go to the brain and not to the peripheral organs. Like, it is just the opposite of what's happening. When you give patients the virus to their blood, your kidney may be transduced more than your brain, but you want your brain, not your kidney. So then we realized that when you actually give blood to the bloodstream, right, and it comes, but you give low amounts, okay? So that when it comes to the brain, blood-brain barrier, it's like you open the door, right? You open the door, but only this door, so they can only go to this room. So when that door is open, because it's already in the system, whoop, they go into that room, and then boom, you close, and then they get trapped in that room, right? So that's our goal. We direct them where we want them to go by ultrasound. So ultrasound is like opening the door. We want them to go to the motor cortex, so we put the probe on top of the motor cortex, and the virus would go there. And then you close the door, and that's it.
Great. Can you go back one page for your QR code that people want to take? Thank you.
I'm sorry. Yes.
We'll leave that up. Another question in the back right.
The question you had about the virus, I don't think he understood. It's not a replicating virus. He's thinking the virus, will...
Oh, I am sorry. Yes, the virus is a non-replicating virus. They won't replicate and enlarge. So in a viral genome, there are genes that would allow viruses to replicate. So these are engineered viruses that we take the replication genes out, so we only use them as a delivery method.
Okay, one more question. Do we have anybody? One more.
So this is actually a grant that we have written recently. So crossing fingers.
Okay, I think we got it. We're moving on. Thank you, guys.
Thank you.
Dr. Ozdinler. Okay, everybody, thank you for being so patient with us today. This is the point that you've been waiting for. But first, if any of you had made a pledge last night during our fantastic end of show last night and have not yet seen Linda out at the front desk to confirm your pledge that you made, you all know who you are. Okay, you know who you are, and if you've completed all the parts you need to do, make sure you see Linda. She's standing at the door. So before you leave today, make sure you check in with her. Hey, and also, we've got some t-shirts out front, some smalls and mediums that if you're interested in, if you'd like to have one of those, we're giving those away, okay? I used to wear a small, then it went to a medium, to a large, extra large, trying to stop there. So anyway, but if you have somebody who can wear those, we'd be more than happy to give those away, okay? All right, so this is what we're going to do now. We are picking for the 50-50, and that winning ticket will then be re-entered back in for the $200 Cadence gift card, okay? So I'm going to do it, and so I'm digging. Oh, the total, what's our total?
The winner would get $545. So
you guys did over $1,000. So thank you very much for contributing that to the foundation. We both have allergies. Okay, she's got it worse than I do. Okay, I'm sorry, and it's going to take a while because you guys really stepped up. Okay, you bought a gazillion tickets, and there's a bunch in here, and you got strips all over the place. I'm mixing. Okay, golly, the tension in this room was incredible. My gosh, my goodness gracious. I'm telling you, I'm really mixing, I swear you. There's nothing taped to the bottom, I promise. Okay? All right, here we go. I'm mixing. This is it. This is the one. I'm going to read the number about 400 times. Here we go. Okay. Here we go. This is our ticket for the 50-50. 480836. I know it's going to take a little while. 480836. 480836. You guys did so well, we had to start with a second roll of tickets. Okay, here we go again. I know it's going to take a while. It's all right. 480836. Oh my gosh, there's a hand. Here, Mary Kay, go check on that. We're going to confirm that first. You know, I love you, but, you know, just check, just in case. And then we're going to bring that ticket back and make sure that it's re-entered for the other event. We have a winner. Nice, cold, hard cash, real cash. Thank you, everybody. Okay, we're bringing that ticket back. We're going to mix it back up, and we're going to pull for our Cadence gift card. Let Mary Kay do that. Mary Kay's doing that. I'm just helping her virtually. Wait a second. Oh my goodness, we have a donation back to the foundation. Whoa, thank you very, very much. Oh my goodness gracious. We thank you very much, and thank you guys for participating in this. It's a fun thing to do, and we're so grateful. You guys you saw Dr. Ozdinler. This is where this goes. This is what great stuff is. Okay, we're pulling for the Cadence gift card. Mary Kay, that's you. You get to pull it, and you get to read it.
480710. 480-710. 480-710. 480-710. 480-710.
Well, okay. It's okay. Mary Kay, do your holy smokes. Well, 480-710. Well, that's okay. Hey, in the long run, we did okay. Yeah, Mary Kay, go check that. Just in case. I think I now know the system. You buy the whole row, it works, everybody wins. Mm-hmm. All right. Thank you, Mary Kay. Everybody's going to be in this picture, okay? Don't worry about it. At the rate it's going, we're all going to be in this picture. Why am I quiet? It's okay. We're going. All right, we're getting the shot over there while this is going on. Okay, we're going to move on to our next presentation here in just a couple of seconds. I'm watching Rick in the back, and we're going to get this picture. Fantastic. Congratulations, guys. Thanks for participating in our 50-50 raffle. This is good. So now we're moving on. Here we go. Dr. Oscar Qiang of Drexel University is advancing preclinical research into axonal protection and neurodegeneration. Working closely with Dr. Baas, his studies explore how microtubule stabilizing agents might slow or even stop disease progression in HSP and PLS. Doctor, you're on.
Hello? Oh, it is on. This is my third meeting of SPF. Every single time I came here, I got pumped and I want to go back and do more research to this field. I really cherish the projects going on in my lab for HSP, SPG4, and now we're moving towards more HSP forms. I'm very excited with the collaborations with other scientists around the world, actually. Today, my talk is a little bit tweaked because you guys probably heard a lot about animal models, and I swear I'm not going to do too many animal models in my talk. Mainly, I'm doing stem cell research in my lab at the moment, and I want to introduce you guys to this kind of patient-derived models or human models that you can use for experiment approaches. I think it is really a revolutionary milestone for the biomedical research in several decades, and even won 2012 Nobel Prize for this technology. So my talk today is from human stem cell-based motor cortical organoids to preclinical therapeutic testing for HSP. I have no conflict of interest for this presentation. So first of all, what are the stem cells? I think you guys heard from yesterday, even today, a lot of people were talking about iPS cells and human stem cells. I would like to kind of give you guys an overview of what are we talking about, because a lot of people are talking about stem cells, sounds so cool, but what are they? particular stem cells I think a lot of people, scientists, referred from yesterday to today is pluripotent stem cells. What is pluripotent stem cells? I'm thinking about these type of stem cells will give rise to every cell types in your body, from your skin cells to your heart cells to your kidney cells, the lung cells, as well as the brain cells. So this is pluripotent means like, you just have almighty differentiation sort of capacity to become any type of somatic cells in your body. So years ago, actually before the 2000, in the stem cell field, people always believe when you have stem cells differentiate into somatic cells, for example, you have skin cells or you have your lung cells, there's no way to come back. For example, everybody sitting here for 20 years ago, you never thought about you can go back to your embryonic stage, right? All the cells in your body. However, the dogma is changed. And that's what I'm talking about earlier about the 2012 Nobel Prize winning is the cellular reprogramming. So what I mean reprogramming is to put your somatic cells, which is terminally differentiated cells, back to your embryonic stage. So then you can have your own stem cells and differentiate into any type of the cells in the body. And so this really is, in my opinion, one of the greatest milestone or breakthrough in the biomedical research. So what we talked about, iPS cells and induced pluripotent stem cells, are those cells. And I'm going to talk about how do you use these cells to do the research a little bit. So we love animal models, and the field, any type of field benefit from generating animal models, especially rodent models, to study a disease, no matter whether it's a CNS disease or a central nervous system disease or any type of the organ-specific disease we have. The animal models are so useful. However, there is an inevitable hurdles and limitations for animal models. First of all, it's very costly, so you have to spend a lot of money to generate models, and to keep for example, the mouse colonies or rat colonies. They're very time-consuming to, do the research with them. You have to generate the models, take 6 months probably to 8 months to start, and then you kind of you need to characterize these mouse models or rat models, and then really start doing the research probably it's like 1 year to 2 years later. And then also, there is an intrinsic genetic and physiological difference between animals and human. As Dr. Blackstone yesterday was saying, mouse are not SPG4, right? Even though you have the mouse models, but it's not mouse don't develop SPG4 or HSP. The third thing is a lot of studies in the mouse models, and he touched a little bit about that yesterday. Depends on the model you're studying. There is a good amount of the clinical trials failed, almost more than 90%. I mean, can you believe that? 90% of the chance that works in the animals won't work in human. So the animal models have these kind of the gap between its translational value. So that really also is a concern. The last but not the least, I think is really important is how many people here are HSP and PLS without known genetic mutations? If you can raise your hand. Right. A lot of people in this population or in this audience don't even have known mutations. How do you use animal models to model this disease? Because you don't have a targeted genes to mutate it and to model the disease. So the animal models is almost useless to study sporadic disease, which is not known genetic mutations. And that's why we should use human stem cells. So first of all, like I just said, in sporadic disease, you can take the patient's cells and reprogram into the embryonic stage. Now you have your own models to develop into neurons or to develop into what we're going to talk about a little bit, organoids to study the disease. And then also in the HSP and PLS field, particularly, there is a very limited post-mortem human brain tissues to study, the human histology and any type of the biochemical analysis using human tissue. So that's another way to get to the human tissue by using the stem cell technology. the next two ones are really useful in terms of like, you can actually study your specific disease. That's called personalized medicine or the precision medicine. You can screen for drugs with your own sort of the cells, or, we want relevant cells, which is the brain cells, right? So you can develop these cells from this, your own human, your own stem cells, and then differentiate into the cell types you want to study. So what are we going to use? Now we have this kind of reprogrammed embryonic stem cells, HIPSCs, or human-induced pluripotent stem cells. I'm going to be short for HIPSCs. So how do you use this for HSP and PLS studies? So for 10 years in my lab, we developed this called organoids. And then recently, we're really patenting or differentiating these organoids and drive them into the motor cortical region, and we call this motor cortical organoids. So what are the organoids? The organoids are miniature brain tissues, and that are like small and brain-like structures. It's containing essential brain cells, and not only the nerve cells and neurons in there, but also supporting cells such as glial cells, and we're also getting the blood vessel cells and microglia cells and astrocytes into, so it's a mixed culture, not just the neurons in there, and it's very orderly, organized, and then very complex structures, not just like you culture them on the 2D, which you guys are seeing those cultures in the 2D platform. So it's the 3D miniature-like structures. So in my lab, we have two different strategies to do the HIPS reprogramming. So we either can get the patient cells, which we're obtaining some of the fibroblasts from different resources, and then we can reprogram using our technology established in the lab into the HIPSCs, and those are patient-derived cells. So can realize the personalized medicine. The other strategy here, it's a very unique, is because, if we want to study a disease, a mutation, you want to have the perfect control. In rodents models and mouse models or rat models, it's easy to do because these rodents are inbred, so they have the same genetic background. So if you have control and you have a mutation, it's only the mutations in there. But in human, every one of us sitting here, our genome is very different from each other. How do you know the phenotype you're seeing is from the spastin or from other gene, HSP or PLS gene mutations, instead of your variations in the genome? So by doing CRISPR, we can actually turn your mutation into a control, a healthy one, so that you have a perfect control to study your gene mutation-specific cellular phenotype. The other way around, you can introduce a mutation into a healthy donor cells to see whether that mutation can actually lead to the disease phenotype, so vice versa. So there are two ways to do, we call this isogenic, because you have only the mutation difference between these two cell lines. And here is the models, and those are really pretty pictures of the organoids and doing by immunofluorescence. And basically what you see in the rolling is our bioreactors, or anti-gravity or gravity against sort of bioreactors, and you can grow those small little, you can see the little ball-like things in there. We call these organoids, and these are the tissue engineering. And then we can section these tissues into just like human histology, and then these are immunostaining showing these organoids are containing some of the early development of the neuroprogenitor cells. Also, when wait for longer, for example, 3 months and 6 months longer, we can get into the mature neurons as well as astrocytes. And what I'm showing here is I want to highlight some of the markers we use. For example, CTIP2, I don't know whether you guys can see that, it's kind of small, but also the L1-CAM, they're both upper motor neuron specific markers in there. So you can see our organoids contain upper motor neurons with a good big population in there. So we have the good characterization of our organoid system. Now we want to see whether these organoids are actually functional. So what we do is we can either stain the synaptic markers to see whether these neurons or nerve cells in the organoids make connections, and then we do. And here is the synaptic marker synaptophysing showing that they can make connections with each other. And also we put these organoids on the device called a multi-electrode array system, so you can record neuronal activities, because we all know nerves. How does nerve cell work? They transmit electric signals down to your muscle, and then you can relax or you, contract or flex your muscle. So that's the functional readout we can read from the organoid development. We put the organoids on this little device here, and then you can have those black dots you see here are the electrodes. You are recording the electric activity of these neurons, and then the lower panel to the left are the raster plot. We see in this activities in each electrode. You can record these activities close to this electrode, and then we can analyze that. I'm not going to bore you guys with a lot of detailed analysis. We're doing the lab, so you can see spikes, the frequencies of spikes, and as well as the duration of the spikes. That tells you how active your neurons are or how deactivated your neurons are. So we also kind of want to make sure what we're getting into the cortical region is motor cortex. So it's a technology called single-cell RNA sequencing. So I'm not going to go into the technology into too details because it's a very newly developed technology. A lot of people are using. It's a sequencing on one cell with a lot of mRNAs in there, and then they can pinpoint what type of the cells you have, as well as what are the phenotypes of cells based on the RNA profiles or transcriptomics we were talking about. These are the single-cell RNA sequencing. We were doing the flow charts. We dissociate the organoids, making the single cell and going through the machine we call 10x genomics machine, and then we can sequencing on one single cell, barcoding them, and then we know where the RNAs come from, the one cells. And here are the UMAP, we call this, is just to see how many clusters of the cells, different types of cells we have in the motor cortical organoids, and we can clearly see the green bar graph, the green one, the CSMN, is the cortical spinal motor neurons, and we have a good population of that. But not only the cortical spinal motor neuron, just like our motor cortex, it contains other cell types too. You have, some of the astrocytes, which is the glial cells, supporting cells in motor cortex. You also have some of the inhibitory cells. So these are the satellite cells, probably, kind of make connections with motor neurons in the motor cortex as well. And then, these are what we characterize our motor cortical organoids and make sure that we're getting to the region specificity. And then we also did qPCR. Now, those are the high throughput sequencing data. We want to confirm is actually we are getting to motor cortical regions. Those are the 4 factors we collected, from different research papers and then characterized in our motor cortical organoids. And you can see the purple bars are just generic cortex, but the teal bars are the motor cortex we're trying to develop to. You can see these markers supposed to be more highly expressed in the motor cortical region is actually more highly expressed in the motor cortical organoids, which confirm that we're having the regional specificity here. So here are the projects I have with HSP in my lab. There are a lot of them. I won't be able to get into the details for all of them, but I do want to talk the 2 really major projects we have in the lab for SPG4 today. So as a lot of people from yesterday and this morning talked about, the common clinical manifestation of, for example, HSP and SPG4, but there also, people didn't probably talk too much about is the different genotypes of SPG4. For example, spastic mutation, they have different types. You have a missense mutation, which is just one nucleotide difference and change the whole protein sequence, change one nucleotide or change the one amino acids in your protein sequence. That's called missense mutation. You also have truncation truncation mutation, which means your protein get trunked into half or cut into half. So you also have frame shift mutation. That means like, your protein is totally different. So there is clinical data showing there is a genotype phenotype, which means different genotypes showing different phenotypes in the SPG4 or other HSP forms. And then my lab is like, we have this kind of CRISPR technology. We really want to study whether there is any genotype phenotype difference we can recapitulate to explain some people will have more severe symptoms versus the other people probably have less severe symptoms, even though you have the same disease. So we create the iPS cells from a healthy donor, and because we want to do isogenic, so we introduce using CRISPR-Cas 2 different types of mutations on spastin, which is SPG4. One is called truncated mutation, which means spastin becomes half of the size. And then the other one is called missense mutation, which means that only one amino acid difference from the wild type or the control, healthy spastin. And we make organoids, motor cortical organoids on that. It really took us a surprise when we characterize the phenotype, genotype difference. And this is all recent data we're showing. We didn't expect it to see the truncated version, which you have half size of spastin, the mRNA will be still the full length. And it took us a surprise, and I kind of disagreed with the field was thinking if you have a truncated spastin, you have truncated mRNA. It doesn't. It have the full-length mRNA. It's actually against the theory of the nonsense RNA decay. So it means a truncated version of the spastin does not mean you have no spastin in your brain or in your body. So that's the mRNA showing the red bar and the teal bar. You can see both of them, the truncated one's the red bar, the teal bar is missense. Both of them have the full-length mRNA way higher than the healthy ones here. And then we look at the protein level, we do see it within the protein, you also see there is a difference. So obviously the truncated one in the protein, because it's truncated on the translation level, you have half of the, or reduced level of the full-length spastin, which is not the case with the missense, because missense has more spastin in there. So, and which really took us a surprise, which is really surprising, is the truncated one. You can see in the middle lane, you can see on the bottom of the blot, there is a very small fented band of the truncated version of the spastin, which really is actually the first time we see in the truncation mutation in spastin work. So that's the first genotype-phenotype difference between the truncation and the missense. And then we look at the upper motor neurons in the organoids, and then at 3 months old, we can see the beautiful staining for CTIP2 labels upper motor neurons. I don't have to tell you guys, when you look at the pictures, all the way to the right are the missense mutation. The motor neurons are rapidly dying. So you can see the CTIP2 is bursted out. It's supposed to be in the nucleus, but it's bursted out into the cytosol. And these cells are in the way to apoptosis or necrosis. So, I mean, we'll quantify that. There is nothing that dramatic in the truncated version of the organoid system. The other genotype-phenotype difference is we look at the axonal degeneration. Here, I want you guys to focus on the lower panel. Forget about the green colors, because those are loading controls for us to see you have the same cells to amount of the cells to analyze. But if you look at the red color, you can easily see there is a genotype-phenotype difference between on the 3 months and the 6 months developed organoids. The truncated version of this SPG4 that develops slower than the missense mutation, and marked by the red. The more red it is, the more degenerated that is. And also we see a flipped the neuronal activities of the organoids. Compare the truncated version with the missense. You can see at the 3 months, you have lower activities of the truncated version, but higher activity of missense. And it was flipped at 6 months. So it's another phenotype, genotype difference. So this is, like we look at the different aspects of the histology level and the activity level of the phenotype, genotype difference. And now we have these models and showing the deficits of, degeneration and deficits in the cellular level. Can we test it for drugs. So we actually are, based on our previous study, we're testing HDAC6 as the druggable targets for SPG4 in my lab. And these are based on the previous publications we have and with other groups in the world that the microtubule hypoacetylation, which is the lower acetylation of the microtubule, is a culprit of the SPG4. And then we actually recapitulate here. So this is the HDAC, this is microtubule acetylation level. You can see in SPG4 is lower. And we contribute that why is it lower is because of the HDAC6, which is histone deacetylase 6. That is the enzyme that deacetylated microtubules and make microtubules less acetylated. And then you can see, as we expected in the animal models, there's increase of HDAC6 activities. So that tells us HDAC6 is a good target for us to do therapies on. So I was thinking this morning, how do I explain this really detailed mechanism to you guys, because I don't want to use a lot of jargons, here for people to understand what I'm talking about. But thinking about microtubules as railways, right? Like you have Amtrak and other trains go up and forth. Because I'm from Philly, so thinking about Philly is your upper motor neuron where the motor cortical region is, and then the spinal cord, the lower motor neuron, is your DCA region. So there are railways connecting between these, and the microtubules are the railways, act like railways in the neurons like this. So there are cargoes and the vesicles moving on the microtubules. But there are a lot of enzymes, other players that controls the railway. So for example, the railway can have a sign on it to say don't move, or to have a more smooth ways for you to move these cargoes and things. I think HDAC6 is actually put labels on these microtubules to say, hey, when the microtubule is more acidylated or less acidylated, then you can control the microtubule dynamics or to control the cargoes move along the microtubules. That means your train is going good or get blocked. So it's really important to have a balance of the microtubule with the different modifications. And here is, I'm talking about acetylation. So add an acetyl group to one of the amino acids on the tubulin subunits. And HDAC6 is actually remove that acetyl group onto that. So when HDAC6 is hyperactive, they remove a lot of signs from it. Now the microtubules, like railways, ask workers to come here to move those trails, and then your cargoes are not going to move very smoothly and good. So in your neurons, and things need to be transported in the distant region, won't even get to that. So that's really what it's doing in the neurons for the HDAC6 related to microtubules. So actually in SPG4, we find HDAC6 is hyperactivate. And then that's actually seen in other disease, for example, the AD, Alzheimer's disease, Parkinson's disease, as well as ALS as well. And then that's why we really want to inhibit HDAC6, because we see there is hyperactivities. And we use a drug called tubistatin A, which is a highly specified the HDAC6 inhibitor, and then it's actually blood-brain barrier permeable, and then it has been tested in other disease as well. So what we do is we put this drug into organoids, and then with a specific concentration for 3 days, and then we actually can see that there is still a genotype-phenotype difference in HDAC6, consistent with what we were seeing before. The missense is way more toxic than the truncated ones, and we can really reverse or rescue the hyperactivities with the tubistatin A. And what's really exciting is this treatment, you can see here, again, focus on the right part of the green, the red. You can see the red top panel is healthy. You can see the microtubule is healthily acetylated, but in those two missense and the truncated version of the organoids, the microtubule acetylation becomes lower. And we treat it with tubistatin A, it rescues the microtubule acetylation. What about degeneration? Now you rescue the microtubules. What about the degenerate phenotypes? Can you reverse that? And we actually, now we look at the red, is SMI32, which is a dephosphorylated neurofilament that labels the degenerative axons. You can easily see that SMI32 is hyperactive or is highly expressed in those two mutant organoids, but when we treat it with tubistatin A, it also rescues the phenotype. So I talked to you guys, these are those isogenic lines we're generating. What about the patient lines? This is really recent data we generated because we received 3 different R499H lines, which, it's really cool because they're the same mutation, but from 3 different individuals. And we're testing the HDAC6 activities in these patient lines. Now it's not CRISPR edited, it's just the patient lines. What you can see here, there's a discrepancy between one line we have, the same mutations. You can see one is called this is labeled 289 line, and then the other one's 320 line. One line is hyperactive HDAC6, the other one is not. We're doing more research on if you keep that longer, develop for a longer time, does it catch up for the 280? Both of them are symptomatic SPG4, and they're actually pretty severe type of SPG4. But you can see there is still a inconsistency between the cellular phenotype between these 2 lines. So we actually, I'm going to go through it very briefly. We put the HDAC6 inhibitor tubistatin A into animals, and these are our animal treatment regimen with the different arms, 4 different arms here, and then treated for 1 week tubistatin with IP injections. And what we see here is we actually rescue the phenotype of the microtubule acetylation as well as the HDAC6 activity, reversed it back to normal. And then we use the similar behavior test John showed this morning with the catwalk and when the rodents going through the calendars, and then they actually have, not going through one by one, they just to take my words, they're actually improved the gait deficiency in these SPG4 mice for this tubistatin A treatment. Next one we want to see, what about histology? So does this treatment change the behavior? Does it have the anatomic changes? And we also find the treatment of SPG4, treatment of tubistatin tubistatin A on SPG4 animal actually reversed the axon degeneration phenotype in animals, which we did a cross-section to look at the axon numbers as well as axon swelling. We characterized as one of the characterizations or features with the animals, SPG4 animals. So all of these work, if you guys want to know more, it's deposited in bioRxiv, and it's under revision right now for a peer review. We hope it will be submit our revision by next month, and hopefully it will be accepted soon. So we're really excited to see the small compound is actually effective for SPG4 for 2 different mutations at least. We'll keep you guys updated. I will email Norma when it's accepted. But if you guys want to read more, this is the paper in bioRxiv with more details and more quantifications in there. I do want to talk about other projects, but in very brief, I asked Norma to give me 5 more minutes because those are really important, exciting things we're having in the lab. And this one is a collaboration with Unravel. Dr. Novak is going to come up later to talk about the collaboration between us. We're repurposing an FDA-approved drug, which is NOT6 HDAC inhibitors, and they're actually very generous to send us those compounds. We tested in organoids, and we had really interesting data. He's going to present it a little bit. I think it's really exciting because the drug is FDA approved, and technically you can ask your neurologist and negotiate with them to see whether they can prescribe it with a low dose to start with. So I'm not going to spend time on that. But I do want to talk about one project we submitted to SPF Foundation to the grant is combination therapies. We heard a lot about different therapy, gene therapy, small compound, exercise. I think in my personal opinion, is the combination therapies probably is the best suit for SPG4 or for HSP and PLS treatment, because I don't believe one treatment can get like a silver bullet to hit everything. So what we actually propose to do is we adapt some of the knowledge from the spinal cord injury group, because I have a lot of collaborators at Drexel and collaborators in Kentucky. They're doing treatment for axon regeneration, right? When you have an injury, you want axon to regenerate, because axon is almost impossible to regenerate without any help in adults. So we focusing on the molecules called P10. That's the molecules intrinsically inhibit your axons to grow. So we find out it's really interesting when we use tubistatin A in the animals, the rescue is very moderate, but why? So we find out the P10 is actually activated. So whatever its boost axons to regenerate is actually inhibited with the tubistatin A treatment. So we really need to go in there to, for example, using vorinostat, which we are collaborating with Unravel, and then to combine with another compound that boosts of endogenous or intrinsic regeneration capacity to make the axons to grow again. And then combine with exercise, then the axons can go to the right target, as Dr. Baas was talking about this morning. Then we, with the 3 treatment addressing the degeneration in SPG4, and promote your own neurons to grow better, and then to exercise for the neuron to send the nerves to the right target, I think that's a really promising therapeutic approach. Hopefully, this will go through, we will see. The other project is recently we submitted to NIH. It's a collaborative work between several groups around the world. We actually are thinking about it. This project is not just SPG4 anymore. Our ambition is high in this project. We want to take 50 fibroblasts from 50 human beings from the HSP, contain almost 10 to 12 different HSP mutations, and then 50 control fibroblasts, which is healthy donors. Now we want to reprogram all of them all at once or several different times, and then pull together, and then we can do screening using the advanced technology, single-cell sequencing, barcoding, to find common cellular phenotypes. And now, in the end, we want to do drug screening on that. I don't have time to elaborate on this really, really elegant proposal we sent to NIH. Hopefully, they will be reviewed very soon. I mean, the government is shut down now, but hopefully very soon. And then we are excited about the collaborations between UMass, my collaborators and UMass are doing the pool reprogramming. We're doing the phenotypic studies. And thanks to Dr. Fink and Dr. Fakari to send us all the fibroblasts if it's funded. And then big shout out to Greg and SPF Foundation to provide a letter for us to really go for NIH, big grants to study a lot of HSPs, not just SPG4. We want to find common mechanisms for these study, and then hopefully we can find a common pathways and drug targets that can be applied to different forms of HSPs. And that can be also applied to PLS as well. So last but not the least, I will spend maybe 2 minutes to talk about what we have such a cool technology recently built in the lab, and we're funded to do that with ALS research in the lab. I want to apply that technology to HSP as well, is to create this called assembloids. You heard me talk about organoids, but now the term's going to even deeper because we can assemble the organoids from different regions. So this is the schematic, this is the pictures we took from the lab recently. So the upper ones are the spinal organoids would generate, which is containing the spinal neurons, not the brain, but the spinal cord neurons. And then the lower ones are the brain ones you can see here. So you can see labeled with HB9, which is upper ones is the spinal cord, lower is the cortical region. And this is the first of its kind. If it's applied to HSP and PLS, will be the first of the kind in the field to create assembloids to connect your motor cortical region with the spinal cord region. And this, we call this kind of like assembloids, and then really, really useful to study circuitry, network, and cellular vulnerability with a more complex system, not just the brain, but also contain your spinal cord. I would like to thank all my lab people who dedicated to this project, especially Neha and Skanda, who work on SPG4. And I'm fortunate to have so many different collaborators, including some scientists not even in the United States, but people from scientists from Columbia, Texas, and also I'm very thankful to get connected with Unravel. We're doing drug repurposing and screening very soon, and also Dr. Baas and Emanuela from Drexel as well. So that's all for my talk. Also, last but not least, to thank all the foundations to support us. We have an NIH fund, and we have the SPF fund before. We finished it. And then also the Cure SPG4 and other family foundations to support our research in the lab. Thank you very much for listening.
Doctor, you got time? We're going to take a couple questions here. I saw a hand right here first.
So is it possible to have one mutation and then have other mutations that are either non-identified or have been identified as at other times?
It's possible, because like there are also like in people. It's a very rare case. I encountered a patient who actually SPG4, but it's autosomal recessive. So both parents have different SPG4 mutations and a different allele. Unfortunately, the kid has two different SPG4 spastic mutations, but the parents are fine, not non-symptomatic. But the offspring, the kid is severely affected by two different spastic mutations, actually.
Does that answer your question?
Great. Have another one back here.
Hey, Oscar, great talk. I have two quick questions. In your organoids, do you also have interneurons?
Yes, we do.
Okay.
We have GABAergic inhibitory interneurons in there.
Great.
We haven't looked at this phenotype yet. I think the single-cell RNA sequencing in the future will tell us more about what happened, whether there's any possible in the interneurons in there. But our spinal organoids have a lot of interneurons in there. Not just lower motor neurons. Spinal motor neuron has a lot of spinal interneurons. I personally believe spinal interneurons are so important to keep the motor neurons functioning.
Sure. And when you apply this HDAC inhibitor, do you think it also modulates the epigenetic mark and the gene expression in turn?
It might. We haven't looked into that, but I think Richard might have more, state about it, because HDAC inhibitors probably hits the epigenetic more than the HDAC6 inhibitor.
Thank you.
Okay, everybody, that was a lot of science, and I know you took great notes and you're ready for the quiz. So, good stuff, Dr. Oscar Qiang. Get everybody back to center, okay? All right. So guess what? I don't have any notes, so we're moving right along. We are picking up speed. Everything is going good. Coming up next, we have Dr. Richard Silverman. He is the renowned medical chemist behind the development of Lyrica. He brings a lifetime of expertise in drug discovery. His collaboration with Acava Therapeutics represents a powerful opportunity to repurpose and refine compounds that may benefit HSP and PLS. Dr. Silverman, it's your turn. Come on, sir. This is your controller right here, and you're all good. You just, oops. There we go.
Unless it breaks. Thank you. So I should have one of these first-time attendee tags on mine. This is my first time, and it's really been quite an amazing conference with the research that's been given, but also the advice to the patients I thought was really outstanding. So Hande's already given my talk, so thank you very much for your attention. Any questions? No. So I was asked to give this talk by Norma, and I said to her, what am I going to talk about? I mean, I just make molecules, and I give them to Hande, and she does all the great research. And so she gave me some suggestions of what I should talk about. And so we know Norma's a force. You don't go against her wishes. And so this is what I'll talk about. We'll talk about the discovery properties of NU9, how it goes to clinical trials, the importance of collaboration, and then how it affects you folks. So here's where the story begins. 2007 is when I had an option agreement with a small company, Cambria Biosciences, that's now defunct, And we came to an agreement that we would work on molecules for neurodegenerative diseases, and they were interested in ALS. And so that's what we started with. And just a few months later, in November of 2007, we got $3.5 million for a collaboration among a pharmacologist at Cambria Biosciences, Don Kirsch, my colleague Rick Morimoto at Northwestern to do the molecular biology, and myself as a medicinal chemist. So that's where this all got started, and we decided then to take a different approach from what has been done, rather than look for a target that might be important and then make molecules to affect that. Instead, we realized that all neurodegenerative diseases have a hallmark of protein aggregation. Different proteins aggregate for different diseases, but it's all protein aggregation. So that's what we thought we would do. We would do a screen of molecules to see which ones inhibit protein aggregation resulting from a mutation in a gene that's known to cause ALS. And then, as you'll see, once we got working with Hande, this whole project then got moved to upper motor neurons specifically. And so not only for ALS, then, this would be very important for PLS and HSP as well. So let me tell you the story from ALS point of view first. ALS is a very horrendous neurodegenerative disease. Usually the patient dies within 2 to 5 years of diagnosis. 10% is hereditary. And of the hereditary patients, about a quarter of them have a mutation in the gene that encodes superoxide dismutase 1, and so that's this SOD1. The other 90% sporadic. They don't really know what causes it, and it can just happen. It's the mutation in that SOD1 gene that then aggregates, and that leads to the neurodegeneration for ALS. For, in that case, SOD1, it's only now about 2% of the ALS patients. There are only 3 drugs on the market approved for this, and none of them really have much of an effect on stopping the disease or preventing it from proceeding. So, they said we don't have a target in mind. We're doing what's called a phenotypic screen, where you're looking for a change in a particular property, in this case, protein aggregation. And so we had 2 screens set up, one to look for the aggregates that are formed, and we had to block the proteasome in order to see them, and then another screen looking for the toxicity that's caused from the protein aggregation. And so this company then had a library of 50,000 different compounds that they set up to screen. This was a screen that my colleague Rick Morimoto had originally developed. And so he screened all these compounds, and we came up from that of 17 general chemotypes that had some activity. And then I looked at it and tried to hone that down through different methods. And we got it down to 3 lead series that was more manageable. And I'll tell you about the one series then that led to this compound, NU9. And all these compounds that we selected were active in both of those screens. Okay, so for the chemists out there, this is the structure of that first class of compounds. And what we found early on was about a dozen of these in that library had activity, so that suggested this class of compounds would be important. But what we found is that there's these two rings. If you modify this top ring, you lose the activity. So we felt we couldn't do anything with that. The bottom ring, then, if you got rid of it, you lost the activity. And so then of the 10 that were active, these were two best. And they had really good properties in terms of solubility, stability against metabolism, penetration of membranes, because you have to get it into the brain. The only thing that wasn't so good was the potency. They were actually weak at doing this. And in both cases, it was the potency that was the problem. And so that's what we really wanted to focus on, making these molecules more potent. And so we started to modify the structure. We said we had to leave the top part as is. We changed this ring to different structures, and we found if you don't have groups around the ring, it's inactive, or if you change the ring, it's inactive. So we're really left with a relatively simple problem of taking this structure and just figuring out what groups do you put around this second ring. And so as a medicinal chemist, that's the kind of thing we do. We're looking for changing this R group in different positions around that ring to see how we can improve it. And then once we found a group that was active, we then said, well, what if you put two of them on there? What would happen? And so then we had to figure out what positions would be best. And it always seemed to be if the group was 1, 2, 3 atoms away, that was the best. If you had two of them in that position, they were the best. And that was the case in all of the structures we made. The best of the lot still wasn't tremendously potent, but it was pretty good. And it had these two groups, these trifluoromethyl groups on there. So that was our first compound that we thought could really be active in this. And it had all very good properties. Again, potency was okay, solubility great, stability, penetration through the brain. This hERG channel is a potassium channel in the heart that regulates the beating of the heart. You don't want to mess with that or you're going to have arrhythmias, and the molecule does not affect that, and it doesn't affect a whole bunch of other proteins that would cause side effects. So this seemed like a really good compound to work with. So then it was time to put it in animals and see what happened. And the first study we did was to see if it was toxic. And what we found is that you could give 75 milligrams of this compound per kilogram of mouse. So for a mouse, it's not a whole lot, but for a human, it would be. So that means it's tolerated pretty well. It gets into the brain quite well. That's what we need to do because we're trying to affect the protein aggregation in the neurons there. But when we tried this mouse assay for extension of life, there was no extension of life. And it was like, whoa, this thing had all the properties we wanted. It seemed to do what we wanted. And the other two classes of compounds we worked on were comparable, but they did extend the life of the mouse. So our question was, well, why isn't this molecule extending the mouse life, which was the typical test for whether the molecule is going to be active in ALS. And so we looked at various properties, comparing this molecule. This was another one from another series, and then there was a third one also. And nothing jumped out in terms of stability, whether it got into the brain or not. The only difference is this term, it's a volume of distribution. So this measures when you take a drug, does it distribute in all the different cells? And what we found is that this molecule wasn't doing so well compared to this one, which was active. So we thought, well, maybe it gets into the brain, but it doesn't find its way into the neuron, which is where it has to have its activity. And sure enough, that was the case. We did a cortical neuron assay, and whereas this molecule was active in cortical neurons, this one was not. And so that seemed to be the problem. So how are we going to get it into the neuron? I had a very talented postdoc who looked at the structure of this molecule and of that third class, which also had 2 rings connected by some linker, whereas this thing, there's nothing in between. It's just 2 rings connected to each other. And she said, well, why don't we put a linker in between and expand it and see what happens? And she was right. So if you put a linker in between the 2 rings, then they are active in cortical neurons. And again, the best of the lot was the one that had these 2 CF3 groups at that position. So this molecule then was our new lead molecule. And for the chemists in the group, this carbon right here has 2 different geometries. And so you need to, it's actually 2 different molecules. And so we separated those 2 molecules, and both of them are active in cortical neuron assay, but it's this one that's the more potent, and this one is actually what I'll talk about is NU9. And so that's where that all got started. And so we looked at properties of this as for what you need to do to get approval eventually by the FDA. And what we found is that, again, it's stable. It gets into the brain well. And compared to the maximum tolerated dose of the other molecule, which was 75 mg per kg, this is 1,280 mg per kg, which is a huge amount, saying it's really not toxic at all. It does get across membranes well and doesn't get ejected out of the brain. So it has very good properties. And in this case, it does extend the life of the mouse model. So then we need to look at other possible side effects that could occur with this. And one thing you look at are this class of proteins called cytochrome P450, because they metabolize drugs. And if you happen to be taking 2 drugs, and a lot of people take more than 1 drug, and you interfere with one of these metabolizing enzymes, maybe it won't metabolize your other drug, and that can cause toxicity from the other drug. And so you always have to check whether they're inhibited, and there was nothing significant in inhibition. Again, that hERG channel, the cardiotoxicity, there was no effect on that. And so then for the toxicology, you don't want to just give it once. That's basically what the maximum tolerated dose is. But if you now give it every day for 7 days and see if it's toxic, we went as high as 300 mg per kg per day, and the animals were the same as the healthy wild type animals. So there was no observed adverse effect on that, and that level was at least 300 mg per kg per day. And so if I convert that to a human, and say a 65 kilogram human, about 150 pound human, 300 mg per kg would be about 20 grams a day of this stuff, and it still would be safe. So it seems really quite non-toxic. So this is when I started to interact with Hande. We happened to meet at a conference, coincidentally, and found that she is an expert in ALS. And so we started a collaboration. In our discussion, she made a very important point that at that time, the standard assay for testing molecules was that extension of life. How does the mouse survive longer with your drug or without the drug? And it turns out there are lots of compounds that extend the life of the mouse, but when you give it to a human, it has no effect at all. So it's like, why even bother with that assay? Because it doesn't mean anything. Instead, Hande's approach was, well, let's see what the cause of the disease is and see if we can then, from a cellular level, understand what the cause is and if we could fix it. And so that's the approach then that we were taking. And in doing this could be a new paradigm for testing molecules if we could show that it had some way to maintain the health of these upper motor neurons, which was her specialty. So why didn't anybody else think of looking at upper motor neurons before? And the reason is because there really aren't that many of them. Only a couple 100,000 upper motor neurons in a sea of other billions of other neurons. So no one could see an upper motor neuron in order to study it. And that's what Hande was able to rectify. And I think you saw this from Mukesh's talk, that she was able to label the upper motor neurons in the presence of all the other neurons. So then you could study what happens specifically to the upper motor neurons. And the upper motor neurons in mice are pretty much the same as upper motor neurons in humans. So if you can have an effect on stabilizing those neurons in a mouse, then there could be translation to humans. Unlike extension of life, who knows why the mouse lives longer in some cases and another, may have nothing at all to do with the disease that you're looking at. So then Hande crossed that upper motor neuron labeled mouse with a mouse that has a mutation that causes ALS. And the first one she did was this SOD1 mouse, and then ended up with a SOD1 mouse that had upper motor neurons labeled. But then she went on and looked at other mutations. For example, this one, TDP43. Now that pathology occurs in greater than 95% of ALS patients. That's what the sporadic patients really have, TDP43 pathology. And these are two non-overlapping protein pathologies. So she had these two, and then she also now spoke about a spastic mouse that she has studied. So the first study was to take these fluorescently labeled upper motor neurons, cut them out of the mouse, stick them in a petri dish, and then look at them in vitro in the petri dish. And this is what a healthy upper motor neuron looks like. There's the soma, the cell body, and then a long axon with branches and whatnot. An unhealthy neuron, however, has short axons, and the soma can start breaking apart. So if we take the mouse that has a mutation in it, cut out the upper motor neurons, culture it, and then see the effect of NU9 on it, you see that the axons are perfectly long and branched, and they look like healthy axons. And so we then compared that in this study. So this is the length of the axon for a healthy mouse. This is the length of the axon of the mutant mouse. And now here is the mutant mouse that's been treated with NU9. You can see the axons are quite long. But then the other two drugs, Riluzole and edaravone, well, it does increase relative to the mutant mouse, but not nearly like NU9. But now if you combine NU9 with either Riluzole or edaravone, now you see the axon length is even better. There's an additive effect with this, and this may suggest that these are different mechanisms that are involved, but there is an effect of using them in combination. So that was in vitro work. So then Hande moved on to in vivo work, where we're actually looking at the mice with these upper motor neurons labeled. And first we're looking at neuroprotection. So this is the health of upper motor neurons in the mouse. And so I think it was pointed out that these mice, the upper motor neurons in mice degenerate very early on, like P15, 15 days after birth. But you don't see any symptoms until P60, 60 days after birth. So there's a whole lot of time where the neurons are degenerating, but there's no symptom. And that's a problem with all neurodegenerative diseases. By the time you feel something and go to the doctor, you're really pretty far along in the disease. So we wait until the symptoms, because no one's going to take a pill unless they have a symptom. And so wait till P60 to start the experiment, and then treat these animals every day for 60 days, and then see what's the health of the upper motor neurons after that time. And here is the healthiness of a healthy mouse. Still doesn't look great, but that's as good as it gets. That's the health of the upper motor neuron of a mutant SOD1 mouse. And now if we treated this mutant mouse for 60 days with 20 mg per kg of NU9, it's up better. And at 100 mg per kg, it comes back to what a healthy upper motor neuron will look like. To me, that sounds like we've reversed the neurodegeneration, because it's been degenerating and now it's back to the healthy. Well, it's not just in SOD1. The same thing happens in that TDP43 mouse. And that TDP43 wasn't what we used in our original screen to identify these molecules. And we're finding the same results. Here's the healthy animal, upper motor neuron. There's the mutant, and now here's the treated one. Again, it's back to the healthy upper motor neuron. So apical dendrites you've heard about. That's what's important for this cytoskeletal architecture. And when they start to degenerate, they get vacuoles. That's really bad. And so we're looking at, with the wild type, this is the number of vacuoles in the apical dendrites. It's relatively low. And here's the number of vacuoles in the mutant mouse, very high. But that mutant mouse treated with 20 mg per kg, 100 mg per kg, it brings you back to the healthy mouse. Again, that was SOD1. Exact same story with TDP43. There's the treated, there's the healthy, and so the vacuoles now have been reduced. Protein aggregation, that's what we were really focused on. And you can see here, this is the mutant protein aggregates, 20 mg per kg, 100 mg per kg. We're getting rid of these protein aggregates. You heard a lot about mitochondria, ER. Mitochondria is the part of the cell that generates ATP and the energy and keeps things rolling in the cell, so that has to be healthy. The endoplasmic reticulum was where the proteins are made and processed, and without these proteins, then everything goes awry. And so you don't need to look at all these structures you've seen for the last 2 days. So here's a graph that's summarizing it. This is the average percentage of healthy mitochondria in a healthy animal. This is the mutant animal, and this is treated with NU9. Again, it's brought back to a healthy level. That was SOD1. Same story with TDP43, healthy, mutant, and then treated with NU9. That's the mitochondrial health, the ER health. This is healthy, mutant, and treated with NU9. So body weight tells you a lot about toxicity of things. If you take a drug that's got some side effects, toxicity, you start losing weight, at least the animals do. But at treatment with NU9, there's no change in body weight of the healthy animals or the mutant animals. It stays the same. And then finally, looking at some kind of event that would be important to a patient, namely grip strength. What you can do is take a mouse, put it on a mesh, a wire mesh, and then invert it so it has to hold on to this thing and see if it can hold on. And in this study, it was just carried out for a minute. And so they all held on. For the healthy animals could hold on fine, but the mutant animals, after a certain number of days, started to lose their grip, and they would fall off sooner and sooner. And as they got older, their grip strength got less and less. But treatment, either the SOD1 or TDP43 with NU9, they maintained their grip strength throughout. So when we had all these results then, we thought, okay, now we think we have a molecule that we want to advance to clinical trials. I had a number of issues licensing some compounds out of my group to other companies. And so my sons convinced me I ought to start my own company so that it would be in my control. And so I started a company called Akava Therapeutics. The first program in this was NU9 to see if we can then do all of the studies that the FDA needs in order to get approval for clinical trials. And once it went into Akava, we changed the name to company name AKV9. And so once we started then, we did all the investigational new drug tests that you have to do to get approval from the FDA to start clinical trials. The IND then was approved for phase 1 clinical trials in ALS. And we're now raising funds to start those clinical trials. And as I said, so the good news was I have this in my company under my control, but now it's up to us to raise the money. And so that's where we are with that. But this is now, as you see, an upper motor neuron issue, and that's what you guys have. And so we got orphan drug designation, so ALS, HSP, PLS, they're all orphan diseases. Less than 200,000 people in the country have it at any given time. And so it's approved then for any of these diseases, I believe. And so I said we discovered these drugs from an in vitro assay looking at a mutation in SOD1, and it worked great when we finally got it to a mouse, but it also worked in TDP43 mouse, and the TDP43 mutation or pathology occurs in most patients that have ALS, and about half of the Alzheimer's patients have it. And so we thought, all right, maybe this thing is inhibiting protein aggregation in general. It's not specific to ALS. Let's see if it works in another neurodegenerative disease. And so we carried out a small proof of concept experiment. This is a novel object recognition experiment. Mice are very curious. If you put out an object, it's going to spend time looking at it. If you put out a second object, well, that's a new object. So they spend more time looking at that object than the older object. And that, in fact, this is a control. You can see they spend more time with the new object than they could with the old object. But an Alzheimer's mouse doesn't have a good memory. So if you put out a second object, it doesn't remember it saw the first object, so it thinks, now I've got two new objects, and they spend the same time with both objects. And that in case this is the vehicle-treated Alzheimer's mouse, they're spending the same time with both objects, but the NU9-treated mice now are just like the healthy, spending more time with the new object than the old object. So it's translating now to yet another neurodegenerative disease. And now if you look at the actual biochemistry that's going on, the astrocytes you've heard about, these are cells that sort of support the health of neurons. When the neurons start getting damaged, then these astrocytes then start changing, and they become what we call reactive astrocytes. And this is indicative of the neuron degenerating. And so that's what we looked at in that Alzheimer's mouse model. This GFAP is a protein that is produced by the reactive astrocytes, whereas normal astrocytes don't produce this protein. And so we see these animals now that have damaged neurons. In this case, these are hippocampal neurons, actually. So this is a whole different set of neurons, not just the upper motor neurons, but a completely different set of neurons. That this GFAP is really large, but those animals that have been treated with 20 mg per kg, it's less, and the ones with 100 mg per kg pretty much wipes out that protein, which says then that the astrocytes now aren't affected, which means the neurons are healthy. So in conclusion, we started out trying to look for compounds that inhibited mutation in SOD1, and we found not only do they inhibit that, they also inhibit a completely different set of neurons, that protein in the neuron, TDP43, and then goes on to prevent the problem in an Alzheimer's mouse. And so we're looking at the mechanism of this, and so it's not specific to just that one class of proteins. We're finding what this molecule does, that it activates the part of the cell that clears out aggregated or misfolded proteins. And it doesn't matter which proteins misfolded, this part of the cell just clears out any protein that's misfolded. And so it then should be translatable to other diseases such as HSP, TLS, any disease that's characterized by a misfolded aggregated protein. This compound then should activate the part of the cell known as the lysosome that would degrade it, clear it out. And you're seeing a reversal maybe, and this is all hypothetical, that there's a lot of aggregation that goes on to sort of maim the neuron. The neuron isn't dead yet, it's just sick. But if it goes on a little more, the neuron will die. But if you can clear that junk out before the neuron dies, then it can become healthy again. And so no drug is going to take a dead neuron and make it live again. But if it could take a sick neuron, one that still has life but is got a lot of issues, and then clear out whatever's causing the sickness in the neuron, then maybe you could have a healthy neuron again. And so that's our hope. We would like to put in some HSP patients into a clinical trial to see that. And the Hande's results in the spastic mouse is the first indication that there is crossover. We have to do, I think, more extensive studies with the spastic mouse to convince the FDA that we're ready for that. But I think that certainly is the next step. So I have a lot of people that were involved in all these studies, got funding from various different organizations, and so I'm very grateful to all of them. Thank you all for your attention, and I hope in the future we'll be able to have an effect on this horrible disease. Thank you very much.
Hey, doctor, I've got a question right over here, right next to me.
Thank you for your talk. Wonder if Akava Therapeutics stock is available on the market.
It's not a publicly traded, but we do take investments. So you can just go to akavatx.com and you'll see how you can do it.
Okay.
Thank you. Do we have any other questions? Okay, way in the back here.
Dr. Silverman, this is not a question. This is a comment. I want to thank you. I get excited when I hear about a chemical or compound that might clean out the part of my neuron that's not working, number one. And number two, I want to thank you that you didn't sell it, that you've kept it, and you're trying to make it happen the way you are. That's very important, so thank you very much.
That's a
Yeah.
Thank you. Okay, we're going to do one more over here as I work my way around, handing this over.
Well, thank you for your presentation, but there's been a lot of discussion of identifying genes as a cause, but really NU9, am I right in understanding it makes that a moot point?
Right. Yes, so I mean the mutation isn't important as long as the mutation causes protein aggregation, which is typically what it does, then hopefully this would take care of it. So it's gene agnostic.
So earlier comment in the political arena is we should really put pressure on passing that legislation that allows repurposing drugs.
Well, in this case, it's not a repurposed drug because it hasn't yet been shown to be effective in ALS. So,
Well, thank you, Dr. Silverman. Thank you very much for being here with us today. And we are moving right along, guys, trying to get through all of our speakers today, which is really great to have this many speakers. And we're going to take a second here to kind of get set up. Anyway, I know it's been a crazy day, and we're moving right along. We're getting there. We're almost there. Our next presenter is Dr. Richard Novak. He is the co-founder of Unravel Biosciences, and he is accelerating therapeutic discovery through AI-guided approaches and patient-derived data. His work with Boston Children's Hospital and rare genetic HSP subtypes illustrates how patient samples and modern biology can come together to identify small molecule treatments faster than ever before. There you go. Great job.
There we go. Thanks, everyone. It's been a pleasure meeting with all y'all over the last 2 days. Really just grateful to Norma and Greg and Leonard for inviting me to here. I'll share a little bit about what we do on HSPs. It's actually, we work on 5 different HSPs, and thanks to Oscar, a 6th one. So really excited to be here, and it's been just wonderful meeting all the patients and the families and just understanding better what everybody's going through. So I'm here to talk about Unravel Biosciences. We have this concept of predictable medicine. Like everything you've heard the last few talks especially, there's a lot of, well, we don't know, there's a lot of uncertainty, we have to do all these studies, and that's the reality, that's the hard truth. But we're trying to change that. And so we're trying to combine AI, patient samples, just a different way of thinking about drug discovery and drug development to actually get something that might work for patients faster, better, and cheaper. I have an obvious disclosure as the CEO of Unravel. Hopefully that's self-explanatory. So you guys could teach me about this, but really the diagnostic odyssey is terrible for everybody with a rare disease. Even without a rare disease, we're still left hanging. Very convoluted path, symptomatic treatment. Now genetic testing is becoming more and more standard, but the reality is that about 60% or more patients will not get a genetic test result necessarily. Actually, my co-founder has a daughter that just recently got her result through kind of retesting, but it took years. And that's the reality. Well, even worse news, now you have a diagnosis, you only have about 5% of patients have actual treatments. And of those, you don't actually know if it's going to be working for you, even though it might be approved for your disease. And so that sends you back to this lovely convoluted path. And that's about 95% of patients. These are terrible numbers, right? And so the bar's pretty low for improvement. And that's really the focus of Unravel. How do we make a dent in this? Because it really hasn't changed that much. It's starting to a little bit, but it's way too slow and way too little. And this is how current drug development is done, and there's been some really great descriptions of this already. But the idea is that you start with a target, a hypothesis. It could be one of the HSP genes, kind of driving this discovery process. There's some preclinical work shown with a mouse as an example. And then he gets to the clinic. And there in the clinic, we find out, does it actually work for patients? It could fail here in the early days. It could fail here, getting into the clinic. It might be toxic. There might be other problems. Unfortunately, many drugs fail here. It gets into the clinic and just doesn't work. All right, that's the most likely outcome. And for new targets, for the industry, it's a 98% failure rate. In ALS, it's like zero success rate, so 100% failure rate. This is unpredictable, and this is terrible. It's also expensive, and it hurts patients. So we had this insight that it's really not patients. It's really not the disease that you're trying to treat, it's patients. And you can have 2 seemingly identical patients, and one does great with the drug, other one might even do worse, right? What on earth is that? Well, the truth is we don't understand biology nearly enough to our liking. And this concept, actually, I have to give credit to this guy, William Osler, from about 200 years ago. This concept's been around forever. But with this kind of advent of modern medicine, everybody's been focused on more targets and more precision, kind of losing track of, well, they're patients behind the scenes. And not just behind the scenes, that's the problem we're trying to solve. And the reality is that a patient is not their mutation. That's not the defining characteristic. What a patient is, sure, it's the gene that's causing the disease in this case. 25,000 other genes doing something. Environment, medication, activity, sleep, traveling here, all of that plays some little role, right? And it can add up. And then time. And with neurodegenerative diseases, time is definitely a major, major factor. So what can we do? So what we realized, and this is work that we did at Harvard and then spun out about 4 years ago, we need to start with the patients. Solve for the problem you want to solve. Let's get patient data and drive this whole process from patients to some sort of intermediate test models. Yes, we can discover targets in the process. Great. It's not required, but it absolutely is useful. But then let's go back and let's test in patients before actually going into the clinic for a formal approval study. And what we're doing is really changing how we go about orphan drug development and rare disease. And we like to say we're defragmenting rare by taking data from patients. And notice I'm not saying any particular disease. This is really patients as a whole. Use existing drugs, and I'll tell you about how we do this, but find existing drugs to ask the critical question, does this work in a real patient? Mice are great, organoids are great, we use them, we love them, but they do not answer that question. Only a patient can. And then let's spend time building new molecules, right? Now you can get lucky getting to the new molecules, and people do, but we're trying to make this much more predictable. But the value that we realized in this middle piece, families and foundations started coming to us. This was not our discovery at all. Basically asking, hey, those discovery compounds, can we just use those? And that's basically repurposing, right? And we work with clinicians to get clinical validation on N of 1, just a single patient potentially. We're here to defragment rare disease. We cannot tackle one of each of the 15,000 rare diseases one at a time. That's just impossible. We need to have some aggregation. And then the other part is patients don't have time always. And so what can we do today can be much more helpful than something in 20 years. So that's what we're trying to do. And so out of this really came this novel business model. And so the right side is what we started out with. We're biotech, we have this great platform, we're gonna make new molecules, and we are, and I'll show you what we're doing. But we started RareShift about 2 years ago, which is really to repurpose drugs for rare disease. And so what it does, it actually generates data that we can then shift into biotech that can commercialize this, right? So it's sort of like what you heard in this last talk was a really great example, but we're trying to do this over and over and over, where the group that discovers it can actually develop it, keep control where that links it to patients far more directly than getting it over to Pfizer or somebody. And so let me walk you through what we do. So on that clinical stage, how do we get the data? And so we work all around the world. We have these collection kits where we send for patients to self-collect. We analyze the data from them, but we can ship to most countries in the world. There are a couple we can't. No penguins yet, though. And what we've done, we built a platform called BioNav. And it's sort of, you'll see in a moment, it's like Google Maps for health. Again, making this predictable. You want Google Maps to be predictable, right? You don't want it to be random. That's what we're doing for biology. And essentially, we have a model of what is health from a mechanistic biology standpoint. This has nothing to do with ChatGPT, some related algorithms, but really being driven by molecular data. We also have analyzed about 40,000 existing compounds, including most of the approved drugs, and we can see what they actually do. Forget what they were developed for. That's irrelevant to some extent. It's what do they actually do. And we have this data mine, as we call it, of patient data, because that's the ground truth. That's the problem you're actually trying to solve. And so pulling this all together is really like this Google Maps. You have networks, maps of cities, the traffic patterns, all of that. Now you're trying to navigate from a disease state to a healthy state instead of, let's say, from your home to your work. And we essentially can just map all the different paths. This is the power of computation. Hundreds of millions of different paths. Brute force, just ask, where does this take us? And then we can score it based on, did we want to end up that way? And so here on the left, we first have to map. There's a disease state, there's a healthy state. We typically take first degree relatives as a healthy control, and we just simulate all these drugs. No assumption about what they actually do. And we can essentially map these pathways to restore health. Then on the right, we can see what actually works, and we can start asking more mechanistic questions and do additional research using proteomics and other types of analyses to ask, how did we get there? What are some waypoints along the way so we can find our path the next time? Right? Like you would, for example, drive to your work the first day and then say, oh, that billboard, I always need to turn right at that billboard, right? That's kind of what we do. And then let's find an even better path. Now, this right part might take 10, 15 years, right? So that's what we want to be really sure about, have good predictability before we spend $100 million in 10 years working on that. So on the left that's what we can do today. and just ask, well, what can we do? What does this disease tell us? What's going on? But so then first, sanity check. This all sounds good. It's all nice math. That part checks out. Is it garbage in, garbage out? And so we basically said, well, there are drugs that are used routinely for various clinical disorders that just work in a large number of patients, never 100%, but a very large fraction. So let's say half, 3/4. Could we recreate those if assuming we know nothing about this disorder, could we just come up with those, right? Kind of self-sanity check. And so we started working on tuberous sclerosis complex. It's caused by genes TSC1, TSC2, very different from HSPs, but it's also a rare disease. And here, the clinical standard of care, and it's approved by the FDA, are these drugs called mTOR inhibitors, sirolimus, everolimus. And we basically said, let's take 10 patient samples worth of data, 10 controls, that's it. There's no assumption. I wouldn't even put the name of the disease, there's nothing in there. Would just the molecular signature tell us what we should be treating this with? All the approved drugs are in the top few percent of the results, right? And this took about 2 hours. It took about 6 years of research to get there in real time. And so basically, yeah, we are able to recreate known clinical results. Now, let's look prospectively. So this is a girl we work with. She has a form of cornea de Liang syndrome caused by the SMC1A gene. Unable to walk after having a really severe epilepsy episode. She'd been deteriorating over about 1.5 years before we started working with her. Spent over 100 days a year in the hospital. And even a mild cold would send her to the hospital for a week or two. And she was actually transitioning from palliative care to hospice, so not a good situation. And they started working with us. We used the patient samples, predicted it, and the clinician felt it was appropriate to treat the patient with a couple of these molecules, 2 vitamins and a nicotine patch, of all things, right? So these are easy to come by. And 7 weeks later, she's walking. That's her. We had a video call with her, right? So this doesn't have to take 10 years. Now, this is for this patient. This is not a treatment for cornea de Liang syndrome. This is personalized medicine here. But you can see what the quality of impact has been, right? They were able to travel this summer for the first time ever. They went to, they live in kind of in the Midwest. They traveled to Florida and then traveled to California. First time they've been able to do that. 7 weeks, right? So and she continues to improve. We're actually working on publishing this with the clinician and the family as a case report. And so I just want to show kind of those, there's the science, there's the algorithms. Yeah, we got those checked out, but it actually works in the clinic, and that's the important part. That's why I go to work every morning. But I want to share with you this. So this is a little bit of an aside, but this is Rett syndrome. Not at all similar to HSPs, SPGs, but there's a very direct link, and I'll show you at the end. And so we essentially found a drug candidate, again, starting with, I had never heard of Rett syndrome, to submitting documents to the FDA in about 18 months, right? Like, this is how fast it can work for an existing drug. There's an existing drug, but we also have a new drug that works even better. And so Rett syndrome really, we always hear these names like, oh, it's a neurological disorder, neurodevelopmental, et cetera. These are all whole body problems. It doesn't matter how you slice and dice it. These patients, they have cardiopulmonary problems. Those are actually the most lethal ones. Absolutely a neurological disorder too, but there are many, many things. And so we're thinking about things in a more systems level, whole body problem way. Just like with Google Maps, you don't think about the traffic on this one block or this one street. Everything interacts with everything else to some extent, right? And so, again, there's a publication. I encourage you to go to our website, unravel.bio/science, or it's here. But this is the only data I'm going to show you on this project, because I want to get to the HSP data. But basically, we started with patient RNA-seq data, found a new mechanism, and there's the mutation on the left in this complex network. We found a completely different target. Has nothing to do with the mutation, and now, just like in this last talk that you heard, this opens up the possibility for a lot more diseases to be treated. And we found an existing drug, but it hits a new target, actually through its metabolite. So your liver actually metabolizes the drug, usually to get it out of your system. In this case, usually it's a bad thing. In this case, it's actually a positive. We put the existing drug, this is an oncology drug, vorinostat, that's given by mouth to these mice really late in the disease. So just like in the last talk, which I really appreciated because that is the right way to test, with symptomatic mice or symptomatic models. Prophylaxis is great for patients who don't have symptoms, but if you have symptoms, that ship has sailed. What can you do? Can you actually regenerate some function or regain some function? And we were able to do this versus the one drug that got approved 2 years ago, that in late stages of disease is largely ineffective. And then as we published some of this, a preprint, and then this family reached out to us. They have a boy who was 3 at the time when they met with us 2 years ago, and he was in palliative care. A boy with Rett syndrome, those are usually much more severe, as was his case. And the clinician felt it was appropriate to actually dose the patient a very, very low dose with this oncology drug. Again, that's how severe some of these disorders are. Essentially, he was immobile, not much, and you can sort of see it in that picture, not much interaction. And within a month, they saw some improvements. 3 months later, and they were increasing the dose very slowly. Within 3 months, they actually had very notable, as the physical therapist noted, very notable improvements. And it's been 2 years now, and this boy continues to improve. He's not in palliative care anymore. And so what we're doing now literally should be getting approval next week if the timeline goes well. We are working not with the FDA, funny enough. So this is, we're always told this is an odd thing. Why don't you stay in the US? Well, it's cheaper outside the US, and the patients are there desperate for treatment, like even more so than in the US, and it's actually faster, cheaper to do the work, especially for a small company. Colombia still has their FDA fully functional. So it's been a good time to work outside the US. We did apply to did a pre-IND application to the US FDA to get their perspective that we then incorporated into the Colombian study. But we're testing this oral liquid vernistat in 15 Rett syndrome patients, validating this new mechanism in real patients. Again, that's the key. I don't care about any other data if it doesn't work in patients. And then I care about all data if it does. But then what we're doing, we have an existing drug that again, there's a patient on it today in the US. Actually, 2 more boys with Rett syndrome either have started or are imminently starting on the same dosing. The clinicians saw the improvements. But we have a new molecule that's derived from that metabolite. And this is what we really want to develop. This gets into the brain. This has extremely high tolerability. And that's what we want to do. And so then this is when we get to HSPs. So Oscar kindly reached out over the summer, telling us about his story that he shared earlier. And he was basically saying, how's this vernistat working? How can I get that into patients? Because the drug that he tested was not, you couldn't administer to patients. And we're making the molecule that will go into the clinical trial, so GMP, clinical grade molecule. So we shipped him some of that, but we also shipped him some of Ravel-2 because we thought that his organoids they don't have a liver, so they're not metabolizing the drug. And so these are his results from his lab, generated by Skanda, his postdoc, and just showing that the bottom, the red coloration, if you look at it, these are the SPG4 organoids that he showed earlier. Red is bad. There's less red if you treat. That's the takeaway message. You can see the graph showing those results on the right. And so thanks to Oscar and his lab for sharing this and letting me present their data. But it's the beginning of, I think, a wonderful collaboration showing that we can start with Rett syndrome. And there's actually a second trial that we're working on for Pitt Hopkins at the same time. Their foundation is actually sponsoring that. But then we can extend to some of these other disorders. So again, it's not one disease at a time, it's multiple diseases at a time. But then we have been working on HSPs for the last 2 years as well, exclusively with these foundations. And so these foundations have been really wonderful partners to develop treatments for multiple HSPs. As you know, it's a very complex space, 90 plus genes. We don't want to have 90 different treatments. The smaller the better. The more resources you can funnel towards one or 2 or 3 treatments, the better. And so we did a large study with about 48 participants, and we started about 2 years ago. It took only a few months, so I'm just sharing some of the results from earlier. And we match kind of same-sex family members. And again, I'm going to just give you the highlights here, but we found these are 5 different genes, so SPG 15, 47, 50, 51, and 52. So the last 4 are part of the AP4 complex. 5 different genes, 3 subgroups. Male and female, about evenly split, give or take. A range of ages. This is a pediatric, primarily pediatric disorder. So the oldest patient's 25. And we saw 3 groups. That middle group, which, funny enough, we call group 1, it actually has older patients. And so we do not have any older HSP patients, so we do not know how it would translate to some of the later onset disorders. But my assumption is it probably won't be too different from this. We just don't know which group will fit with what. There is an effect of age. So again, we statistically looked at it. And then interestingly enough, this is going at kind of how do you treat it versus what's the cause? These patients all have different causes. But in most of these patients, especially in subgroup 1, there is AP4B1 and AP4E1, which are part of the AP4 complex, they're reduced, even if they don't have a mutation in it. So there are these shared mechanisms that we're starting to see that actually help explain drug response, not the disease, but how you actually respond to the drug. But then, of course, we want to see, well, what can we do with these 3 groups? How do we develop drugs for them? And we have lists of drugs for each one, but we need to put it into some sort of model. And there are 3 mouse models for 3 out of the 4 HSPs. And so we added them into that exact same plot that I showed earlier, where it's a correlation of how similar these networks are. The blue triangles show you these 3 different mouse models for the 3 different genes. They align really well with 2 of those subgroups, right? So again, it's not gene by gene. It's not the different tissue types. There's something else going on with these mechanisms. But we have some models that we can say the AP4S1 model, it's probably hard to read, that's the top triangle, aligns with that first group, right? They're actually probably the more older patients. But we can do this with 12 HSPs. And so there's SPG4, there's a whole bunch, there's the genes on the right. They don't have the SPG numbers, these are just the genes. But we did this with 12 using public data sets that were available just to see, well, how consistent are these 3 groups? Turns out consistent. So we still have 3 subgroups within now 12 HSPs. Now the question is, well, what about the other 80 HSPs? How do they fit in? Especially the primary patient data, how does that stack up? And this is a way where we can now start tackling HSPs more generally. It doesn't mean that there's sort of a loss of quality for anyone. It just means that you fall into one of these categories and there could be a very good treatment for your category, right? So that's the idea. And so then going back to what I shared earlier, we of course want to figure out, well, how do we treat these groups? Let's start doing something. And so again, with the foundations, we prioritize some molecules. These are just pretty colors, don't worry about this, but basically you can see some differences. There's a lot of blues on the right, a lot of reds on the left, some differences. And then we found some molecules that we could use to go forward. And then we wanted to test these. And so mice are great, they're also expensive, and they take a lot longer. And so what we developed is a squishy-ware platform. We already talked about the software part. We use hardware for analysis, but this isn't hardware, they're squishy, so we call it squishy-ware. But essentially it's CRISPR-engineered tadpoles. So we engineer them at the 4 cells embryo stage. Takes about 3 weeks to make this model. We can tune it, we can adjust it, we can do all kinds of things. And they actually represent a patient population in the sense that they're very diverse, very heterogeneous. They have different behaviors, they look different, they have different colors. We don't really want to get ideal data early if it's going to fail later. We'd rather fail now, right? That's the idea. And then the reality is we have to then screen a lot more animals to deal with that, but we can look for obviously what they look like, how they swim, social interactions. A lot of these are neurodevelopmental disorders that we work on, but even things like sleep. We can measure sleep in these animals. And then, of course, we can look at the drug and see what happens. And so then we found, between the computation, which down selected it to 10 molecules, we selected the best, well, we screened all 10. There were 3 that were actually quite effective. And this is the best one, Rahul 78. This is an approved drug. I'm just not telling you what it is. It's a very safely administered drug used in a reasonably large fraction of the population in the US. And this is showing these seizure-like symptoms, which are probably more the spasticities. It's just hard to tell in tadpoles, seizure versus a spasm. And they're spontaneous ones, so they actually have their own these spasms. And then we can help it along with the kind of the seizure inducer compound. And in both cases, even low levels of this drug actually help. And so between that and the extensive patient data, we're back to patients. And so then we're now working with the foundation with Cure AP4 and a clinician in Denver who's a rare disease specialist to actually ask, does it work in patients? It's an approved drug and clinicians are relatively nonplussed about the whole thing. So it's fairly straightforward to bring to patients. What we're implementing, we're in the middle of designing this. The idea is to probably start Q1 2026, realistically, with the holidays coming up. decentralized study design. This foundation works internationally. They basically made it their goal to work all around the world if the clinician of the patient agrees. We don't want to necessarily down select it to just US or a certain clinical center. It will be done as a result through primarily a telehealth readout. So less data than a full clinical trial, but also far easier, far cheaper, and faster to implement. And then the results are really, we can have some anecdotal data. We also like to use the word anecdata, which is a little bit more than just an anecdote. And that's really what you get from an N of 1 patient test. But this will be yet to be determined number of patients. And we want to see, well, what's working with this drug? We don't yet know. We know what's going to happen in an animal model, but we don't know what that translates into humans. But let's try it. Let's ask that question. We also are estimating that about 2/3 of the patients will respond, all of these 4 HSPs that we're working on, not 100%. And so one thing that we are doing is building markers to then, for a formal study, have some way to say, well, we think you will respond, we think you are in this other group, and there's another molecule for you, right? That's sort of how we're trying to do it. And let's do it all at once. And we even have some potential genes that already do this, so this would be more validating it. And then this really would be really key clinical data to support drug approval. Not so much the drug approval as part of this study, but to design that future trial that would let us really get this drug approved. Though in the meantime, and what happens oftentimes in rare disease is a publication might enable clinicians to have the confidence to start using it more broadly, and it sort of becomes part of more routine care. This is a drug that we do not think has any commercial value. I share it. I don't share the drug name for this kind of our policy, just not share drug names. We don't think there's commercial value. We do think that the targets it's hitting have commercial value, but for us, it's really, let's find something that works. Let's de-risk this decentralized study approach so that then the future study doesn't have to cost $50 million. It could be maybe 5, and you can get a drug approved, right? And that's really the idea, that it would also benefit other programs like Akava. And that's really what we have. So the whole idea is that this is drug development driven by patients, not a mechanism, not a target. And we believe, and hopefully I've shared a little bit of I think, very intriguing data that suggests this predictable medicine concept is making medicine, in fact, more predictable. So yeah, thank you so much for your attention and for inviting me. This is part of our team, and yeah, we're based in Boston. If you're ever there, come visit us. Yeah, thank you so much.
Doctor, let's see if we have any questions. Any questions? Any questions? Oh, I see one back here. Okay, on my way.
Thank you for the presentation. How could a partnership with the SPF Foundation accelerate discovery or translation, perhaps by connecting patient samples, data, or clinical expertise to expand drug discovery across HSP and PLS?
Yeah, thank you so much. Well, it's already doing it. So being here, talking with a number of the researchers and clinicians has already catalyzed a lot of really exciting next steps. And then with Oscar, we're already well on our way with Ravel-2 and testing that in his organoids. So it's already done that. At least the beginnings of it. But I think where I see the potential, when we started working with some of these other foundations and looking at what's available, what data are available publicly, it was scary. It was 7 different data sets out of 90 potential diseases, right? That can change. And the data that we use, how we work with RareShift, we share all the data for non-commercial use. So if we generate the data, we want researchers to have access to it, to enable their discoveries and keep going. So, that's a very obvious area, is generate data for as many disorders as we can, including the undiagnosed ones. And that's a large area of our focus, because again, we just need an RNA sample or just a tissue sample. It's a nasal swab, guys. Like, it's not even painful, maybe tickles. And so we developed this for kids, right? So that's what it was designed for. And so that would be an easy way to get going, build a database of HSPs and PLS. I mean, to us, the disease name means nothing. We are not the experts in that disease. It doesn't tell us how to treat it, what we should focus on. That's a way to get patients together, work with a fantastic foundation, and be stronger together. That's what impacts us. The disease name and diagnosis, that to us, that's secondary because we see patients with identical diseases, identical even point mutations have completely different responses. So we've seen the reality that it's not that helpful. So we're focused on that data. But I think that's one way. And then with several foundations, I mean, we're about to start a clinical trial with one foundation. So that's yet another way we can work together later, right? That's not the first step, and everything in between. And you guys have already done some fantastic work supporting these discovery tools, screening platforms, the models. All of that comes together.
Thank you. Excuse me. Any more questions? Anybody else? I know. Oh.
What would be that cost on a per person basis to provide you with the swabs, if you will, and are there any kind of particular procedures that need to be considered?
Yep. So all the details are on rareshift.org right there. So we actually set up it is a not-for-profit business model. It's not free, but we don't make any money off of this. It just covers the costs. So typically the population studies are 20 or more people. Because you want to have that for statistical reasons, because you're going to get subgroups. So those are $66K for doing all of that analysis, and then there's like a per patient additional cost that's much smaller for any additional samples, because that covers all the computation. Shipping has gone through the roof these days, things like that. Yeah.
All righty, ladies and gentlemen, Dr. Novak. Okay, we're getting set for our last speaker of the day. I know we're doing something right. I can see it in your eyes. It's been a long day. You're learning a lot of science. You know we're getting to the end of our day, but this is all super great stuff. And what's so interesting is to see all the different groups and types of people that are working around this whole series of work that's being done for HSP and PLS. Pretty cool stuff, guys. So hang on. We're getting close, and we're getting set up right now, and I think we are ready to go. Hey guys, everybody we have here is Dr. Rahul Sachdeva, and he is from the University of Kentucky, and he's going to talk to you about neurostimulation. Here we go.
Thank you, Tim. So thank you, everyone. It's really an honor for me to be here. I was introduced to the world of HSP by Dr. Baas about a year ago. So my research focuses on spinal cord injury primarily and a little bit on cerebral palsy. So I will not be showing much or any data about HSP or PLS in this presentation. But what I've been finding since last day and a half here is so refreshing to see the talks on something that is not spinal cord injury. So I hope when you see my presentation, you find it refreshing to see something that is not HSP, and hopefully maybe you can guide me on how I can use the tools in my lab to help the population with PLS or HSP. So with that, I would like to thank my research support. I don't have any conflicts of interest financially. So as I mentioned, I'm not going to talk about HSP or PLS today. What I'm going to talk about is two conditions. First is spinal cord injury, which in most cases is a traumatic condition affecting young adults. It affects more than 15 million people globally, and more than 300,000 in US alone. So when there is a traumatic spinal cord injury, there is a direct loss of function. But along with that loss of function, which a general public will see as a motor impairment, there is also secondary implications which are far more devastating to this population. And I'm going to talk a little bit more about that. The other condition that I'm going to, sorry, I didn't play the video earlier. So here is how a schematic animation of how a spinal cord injury happens, and it sort of disconnects the pathways within the spinal cord that are sort of conveying information to and from the brain to the target organs. So the other condition that I'm going to talk about is cerebral palsy. Here's an example of a very severe case of cerebral palsy without any neck or trunk control in this kid. So cerebral palsy, just like spinal cord injury, affects a lot more people globally, a lot more in number compared to HSP or PLS. It is one of the most common childhood motor disorders. It usually happens during or after birth to as an injury to a developing brain. So although it's non-progressive, but those symptoms persist and can have more progressive physiological complications over the course of life of these individuals. So it also presents as motor weakness, spasticity, or other developmental delays that sort of start at the time of the birth of a child. So what I'm going to try to cover today is give you a little bit of a 100,000-foot view of what is neuromodulation and where I fit in that big field. I will also give you some examples of my work on spinal cord stimulation, neuromodulation, whatever you want to call it, for spinal cord injury and cerebral palsy. And most importantly, I would like to learn from you guys if we can use this technology to benefit you all. So, as I said, a brief overview of what neuromodulation means. So by definition, neuromodulation means we are altering the activity of neurons, whether it's in the central nervous system or peripheral nervous system. And this can be done a number of ways. Electrical spinal cord stimulation, electrical neuromodulation is the most common way to do it, but that's not the only way to do it. Magnetic neuromodulation, it can be done by light, optogenetics. It can be done by ultrasound. It can be done by chemicals. It can be done by mechanical or sensory feedback. So there are a number of ways you can alter the activity of neurons. My focus stays on electrical neuromodulation, which is we are altering the neural activity using mild electrical current. Within electrical neuromodulation, it's a wide field. So some common examples are deep brain stimulation, cortical stimulation. We heard about vagal nerve stimulation as well. That's also a type of neural modulation. And what I specifically focus on, spinal cord stimulation or spinal cord neuromodulation. So spinal cord neuromodulation itself is a big field as well. There are two main ways that we do spinal cord stimulation. They're not the only two ways, but the two main ways is one, using an electrode placed right above the dura mater. So surgically implanting an electrode over the spinal cord under the bone. And that would be, if you magnify the cord here, the electrode is implanted here. So that's a surgical implantation of an electrode. It's also called epidural spinal cord stimulation. What I focus on is placing the electrodes on the skin using a non-invasive spinal cord stimulation. That is the focus of my research in the lab. And there are a number of studies that make us believe that we can target similar neural correlates with a non-invasive approach that have been shown to be targeted by an invasive implantable electrode. So now let's dive into some of the data that I wanted to show you for spinal cord injury. So I just wanted to start with just this statement that I usually always start my presentation with, is that spinal cord injury to a normal person looking from outside, it might be perceived as a motor paralysis, that the person cannot walk, they're confined to a wheelchair. But if you talk to the people with spinal cord injury, it is a lot more than motor paralysis. So we published this review about a year ago, and we sort of covered in this review that there are a lot of invisible consequences of spinal cord injury. And looking at the survey from you guys yesterday, even some of those are also being affected in this population, such as bowel and bladder control, right? So these not only are invisible consequences of spinal cord injury, they are also some of the greatest determinants of the quality of life in this individual. And they are indeed the top priorities of recovery in this population. So there are surveys published by many people and looking at these priorities for recovery in people with spinal cord injury, and walking is usually not the number one priority in these individuals. They rank sexual function, arm and hand function, bowel and bladder function, blood pressure control as a higher priority for recovery than walking itself. So my focus in spinal cord injury has been on modulating the blood pressure control. So before I show you some data, so I wanted to ask audience here, what is the normal blood pressure in a normal individual? Anybody? 120 over 80. So if you look at it over a course of a day, over 24 hours, this is what a able-bodied, neurological, normal individual blood pressure looks like. So this person was implanted with a blood pressure cuff, sent home. The blood pressure was recorded the entire 24 hours. The gray part is the nighttime, and the white part is the daytime. And what you can see is also a nocturnal dip. Blood pressure sort of dips at night. Where's my pointer? Here. So this is nighttime blood pressure, this is daytime blood pressure. So yes, there are fluctuations, but this 120 over 80 is the dashed horizontal line that you see. The blood pressure is somewhat in that range. What if you measure the blood pressure from a person with a very severe cervical spinal cord injury? This is what it looks like. Their blood pressure is almost never normal. What you are seeing in this red trace compared to green trace is, yes, there are fluctuations, but the fluctuations are far more severe. So for the purpose of this talk, I'm not going to go into the mechanism of how this happens, but I just wanted to still name these conditions. And these conditions are, you see there are pits and there are peaks. So the high blood pressure episodes are called autonomic dysreflexia. And the low blood pressure episodes are called orthostatic hypotension. So these individuals sort of undergo this fluctuations in blood pressure, kind of like pendulums-like swings, which we sort of described in a review paper, calling it like a pathological blood pressure pendulum that these individuals are suffering with on a daily basis. Their blood pressure is sometimes too low or sometimes too high. And we can sort of isolate these conditions in lab, sort of mimic them, and then we test our interventions. So let's look at the autonomic dysreflexia for a second. So autonomic dysreflexia, or I sometimes call it as AD. So when I say AD, it's not Alzheimer's disease, it's autonomic dysreflexia. Here is a case of a severe autonomic dysreflexia. So what you're seeing in gray is the blood pressure of an individual with cervical severe spinal cord injury who came to the lab, or rather clinic, for penile vibrostimulation. This was a young adult who wanted to become a father, and this was a procedure called penile vibrostimulation. So there was a vibration stimulus applied to his penis to retrieve the sperm. So every time there is a vertical dashed line is when the stimulation is applied. And you can see there's a blood pressure spike. And where the asterisk is, where you see the highest peak, is the time the person ejaculated. We talked about 120 over 80. That's the 120 is the normal systolic blood pressure. At the time of ejaculation, the blood pressure is more than 3 times. It's almost 350. That can't be good. And this is one episode. This can happen more than 40 times in a day in one individual. And not to mention the low blood pressure episodes. It's normally observed in people with higher level of spinal cord injury because there is more impairment, more part of the spinal cord is now disconnected from the brain. And it has some known signs and symptoms like flushing, piloerection, but a lot of times this is asymptomatic, which causes a bigger challenge. I'm not going to get into the nitty-gritty of the mechanism, but it's important to understand that there is a reason why this is occurring several times a day. It is kind of like a reflex. So I'm sure many of you know the knee-jerk reflex, where a tap is done on the knee and you see the extension of the leg. This is kind of like a blood pressure reflex. It's an autonomic reflex. So whenever there is a trigger, because there is a spinal cord injury, there is no inhibitory pathway from the brain. So it sort of causes this massive constriction of the blood vessels that causes this blood pressure to shoot up in response to a stimulus. And that stimulus, most of the times, is a full bladder because these patients can't sense that they have a full bladder. It can be UTIs, can be penile vibrostimulation that I showed just now. It can be fecal impaction or constipation. Their bowel function is also impaired. So a stuck poop can cause massive surge in blood pressure that can be fatal. And these are some of the most common causes, but there are a number of triggers that can cause this blood pressure to spike up in these individuals. And as I said, these are not without consequences. Such a high surge in blood pressure can cause a hemorrhagic stroke. There was a study done by my previous postdoc advisor, Dr. Krasikov, where he looked at a number of cases of autonomic dysreflexia and the complication it causes. So out of these 32 cases of autonomic dysreflexia, what they found was almost 75% of them led to CNS-related complications, so such as hemorrhage. There were some cardiovascular consequences, and 7 of these cases unfortunately resulted in AD-related death. So what do we have clinically right now? So again, this is a blood pressure fluctuation. I showed you an isolated episode of blood pressure going up, but these individuals are showing fluctuations in blood pressure throughout the day. So for AD, for autonomic dysreflexia, obviously education is important. I'm not going to go through all of this. I just wanted to stress on one important point. There is non-pharmacological management of blood pressure, and the last case resort is pharmacological management. Similarly, for low blood pressure or orthostatic hypotension, there is non-pharmacological management and there is pharmacological management. But the key is the word management here. These are managing the symptoms. We heard the word disease-modifying therapies. There's not much disease-modifying therapies for spinal cord injury. And the most important thing between these two is when you are pharmacologically managing these two conditions, it's really important to strike the balance. While you're treating for hypertension, you don't want the patient to go into extreme hypotension because of a drug, and vice versa. And the other important thing I hope you noticed in the spikes that I'm showing you, those spikes are ultra fast. They are like a reflex. But if you give a patient a drug to lower the blood pressure or increase the blood pressure, the drug is going to take some time to kick in, and it's also going to stay in the system for far longer. So a slow-acting drug is not the ideal approach to manage a fast-acting condition like AD, for example. So what can we do? So can we use electrical neuromodulation of the spinal cord to sort of modulate the blood pressure? So using epidural spinal cord stimulation, there have been some studies that have shown that we can modulate blood pressure. So we asked the question, can we do it in a non-invasive manner? So here's one individual with chronic cervical spinal cord injury. AIS-A means this is an Asia impairment scale. Category A means it's the most severe form of spinal cord injury. So this person got an injury in 2016, came to our lab in 2019, and we wanted to see, can we use non-invasive spinal cord stimulation to modulate its blood pressure? So here is the MRI for the patient showing the injury. So first of all, we wanted to trigger autonomic dysreflexia in this patient to be able to mitigate it or prevent it. So we do that using a procedure called digital anorectal stimulation. That's a very common procedure used by these individuals to take care of the bowel routine, to empty the bladder, empty the bowel. And when they do that, it also is sometimes perceived as a noxious stimulus by the nervous system, causing autonomic dysreflexia. So this is a case of a controlled autonomic dysreflexia. It doesn't look as severe as the image I showed you because this is done in a controlled manner. So digital anorectal stimulation causing blood pressure to go up. If we apply spinal cord stimulation using a non-invasive electrode at the back of this individual, same noxious stimulus, same digital anorectal stimulus from the anus is not causing autonomic dysreflexia in this individual. And we quantified this over multiple repeats in this one person, and we were able to prevent autonomic dysreflexia using a non-invasive, just a sticker on the back. That's all we did. And mild electrical current, we are able to sort of block these signals coming from rectum, causing blood pressure to spike. We also wanted to see, can we cause autonomic dysreflexia first and then try to interrupt it instead of preventing it? So this is what we did. So the autonomic dysreflexia was triggered first, the blood pressure went up. This lightning bolt is where we started the spinal cord stimulation, and we were able to bring the blood pressure down again. And this was the quantification. So this is the severity, the change in blood pressure from baseline, and this is with spinal cord stimulation. Same thing here. So this is prevention, and this is interruption of autonomic dysreflexia. The other extreme of blood pressure, orthostatic hypotension. Can I have a show of hands? How many of you have ever felt a sort of a lightheadedness when you suddenly get up. Yes. So that is orthostatic hypotension. The blood is being pulled down to the body because of the gravitational pull. What our body does normally is the blood vessels in the lower part of the body will constrict, blood will go back up, you get the venous return, and you feel normal again. But in people with spinal cord injury, that neural control is not there. So these people can actually faint just going from a supine position, which is lying down on the bed, to even sitting up. They can faint. The blood pressure can go really low, and the body cannot respond to that. So a reduction by 20 millimeter mercury or less or more from baseline is called orthostatic hypotension. So we test this by tilting this patient 60 degrees. And if the blood pressure goes down within 3 minutes, it is called as classic orthostatic hypotension. So in this patient, as you can see, as the tilt begins at this line, the blood pressure went really low, and we had to actually put the patient back into the supine position so that they don't collapse. And I'm going to skip the mechanism slide here. Essentially, it's the lack of neural control of blood pressure that is causing this. So similar to reducing blood pressure during autonomic dysreflexia, we wanted to see, can we prevent this blood pressure from falling by stimulating the spinal cord? So here is during the tilt, another individual. You can see as the person is tilted, the blood pressure goes down. So this is the systolic blood pressure baseline. This is during the tilt. Now, remember, the drugs are slow. We wanted to see, can we do it almost immediately? So when we applied the spinal cord stimulation, again, a sticker on the back, it's just a non-invasive mild electrical current. This is what we see. So this heat map sort of shows you the intensity. So darker red means more strength of current. Yellow means almost off, like 20 milliamps or so. And this person is tilted, but then we start stimulating the spinal cord. And we can bring the blood pressure up to almost normal levels. While the person is tilted, if we stop spinal cord stimulation, we can see that the blood pressure is going down again because person is still tilted. But again, we can restore it if we start stimulation again. And this was quantified, and we can clearly see that we are able to restore orthostatic hypotension. So we have a paper under preparation right now where we did animal studies with rat models of spinal cord injury. I did not show you any of the data today. And then we did this human studies, and we showed that within the same individual, we can use this spinal cord stimulation, transcutaneous spinal cord stimulation, to sort of stop this pathological pendulum of blood pressure swings in these individuals, which we think is a far superior approach compared to let's say, pharmacological intervention. So now I'm going to switch gears a little bit, and I hope this part of this presentation will be a little bit more interesting to you guys, because this is going to be focusing on motor function in kids with CP and one adult with CP. And I wanted to just give a shout out to Dr. Parag Garg from Spinex. Spinex is the company that makes these devices, and this work on CP was done in collaboration with Parag. In fact, it was led by Parag. So I really want to thank him before I show you this data. So cerebral palsy can be graded from GMFCS 1 to 5, 5 being the most severe form of CP. The child that you saw earlier was a grade 5 CP with impaired neck and trunk control. And GMFCS level 1 is the mildest form of CP, where you'll see some impairment, but the child can walk. So there is a spectrum of impairment in cerebral palsy going from level 1 to level 5. Right now, the current standard of care is some oral medications, which of course have their side effects. There are Botox injections, which can, as you know, paralyze muscles. And there is reconstructive surgery, which again can have irreversible loss of function as well, if the person is going for a musculoskeletal surgery. So my take from that is that, again, these are either ineffective or invasive treatments that are currently available, and they are reducing the symptoms. They're not really curing the disease. We are not really modifying the underlying pathophysiology of the disease. So looking at a kid with GMFCS level 5, if I can play this video. Let me pause it for a second. So what we are looking here is a real-time effect of spinal cord stimulation. I keep saying the word disease modifying. Right now, in this video, we are not modifying the disease. I'm just showing you the real-time effect of spinal cord stimulation when the stimulation is on versus when the stimulation is off. So this is a severe case of cerebral palsy, level 5. You're looking at sitting and head control in the kid. So SCONE stands for spinal cord neuromodulation. It's just an abbreviation that was used in this previous version of the video. On the left, you can see the kid is really having a tough time maintaining their neck control and trunk control, and the physical therapist is giving a lot of support. On the right-hand side, the stimulation is on at the cervical and the lumbosacral region of the spinal cord, and there is a lot more stable control. Yes, support is needed, but the needed support is much less. You can see as the support is taken off, the kid is not able to maintain balance. And then same child looking at sit to stand, so going from a sitting position on this therapist's lap, going to a standing position. On the left side, the neuromodulation is off. There is no current going into the spinal cord. On the right-hand side, the spinal cord neuromodulation is on. There is a mild electrical current going through the skin into the spinal cord. And you can see, also look at the knee of the therapist. You will see how less support it needs on the right. So on the right, SCONE is on. There is no knee support. And you can see that the child is still standing. So on the left, you can see that there is a support from the leg also to be able to maintain that standing pose. And this image here shows you where the electrodes are implanted. Or rather attached, I should say. This is the video that Dr. Baas showed earlier today in the kid with less severe form of cerebral palsy. So this is level 4, where there is a lot more neck and trunk control, but there is no stepping. So this device has now been rebranded by the company as X-Step, and they have received the CDSCO approval, which is essentially an Indian regulatory body similar to FDA. And they are marketing this device in India right now. So if I can play the video, many of you have seen this video earlier today. But on the left, as you can see, there is no stepping on the treadmill when the device is off, versus on the right-hand side, when the device is on, there are some steps. This is almost instantaneous effect of spinal cord stimulation. And one thing I wanted to mention here is that the intensity of this current is not a lot. We are not trying to trigger muscle movements. This is actually a sub-motor threshold current. So the movements that you're seeing are voluntary. So what we like to say is we are enabling movement rather than triggering the movements. Okay, so these were the real-time effects. We saw what current was able to do in real time. Then we also did a longitudinal study in 6 children with CP across all the GMFCS levels. And I just wanted to sort of guide you through the study design. So half the kids for the first 8 weeks got no spinal cord stimulation. What you see as ABNT here is essentially physical therapy. It's activity-based neurorehab therapy. And half the kids got SCIP, which is another name for the spinal cord stimulation device. They got spinal cord stimulation. At the midpoint of this trial, these also got spinal cord stimulation. So we were able to compare no stimulation, only physical therapy, versus stimulation for 8 weeks and also stimulation for 16 weeks. And the outcome that we measured was a GMFM 88 score. So it's gross motor function measure score of 88 different points. And what you can see here is the higher the score, meaning more functional recovery. And what you see here is just physical therapy over 8 weeks. Physical therapy combined with spinal cord stimulation for 8 weeks. physical therapy with spinal cord stimulation for 16 weeks. And then these kids were receiving no spinal cord stimulation for another 10 weeks. And then we tested the 3 of them again after 10 weeks, and there was still the maintenance of function. So this is what makes me think that there is some sort of a long-lasting change which tempts me to say it's a disease-modifying therapy. We don't know what it is at this moment, but it seems like there is some sort of a persistent effect of spinal cord stimulation. Whether it will last for more than 10 weeks or we don't know when it will go away, whether we need to keep stimulating. We don't know the answer to that yet, but it looks very promising. And one thing I also wanted to point out here is something called as MCID. So statistically significant is one thing. What MCID means is minimum clinically important difference. So a change of 5 points on this scale from baseline is considered a minimum clinically important difference, or MCID. And we were able to see more than double of that. So we think that we were able to make a clinical impact as well, in addition to showing statistical significance. I also wanted to show you this figure, which I think is really interesting. So 3 out of those 6 kids being shown here. Okay. So what you're seeing here is age in months. These 2 long lines are basically showing how these kids would have recovered. This is data generated from thousands of kids, showing a normal progression of CP and how these kids will recover in terms of the motor function if there was no intervention like this. Now I want you to focus on these 2 kids which received only physical therapy. You can see the lines are a lot more flat, meaning less slope, and they are not reaching the MCID, which is what I showed you in the previous graph. However, in this one kid I'm showing here, this was around 20 months old kid, the line is a lot straighter, meaning the recovery is faster, and also it is crossing the MCID. So I thought this was a really important finding in this study. And here is the kid, same kid that you saw on treadmill about after 12 weeks of treatment. So he's riding his own bike. Remember, this kid was not able to step on the treadmill. Okay. Next thing I wanted to show you, this is the last part of my presentation, is CP is not just a childhood disorder. Yes, it is. It starts in childhood, but thanks to the medical care, almost everybody survives and patients live on their lives. So we did a study in a woman who's 60 years of age who was diagnosed with CP when she was 1.5 years of age. So this paper is already published. It's a single case report. And as I said, she was GMFCS level 3, so somewhere in the middle in terms of the severity. And I was able to get my hands on her medical history, and with her consent, we were able to sort of chart it out. And she was diagnosed here with spastic paraplegia when she was about 18 months. And over the course of her life, she went through a number of different interventions, including corrective surgeries, different types of therapies. For the last 15 years, she was also undergoing physical therapy, but that was not really benefiting her. So at the age of 60, she got enrolled in our study where she got, again, similar 8 weeks of spinal cord stimulation paired with physical therapy. And this therapy, sorry if I did not mention, this therapy is delivered twice a week, 1-hour sessions. So it's only 2 hours a week, essentially. And this is her change in the motor score. Remember, this is the MCID. So this is pre, this is post. We saw almost twice the MCID change, so twice the minimum clinically important difference. And again, these symptoms, these improvements persisted when the therapy was stopped for several weeks. I think it was 8 weeks. Yes. So what you're seeing on the right is her pre-therapy going from floor to a bench sitting position. She was able to kneel better when she received therapy, and she was able to do this progression much faster, going from the floor to the bench. And we have a lot of qualitative anecdotal evidence from her, how she was able to sleep better because she was able to turn better in her bed at night. She was more confident taking showers without the risk of falling. She was able to go up and down the stairs with only holding the rails with one hand instead of both the hands, so giving her more freedom. So there are a lot of things that we did not document quantitatively, but there were a lot more qualitative changes in her life. Okay. So just my last slide. So hopefully what I was able to show you is that individuals with these neurological impairments, such as SCI or cerebral palsy, there is this both motor and invisible autonomic dysfunctions that are not visible to the public, and they're both important. They impact the quality of life in these individuals, and the current standard of care that we have available is more focused on symptomatic management rather than underlying pathophysiology. And I hope I was able to convince you a little bit on that spinal cord stimulation could be a potential disease-modifying therapy, and we are able to do this non-invasively in our lab. But again, there is a lot that needs to be done. It is very promising, but it's in a very early stage. What I showed you was 3 cases, 1 case. These are not very well-powered studies. So whatever I show you, yes, it's exciting, but take it with a grain of salt. We need much, much stronger studies as well. So this is just an example I wanted to show you from a review that we did for spinal cord stimulation in autonomic function after spinal cord injury particularly. And what it's showing is a half of a pyramid. So if anybody is familiar with the evidence-based medicine, this essentially shows the quality of evidence that is available. So lower part of the pyramid means low quality study, individual cases, case series, expert opinions. And as you go higher in this pyramid, it is the highest level of evidence, whether it's a meta-analysis, randomized controlled trials. And you can see that in spinal cord stimulation studies, most of the research is here. Some cohort studies as well, but we don't have a proper RCT. There is one that has recently come out on motor function. This was designed for autonomic studies, so that's why it doesn't show it there. And the other thing is, as you heard throughout the last 2 days, that there is a lot more animal studies for HSP or PLS that needs to be translated. In the field of spinal cord stimulation, that's quite opposite. So again, from the same review paper, you're looking at studies over the number of years, and above is the animal studies, and below is the human studies. There's a lot more human studies being done in the spinal cord stimulation field compared to the animal studies, meaning we know that it's working, but we don't know how it's working. So I would love to invite any collaborative studies here, any partners who can, we can collaborate and sort of also understand mechanisms in future, trying to devise your really cool animal models and use those as tools to understand the mechanism of how these therapies are working. With that, I would like to thank my previous lab where I did most of this work. I recently started my own lab in University of Kentucky, but most of the work that I showed you was done in the laboratory of Dr. Andrei Krasikov in Vancouver, Canada. And I really thank him and all the lab members for that, and also the funding sources. And I'm happy to take any questions now or over emails, outside, wherever you like. Thank you.
Okay, guys. Anybody? I see a hand up. I always seem to be looking in your direction.
Thank you for your presentation. I was wondering, the X step, you said it was on the market now. Is that something that anyone can purchase, or?
Yes, so it's in the market in India, not in US. So a similar version of X-Step. So the company that I was at some point consulting with, they have different versions of this device. Their main flagship device is currently under FDA consideration for bladder function. They have another device named Skip in US, which is the similar version of X-Step. The X-Step that I showed you is being approved and marketed in India, not in US.
So Skip would be the US?
Skip would be the device, but it does not have an FDA approval right now. Mm-hmm.
Got another question right next to me.
So how does the level of electrons equate to like a TENS unit?
That's a great question. So I'm glad you asked this question. So when we talk about TENS, that's usually muscular stimulation. We are trying to guide the current towards spinal cord. The intensity of stimulation in TENS is far higher. As I mentioned earlier, we are trying to not trigger the muscle. So we actually keep increasing the stimulation to the point there where we see a muscle contraction, and then we dial it back to a point where we can call it submotor threshold, meaning it's not triggering muscle contraction because we want to see voluntary movement. So that's the fundamental difference: the direction of current, where it's targeted, and the severity as well, intensity as well.
Any other hands? Do I see any more hands?
I
I
think there
got
was
one
a
in the back
question.
row.
Okay, perfect.
Hi. How do you think the applying the current can both increase and decrease the blood pressure with the same stimulus?
That's an excellent question. So I did not show any of the mechanistic data. We have a lot of animal studies also from our group and from the group in Switzerland. So for increasing blood pressure, so we need to understand how the blood pressure dips. So there is between T1 to L2 spinal cord, we have a set of neurons called sympathetic preganglionic neurons. Those are the neurons that send the signal out to blood vessels, maintain a tone in the vessels, which maintains the blood pressure. When injury happens high enough that most of these T1 to L2 neurons are sort of disconnected from the brainstem, which is where the control center is for the blood pressure. At a resting state, the person is in hypotension all the time because the blood pressure is low. So, and it gets worse when there is an orthostatic hypotension. So we think spinal cord stimulation can activate those disconnected sympathetic preganglionic neurons, sending the signal towards the blood vessels, causing them to constrict. And that's how we think it's causing the vasoconstriction to bring the blood pressure back up to normal. Now, talking about autonomic dysreflexia, it's a little bit more complicated. We have to understand how AD works for that. So it's like a reflex loop. There is a signal coming in from, let's say, rectum or bladder or ingrown toenail. It could be tight shoelaces. Anything can cause AD. That signal gets traveled up the spinal cord through something called as propriospinal neurons. Sorry, I'm getting too technical here, but it's really important for me to explain that. So there is a signal coming up, and then it goes to the same SPNs, causing them to fire in a way they should not be firing. It's an exaggerated firing. The way we think spinal cord stimulation works is a principle called gate control theory. This was done in 1960s by two Nobel laureates called Melzek and Wall. And what they showed is that the application of an external signal can close the gates for a noxious stimulus. So essentially, think of it like, why do you itch when it scratches? Or why do you itch when you get a mosquito bite, right? You are trying to confuse your system. So that's something similar what's happening with the spinal cord. You are trying to activate a different set of neurons in order to close the noxious stimulus gate. I hope that answers your question. I'm happy to talk more. Yeah.
Okay, is there any more questions? Where is it? I know I've been looking for one. Okay, I got one right here.
Yeah, you were mentioning the unit for bladder control.
Yes.
Can you elaborate on that?
I'm sorry?
Can you elaborate?
Yes. Yeah, so that device is called SCONE. The Spinex company that I was collaborating with, they've just finished a pivotal clinical trial across, I believe, 12 or 13 different sites across Canada, US, and India. And they're just putting the data together for FDA application for getting approval for that. And
it is not yet a FDA.
It's not yet approved. The clinical trial has been done. Results are positive.
Is it approved anywhere?
It's approved anywhere? No.
Okay.
So there is one spinal cord stimulation device that has been approved, that got approved earlier this year by a different company called Onward. And they got the approval based on a similar pivotal clinical trial that is for people with spinal cord injury looking at arm and hand function. This bladder study looks at people with spinal cord injury, MS, and stroke, and looking at neurogenic bladder dysfunction.
Okay, guys, any more questions? All right. Dr. Sachdeva, thank you very much.
Thank you.
Thank you for coming out. Guys, I'm going to bring up the president of the Spastic Paraplegia Foundation, Greg Pruitt, and he's going to finish our day out. Okay, guys? Here he comes.
A couple of days with a lot of information, and I know you're probably mentally and maybe even physically worn out, but a lot to take in, and we only get together a couple of days a year, and a lot happens, and it's important, we think, for you guys to know the cutting edge in every way that we can. as we said, we came to Washington to improve and create greater relationships with the folks in Washington who handle money that comes through places like NIH, approvals that come through FDA, and with our congressional people. And we've got a couple of our U.S. senators who have sent messages over to you. One Republican, one Democrat, for whatever that matters. They're both on the Senate Rare Disease Caucus. And so first, let me, if we are ready, if we're ready, our first message is going to be from Senator Chuck Grassley from Iowa.
Thank you very much for this opportunity to join you this very day and say a few words during your annual conference. Like many of you, I wake up every day with gratitude to have another bite at the apple. No matter the responsibilities on our to-do lists or the challenging things confronting us every day, each of us has dreams and aspirations to chase with the dawn of a new day. As a poet during the Age of Enlightenment wrote hundreds of years ago, and I quote, "Hope springs eternal in the human breast," end of quote. To me, that means every sunrise brings a new chance to solve problems, serve others, and squeeze another drop of happiness from life. As a member of the Rare Disease Congressional Caucus, I'm committed to helping you secure a higher quality of life and lower barriers to life-saving treatments and therapies. Tens of millions of Americans are members of the rare disease community. You and your loved ones and caregivers navigate medical appointments, deploy exhaustive efforts to cut through red tape, and you never give up. You reflect the strength and resilience of the American spirit. Throughout my service in the United States Senate, I've worked to make sure government gets out of the way. Uncle Sam should not be the gatekeeper to say who does or does not get access to life-saving treatments. Rationing care is not the American way. Socialized medicine translates to longer wait lines and delayed cares. Just ask those people that live in the countries where they have government-run health care. Now, there are more than 7,000 rare disorders that impact more than 30 million Americans. Many of these diseases are considered ultra-rare. In some cases, fewer than 100 people are affected. No matter the disease or the diagnosis, each of you share a common purpose. That purpose is to survive and thrive in the pursuit of health and happiness. When the government dictates which treatments are available, we devalue people living with rare diseases. And that, of course, extinguishes hope. During my first term in the Senate, Congress passed legislation called the Orphan Drug Act. That act gives financial incentives to drug companies to develop treatments for rare diseases. In 2018, I was proud to co-sponsor legislation called the Right to Try Law. Today, I'm spearheading bipartisan reforms to help patients with complex medical needs afford life-saving prescription drugs and working to ensure a regulatory regime fosters innovation and pursues the miracles of modern medicine for all patients. From neurological disorders to rare cancers, pediatric and hereditary diseases, I want each of you to know this: your voices are heard. Your grassroots movements makes a big difference here in Washington, D.C. And I want you to know that this senator's door is always open. Together, we'll lead with hope and continue to raise awareness and beat the drum for promising medical research and affordable access to life-saving cures, treatments, and therapies. Keep up your good work, and God bless that work.
That's our message from Senator Grassley, and as you know, he's a Republican. In just a moment, we're going to have a message from Senator Klobuchar from Minnesota, who is a Democrat. The point I want to make in that regard is you're going to hear both of them talk about how they want to support our cause, our circumstance, our life issues. So it really doesn't matter who's in what house or what majority's in the Senate or the House. What it means is we've got to constantly make our voices heard. It may or may not make a difference, but it sure will make a difference if we don't make our voices heard. And you heard both of those reps who came yesterday from the congressional side, from the House side, both affirm that those calls that we make collectively are important. So I want to, again, encourage you, we're on the front line every day pushing, trying to move this thing inch by inch towards some meaningful treatment. And we need your help here on Capitol Hill. When you get those messages, please send them. Get your friends to send them. You may get similar requests from other rare disease organizations. It doesn't hurt to do some of theirs as well. These people in Washington need to hear from you. And even if it's the same message, it makes a difference whether they get 3 or 300 or 3,000. So please help in that way any way you can. Just a moment before we listen to Senator Klobuchar, let me share a couple of other things. Some of you have asked, when and where is next year's conference? Well, we can't tell you today. As we work with SP CERN, one of the things they've talked about is they'd like to now have they're going to have an annual one-day conference. And so we're going to look at coordinating with them next year to marry our conference up with theirs so that they are together with us and so on. I can tell you we're looking at the last 2 weeks of July. We want to get this back in place where families with children can be here. So that's the time frame we're looking at. And when we get home this next week, we'll start immediately trying to peg a location. And as soon as we know that, we'll get that message out to you guys by e-blast. I want you to do a couple of things for me real quickly. These two guys in the back, Jeff and Rick, they're part of your family. They're here every year, and we appreciate what they do. Give them a round of applause. What you see on YouTube wouldn't be possible without these two guys. And this MC keeps us moving. He's been doing this for years. Let's give Tim a hand as well. And most of all, we certainly want to thank our speakers, our researchers, clinicians, our sponsors who helped put this conference on. But most of all, I want to thank all of you who are here. It's the camaraderie, the strength that we collectively have together that's going to help make some good things happen. We sure hope and pray. So hang in there with us. Let's keep fighting this battle together. And now let's hear what Senator Klobuchar has to say to us.
Hello to all my friends at the Spastic Paraplegia Foundation's 22nd Annual Conference. I want to thank SPF President Greg Pruitt and my good friend and SPF board member Jackie Wellman, and the patients and families living with hereditary spastic paraplegia and primary lateral sclerosis. Across the country, an estimated 20,000 Americans are living with HS paraplegia and PLS sclerosis. These conditions are rare, affecting roughly 3 to 5 people per 100,000 nationwide, but their impacts on patients, families, caregivers is profound. Your courage, your stories, and your voices are what drive all of us to do better. As a co-chair of the Bipartisan Rare Disease Caucus, I know how important it is to have so many strong partners in the fight against these rare neurological diseases. Together, we are making real progress. The Rare Disease Congressional Caucus has worked directly with the FDA to begin to improve its review process. In 2023, after a lot of work and a lot of work with advocates like yourselves, we successfully pushed the FDA to finally take a close look at its review process for rare disease products. This effort led to the FDA creation of the Rare Disease Innovation Hub, better coordination between FDA center leadership and reviewers, and new opportunities for the agency, patients, scientists, foundation, and advocacy groups to work together. Patients, researchers, and advocates now have a seat at the table, and FDA's reviewers can finally access the information they need when they need it. We've actually had some improvement, at least the first part of this year and last year, in the number of stem cell and other treatments that have been improved, and that slowed down this last quarter. I'm watching every moment, so we're calling attention to that to get it back on track. I'm focused on creating permanent funding for the Rare Disease Innovation Hub and maintaining strong federal funding and staffing for rare disease research and drug review. And I'm pushing back against the attacks on science and the resources that make medical research possible. With all the progress we're making with gene mapping the human genome, research trials, and AI, we're truly at the cusp of groundbreaking developments when it comes to diagnosing, treating, and curing rare diseases. Now is not the time to see that in the rearview mirror. Now is the time to drive forward and make sure that we're continuing to increase investments. I was especially encouraged by the recent approval of the $8.4 million NIH U54 grant to establish the Spastic Paraplegia Centers of Excellence Research Network. This is a groundbreaking achievement. It shows what can happen when you work together to drive progress. Last Friday marked World HSP and PLS Day, a powerful reminder of why your work matters. I'm committed to continuing to work with anyone in Washington, even if we don't agree on much, anyone who shares our goals here, your goals and my goals, to expand research funding, to improve access to coordinated and compassionate care, and to ensure that the NIH and FDA remain strong and are focused on neurological diseases. Thank you for everything you do, for your advocacy, your determination, and your hope. You remind us every day what's possible. Keep up the great work.
As she got toward the end of her remarks there, she said it's time. Some of you who were in Pittsburgh in 2018, one of our themes then was it's time. And it is time. And we're making progress in those directions. I want to thank one more group of people real quickly. Our volunteers that have worked the table out there, Norma and Linda and Marianne. Thank you to all of you for a great job. We appreciate you so much. And one last charge as we go. And I know I sound kind of like a political candidate. I can't help that. I was one for most of my life. Or somebody asked me this week, had I coached some? I've coached a little bit too. But here's where we are. We're at a point where we're closer, I believe, to a meaningful treatment for both HSP and PLS than we've ever been before. We got here because so many people came in front of us and pushed this. And we've got to keep pushing. And that means we've got to look at every possible. You've seen some things here today, deep brain stimulation. We hadn't really thought much about that before. You talk about drug repurposing, gene therapy, CRISPR. There are so many things that we've got to try to be on top of and stay on top of as you help us raise money, and we, through our scientific advisory board and the research that we as a board do, figure out the best places and best ways to spend that money to try to get toward that finish line as quickly as possible. Your board's going to do all it can, but we're only as strong many times as you are with us. I encourage you, the first Thursday of every month, we'd love to turn on that Zoom machine, box, computer, and see that screen filled with more folks than we can recognize who are listening to what each of these committees are doing and hearing ways that you can help from day to day and week to week. SPF talks, those come at very different times because the presenters, it's kind of on their schedule. But there's a lot of good information there from clinicians, from strategists, from people like you sometimes who are just sharing how you live with the conditions that you live with. So we're only as strong as we are together. So I just want to challenge you to stay plugged in, keep your shoulder to the wheel, and help us do the same. God bless you for being here. We hope when you find out where and when next year, you immediately put it on your calendar and plan to be there. We're going to talk next year about how much closer we are to that success. God bless you. Be careful going home.